What if the universe is far stranger than anything we have dared to imagine? Beyond the familiar neighbors in our own solar system, there exist mysterious and unexplained objects that whisper secrets of cosmic enigmas yet to be uncovered. From exotic planets with weather so extreme it defies belief to entire galaxies behaving in ways that challenge the very foundations of our understanding, each new discovery pushes the limits of science further than ever before. These revelations open doors to the unexpected and the unexplainable, as faint and puzzling signals hint at phenomena we have never encountered. The unknown beckons us to question every assumption we hold about reality. As new tools and technologies emerge to observe the far reaches of space, our imaginations are captivated by the possibility of alien megastructures and bizarre stellar behaviors that defy conventional theories. The discoveries expected in the year 2025 promise to bring insights beyond anything we have yet grasped. This journey through the cosmos is one where every answer only deepens the mystery, urging us to embrace the awe and excitement of the unknown. Space has already revealed objects so strange and intriguing that they challenge our most basic concepts of how the universe works. Consider the neutron star, the collapsed core of a massive star that exploded in a supernova. These stars are incredibly dense, so dense that just a tiny spoonful of their material would weigh as much as a mountain on Earth. Yet their density is only part of their marvel. Neutron stars often spin at dizzying speeds, emitting beams of radiation that sweep through space like cosmic lighthouses. When these beams pass by Earth, we detect them as pulsars, steady and rhythmic signals from the depths of the cosmos. Then there are rogue planets, worlds that drift alone through the galaxy without the warmth or guidance of a parent star. These lonely travelers float in the cold darkness of space, potentially holding conditions that could support life despite the absence of sunlight. Their mere existence challenges our ideas about how planets form and behave, and they raise profound questions about the dynamics of celestial bodies. Another profound mystery lies in dark matter, a substance that makes up a significant portion of the universe's mass yet remains completely invisible to us. It neither emits nor reflects light or energy, and can only be detected through its gravitational effects on galaxies and clusters of galaxies. Scientists believe that unlocking the secrets of dark matter could reveal truths about the very fabric of reality and the forces that shape the cosmos. In the unfolding story of the universe, these strange and extraordinary phenomena remind us how little we truly know and how vast the realm of the unknown remains. Each discovery is not just an answer, but an invitation to explore, to question, and to imagine what lies beyond the edge of our current understanding. Additionally, we cannot overlook the astonishing extremes of weather found on some of the gas giants in our solar system, such as Jupiter. One of the most iconic features of this enormous planet is its Great Red Spot, a colossal storm that dwarfs Earth in size. This swirling cyclone, larger than our entire planet, has been raging relentlessly for hundreds of years. The persistence and scale of this storm reveal the extraordinary and complex atmospheric dynamics that can arise when conditions align just right on these giant worlds. It is a vivid example of nature's raw power on a cosmic scale. Finally, another remarkable phenomenon that captures the imagination of scientists and enthusiasts alike is the existence of gravitational waves. These ripples in the fabric of space-time were first predicted by Albert Einstein over a century ago, yet it was only in recent years that we succeeded in observing them directly. Gravitational waves are produced by some of the most violent and energetic events in the universe, such as the collision of black holes or neutron stars. Each time we detect these waves, it is like opening a new window into the workings of the cosmos, allowing us to explore and understand the dynamic and often chaotic forces shaping our universe. The cosmos continually surprises us with mysteries that challenge our understanding, from solitary rogue planets wandering through the void to immense storms that dwarf anything on Earth, and the elusive nature of dark matter, which still puzzles scientists worldwide. Each new discovery pushes the boundaries of human knowledge and reveals that space is a realm filled with wonders, both strange and thought-provoking. Take rogue planets, for instance. These solitary wanderers drift alone through the vast emptiness of space, far from the warmth of any star. Their origins are fascinating and often begin in environments much like those that form regular planets. Typically, they emerge within a protoplanetary disk, a swirling ring of dust and gas surrounding a young star. Over time, particles in these disks collide and clump together, slowly building larger bodies that can eventually become planets. However, the story of a rogue planet can take a dramatic turn. Sometimes, through violent gravitational interactions with other planets or the star itself, these worlds are ejected from their home systems. The gravitational forces at play can be so powerful that they fling a planet into the dark reaches of space, forever severing its ties to the star that once nurtured it. Once cast out, these planets lead a nomadic existence. Despite their isolation from stellar light and heat, some rogue planets retain warmth left over from their formation or generate heat internally through radioactive decay within their cores. This residual energy may allow them to hold on to thin atmospheres or even sustain marginally habitable conditions for long periods. The search for these lonely worlds not only fascinates astronomers, but also sheds light on planetary formation and evolution under extreme conditions. Rogue planets stand as a testament to the chaotic, sometimes violent processes that govern the universe, reminding us that even planets can become cosmic drifters, endlessly roaming the vast, uncharted realms of space. Another astonishing cosmic curiosity is the ultra-diffuse galaxy. These galaxies challenge our understanding of what a galaxy should look like. Unlike the bright, tightly packed clusters of stars found in typical galaxies, ultra-diffuse galaxies are incredibly sparse, with stars spread thinly over an enormous volume. Imagine a dense, vibrant galaxy full of stars, and then compare it to a faint fog barely visible against the backdrop of space. That is what an ultra-diffuse galaxy resembles. The mystery behind their sparse nature lies in their formation and history. Scientists theorize that these galaxies may have had their gas and stars stripped away during collisions or close encounters with larger galaxies. Without the raw materials to form new stars, their ability to shine brightly diminishes, leaving behind a ghostly silhouette. What makes ultra-diffuse galaxies even more intriguing is the possibility that they contain a large amount of dark matter, far more than the visible stars they contain. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence can be detected by observing its gravitational effects on the motion of stars within these galaxies. This hidden mass may provide the gravitational glue that holds these diffuse galaxies together, even though their visible matter is scant. This strange balance between visible and invisible matter raises profound questions about the nature of galaxies and their evolution, hinting at complexities in the universe we are only beginning to understand. Finally, consider the extraordinary concept of stars composed entirely of dark matter. Dark matter makes up a significant portion of the universe's mass, yet it remains one of the greatest scientific mysteries because it does not interact with light or ordinary matter in familiar ways. Unlike the gas and dust that collapse under gravity to ignite nuclear fusion and form stars like our sun, dark matter does not behave the same way. It lacks the properties needed to clump tightly or ignite fusion reactions. Some theoretical models suggest the existence of dark stars, which would be hybrid objects made of both dark matter and ordinary matter. However, the idea of a star made purely of dark matter is far more complicated. Since dark matter particles interact very weakly, they tend to spread out rather than gather densely. This makes it extremely difficult for dark matter alone to form stable star-like structures. This profound difference highlights just how much we still have to learn about dark matter and its role in the universe. While the concept of dark matter stars remains speculative, it pushes the boundaries of astrophysics and invites scientists to explore new possibilities beyond the limits of what we currently observe. Moreover, dark matter continues to loom as one of the most enigmatic components of our universe. Invisible and undetectable through conventional electromagnetic means, its effects ripple across the cosmos like the silent architecture behind a grand cathedral. Its presence does not declare itself with light or heat as stars do, but instead exerts an invisible force shaping the large-scale structure of the universe. Galaxies do not merely float in space, they spin and cluster within immense halos of dark matter. These halos act as gravitational scaffolding, drawing ordinary matter together, guiding the formation of stars, galaxies, and galaxy clusters. It is not a source of illumination or warmth. It does not shine. It does not radiate. It does not burn. Yet without it, the cosmos would not have formed in the intricate web of structure that it exhibits today. Therefore, while dark matter is a critical participant in the orchestration of cosmic evolution, the concept of stars composed entirely of dark matter remains relegated to the realm of theoretical physics. It is a thought experiment, an intellectual probe into the possible extremes of cosmic composition rather than a phenomenon supported by empirical observation. In the absence of light and in defiance of detection, these hypothetical dark stars remain elusive, existing only in mathematical models and speculative hypotheses. They are shadows within shadows, artifacts of curiosity rather than confirmed celestial bodies. In contrast, there are objects that have wandered into our observational reach and left us in awe, not through invisibility, but through their unprecedented characteristics. One such traveler arrived in 2017. It was a visitor from the stars, a messenger from beyond, carrying with it questions far greater than its size. Astronomers named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Unlike the countless comets and asteroids that populate our solar system, Oumuamua did not belong here. It came from beyond, an interstellar interloper, the first of its kind ever recorded. It did not arrive with fanfare, but it ignited immediate fascination. Spotted as it was speeding past Earth, its trajectory indicated it had entered from outside the solar system and would soon leave again, never to return. Its shape was unlike anything previously documented. Long, slender, and spinning, Oumuamua resembled a cosmic javelin. It tumbled end over end, spinning every 8 hours as it surged through the solar system. The proportions were extreme. It was roughly 10 times longer than it was wide, a form rarely, if ever, seen in natural celestial bodies. But the mystery did not end with its shape. As Oumuamua swung around the sun, scientists detected a subtle acceleration that couldn't be fully explained by gravitational influences alone. Normally, comets accelerate when sunlight warms their icy surfaces, releasing jets of gas and dust in a process known as outgassing. This reactive force can nudge a comet slightly, changing its speed and direction. Yet Oumuamua showed no visible signs of outgassing. No tail, no cloud, no trace, only acceleration. This contradiction split the scientific community. Some clung to conventional theories, hypothesizing that Oumuamua's outgassing was composed of invisible materials or that it was shedding gas in ways undetectable by our instruments. Others dared to speculate more boldly. Could it be an artificial object? Could its acceleration be the result of solar radiation pressure acting on a thin, metallic structure, perhaps akin to a solar sail, a method of propulsion suggested for advanced spacecraft? The idea was controversial but not dismissed outright. For a moment, the boundary between science and science fiction blurred. While the majority leaned toward a natural explanation, the very existence of an interstellar object raised new questions. Where did it come from? What forces shaped it? And are there more like it, silently threading their way through the darkness between stars? The story of Oumuamua is not just one of scientific inquiry, but also of cosmic humility. It is a reminder that the universe is not static. It moves, it sends emissaries, it surprises us, and it still contains phenomena beyond our comprehension. This same sense of wonder carried through the rest of the year, a period marked by discoveries that are steadily transforming our understanding of the cosmos. One of the most profound breakthroughs was in the realm of gravitational waves, ripples in the very fabric of space-time. These disturbances, predicted over a century ago by Albert Einstein, are generated by cataclysmic events: black holes merging, neutron stars colliding, massive explosions in the deepest regions of space. Once undetectable, these whispers from the universe are now being heard with greater clarity, thanks to the development of advanced observatories like LIGO and Virgo. These instruments, operating with near unimaginable sensitivity, can detect distortions smaller than a proton's width. And through them, we are now able to observe the universe in a completely new way. Gravitational wave astronomy has become a new sense, like acquiring hearing after a lifetime of silence. With it, we have recorded the merger of black holes that occurred billions of years ago, their violent union releasing energy on a scale we can barely imagine. These observations provide insights into the nature of gravity, the behavior of matter under extreme conditions, and the origins of the heaviest elements in the periodic table. Parallel to these discoveries are remarkable findings in the hunt for exoplanets. Worlds orbiting stars beyond our sun, once the domain of speculation, are now confirmed in the thousands. Each one carries the potential to challenge our understanding of planetary formation and habitability. Some are gas giants spiraling close to their stars. Others are rocky, Earth-like bodies nestled in the so-called Goldilocks zone, the habitable region where temperatures might allow for the existence of liquid water. This year, researchers have not only identified more such candidates, but have also begun to characterize their atmospheres. Using techniques like transit spectroscopy, scientists can infer the chemical makeup of an exoplanet's atmosphere as it passes in front of its star. They look for biosignatures, gases like oxygen, methane, and water vapor that could hint at biological processes. With the launch of new space telescopes like the James Webb Space Telescope, the precision of these observations has increased dramatically, opening the door to the possible identification of life-supporting conditions on distant worlds. The implications are staggering. For millennia, humanity looked up at the stars and imagined other worlds. Now we know they are real. We know some are temperate. We know some have clouds, wind, even seasons. And we are only just beginning. Together, these discoveries form a tapestry of cosmic revelation. Dark matter, elusive and foundational. Interstellar visitors like Oumuamua, mysterious and rare. Gravitational waves echoing through time from events unimaginably distant. And exoplanets, hinting at life beyond Earth. Each thread pulls us further into the universe's story. A tale not yet fully told, rich with possibility of woven through space and time. Every year, every discovery, every observation adds another verse to this grand epic. And in our quest to understand the cosmos, we are not just gazing outward, we are reaching inward, into the very nature of reality itself. And yet, in the quiet, endless reaches of the cosmos, humanity continues to unveil astonishing secrets that reshape our understanding of reality. The universe, once seen through the blurry lenses of early optical telescopes, now stands revealed in breathtaking clarity thanks to the revolutionary advancements in modern observational instruments, chief among them, the James Webb Space Telescope. This extraordinary marvel of engineering has, in its brief tenure since deployment, irrevocably altered the landscape of astrophysics. The James Webb Space Telescope is not merely another scientific tool, it is a time machine, capable of gazing into the deep, ancient past. By capturing light that has traveled for billions of years, Webb allows us to witness the universe as it was when galaxies were first forming, mere hundreds of millions of years after the Big Bang. These deep space images have revealed clusters of primordial galaxies, some arranged in surprising configurations that challenge the standard models of early cosmic development. The starlight from these youthful galaxies, stretched and reddened by the expansion of the universe, paints a vivid and detailed tapestry of what once was and what may still lie beyond. Scientists are not just looking farther, they are also thinking deeper. Armed with this new data, astrophysicists are re-examining some of the most enduring enigmas in cosmology, those of dark matter and dark energy. Though these two mysterious constituents make up the vast majority of the universe's total content, they remain elusive, intangible, and largely theoretical. Dark matter, believed to provide the gravitational scaffolding necessary for galaxy formation, has still never been directly detected. Dark energy, the force thought to be accelerating the universe's expansion, behaves in ways that are antithetical to all other known forms of energy and matter. In 2024, the scientific community witnessed a renewed vigor in its attempts to pierce this veil of mystery. International collaborations launched pioneering experiments aimed at detecting dark matter particles by observing potential interactions with highly sensitive detectors buried deep underground, far from cosmic noise. These detectors, nestled within old mine shafts and shielded by thick layers of rock, are searching for infinitesimal nudges, imperceptible flashes of energy that might reveal the passing of dark matter through ordinary matter. At the same time, astronomers continued to refine measurements of how dark energy affects the large-scale structure of the universe. They analyzed the acceleration of galaxies as they drift apart and measured subtle shifts in cosmic light to understand whether dark energy's influence is constant or perhaps even changing over time. These advances have not provided all the answers, but they have offered tantalizing hints and opened new avenues for exploration. And while we look backward to the ancient light of the cosmos, our gaze also turns outward and forward to distant stars and the strange planets that orbit them. The search for exoplanets has become one of the most dynamic frontiers in modern astronomy. What began as the discovery of a handful of planets beyond our solar system has blossomed into a catalog of thousands, each with unique characteristics that stretch the imagination. One particularly compelling class of these newfound worlds is known as hot Jupiters, enormous gas giants that orbit perilously close to their host stars. These planets are so near to their suns that their atmospheres are often scorched to thousands of degrees. This was a surprising revelation because in our own solar system, gas giants such as Jupiter and Saturn are found in the colder, more distant regions. The presence of hot Jupiters implies that planets may not always stay where they are born. Instead, they might migrate across their solar systems, nudged and jostled by gravitational interactions or driven by disk instabilities during their formative years. This discovery fundamentally reshapes how scientists model planetary evolution. Even more intriguing are the so-called super-Earths, planets with masses higher than Earth's but significantly less than Neptune's. Some are rocky, some are watery, some may be shrouded in thick atmospheres of exotic gases. Each new super-Earth hints at a broader range of planetary conditions than was ever imagined. These worlds suggest that Earth-like planets might not be rare after all, and that habitable environments could exist in forms that defy our terrestrial biases. Moreover, astronomers have observed planetary systems with orbital architectures that appear chaotic, even violent. Some exoplanets follow highly eccentric paths, swinging in and out from their stars in dramatic ellipses. Others are locked in orbital resonances, locked together in intricate gravitational dances. In systems with multiple stars, planets may experience gravitational tug-of-wars that result in tilted or unstable orbits. These revelations underscore the diversity and complexity of planetary systems throughout the galaxy and invite a re-examination of how planets form, migrate, and survive over billions of years. These planetary discoveries are not just curiosities. Each one is a clue, a data point in an emerging narrative about how common and how diverse planetary systems may be. Each exoplanet found is a puzzle piece, suggesting new possibilities about the conditions under which life might arise, evolve, or perish. And then, in one of the most profound investigations of the year, scientists turn their attention once again to the oldest light in the universe, the cosmic microwave background. This faint radiation is the afterglow of the Big Bang, a relic signal that bathes the universe and provides a snapshot of its state when it was less than 1 second old. It is not visible to the naked eye, but with the right instruments, it reveals a pattern of tiny fluctuations in temperature and intensity. These fluctuations are the imprints of quantum irregularities, magnified during the universe's rapid inflationary phase that would eventually grow into galaxies, stars, and planets. In 2024, new high-precision measurements of the cosmic microwave background unveiled unexpected anomalies in these patterns. Certain regions showed more variation or less than theoretical models predicted. These deviations, though subtle, hinted at structures forming far earlier than current physics allows. Some scientists have proposed that these irregularities might be linked to variations in the distribution of dark matter, potentially indicating that this invisible substance was influencing the structure of the universe from the very beginning. The implications are staggering. If dark matter played an early and active role in shaping the cosmic microwave background, it could mean that our theories about the timeline of the early universe need revision. It could suggest that the interplay between dark matter and normal matter was more complex than previously thought. Some researchers have even floated the possibility that we are witnessing the fingerprints of new physics entirely, beyond the standard model, waiting to be decoded. These developments, spanning the deepest reaches of space and the earliest epochs of time, are more than scientific milestones. They are the foundation stones of a new cosmology, an evolving story that is far from finished. They reveal a universe that is not only vast and ancient, but also dynamic, intricate, and mysterious beyond comprehension. In the silent language of starlight and gravity, in the shadows of dark matter and the whispers of ancient radiation, we are beginning to read the autobiography of the cosmos. Each discovery pulls back another veil, revealing a truth more complex and beautiful than we imagined. Each question answered births a dozen more, igniting the minds of researchers and dreamers alike. This is the essence of the human endeavor: to know, to seek, to understand. And so the exploration continues, not with certainty, but with wonder, not with finality, but with curiosity. For the universe does not yield its secrets easily. It demands patience, imagination, and a willingness to be forever humbled by the magnitude of all that remains unknown. Furthermore, some researchers have suggested that these anomalies may hold the key to unlocking entirely new dimensions of physics, possibly alluding to forces or particles that have remained hidden from the prevailing frameworks of cosmology. These irregularities, far from being dismissed as mere observational noise, have become focal points of theoretical intrigue, urging scientists to reconsider foundational assumptions about the infancy of the universe. The implications ripple outward, transforming the way we conceptualize the cosmos from its first few fractions of a second. They compel us to explore uncharted territories of knowledge, illuminating cracks in our current models that could ultimately usher in a paradigm shift in our understanding of existence itself. This possibility invites the scientific community to embark on further inquiries, not just to refine current theories, but to venture into entirely new ones, fueled by evidence that refuses to conform to expectations. As these analytical efforts gain momentum, what once appeared as subtle inconsistencies in cosmic data now stand as compelling indicators of something profound yet unseen. Each unexplained signal or deviation offers a tantalizing possibility that the universe may be governed by principles not yet discovered, operating on levels we are only beginning to glimpse. These revelations do not merely fill in the blanks of an already sprawling story of cosmic origin. They reframe the narrative entirely, suggesting that what we understand as universal truth might in fact be a localized chapter in a much larger and stranger cosmic manuscript. Throughout decades of observing the skies, astronomers have encountered signals so enigmatic that they have challenged our most basic assumptions about what is possible beyond our planet. Among these mysterious phenomena, few have sparked as much intrigue as a singular event that occurred on a summer night in 1977. At the Big Ear Radio Observatory in Ohio, astronomer Jerry Eman was analyzing the printouts from a radio telescope tuned to the frequency of the hydrogen line, the natural wavelength many scientists believe would be used in an interstellar broadcast. For 72 seconds, the telescope detected an exceptionally strong narrowband radio signal that stood out from the background with such clarity and intensity that Eman circled the data and scribbled one word in the margin: "Wow." That moment, immortalized by what would become known as the wow signal, has since become a cornerstone in the ongoing search for extraterrestrial intelligence. Despite countless attempts to identify its source or to replicate the event, the signal remains unexplained. It did not repeat, and no nearby stars or celestial objects were identified as possible emitters. Decades of follow-up studies and improved instrumentation have failed to detect anything like it again, leaving the scientific community with both tantalizing hope and gnawing uncertainty. The wow signal embodies the tension between the known and the unknown in our quest to find life beyond Earth. Since then, astronomers have uncovered other radio signals that, while not as dramatic, bear their own peculiar signatures. Some emanate from the distant reaches of space, their origins concealed within galaxies millions or even billions of light years away. These fast radio bursts, or FRBs, are pulses of radio waves that flash and disappear within milliseconds. Some are one-time events, others repeat, though with no apparent pattern. Their brevity and intensity challenge the limits of our understanding, prompting theories that range from natural astrophysical phenomena to speculative concepts involving alien technology. In many cases, natural explanations seem plausible. Pulsars, which are rotating neutron stars emitting beams of radiation, can produce regular and precise signals. Magnetars, a type of neutron star with an extremely powerful magnetic field, are also capable of generating sudden bursts of energy. Supernovae, black hole mergers, and even the gravitational lensing of signals as they pass massive celestial bodies have all been invoked as possible sources. However, what remains fascinating is that even these explanations are relatively new to science and were, not long ago, themselves considered hypothetical. Complicating the picture further is the sheer scale of the universe. Signals that traverse such immense distances undergo distortion, redshift, and interference. A transmission that begins as a coherent pattern might arrive after billions of years as a whisper in the static. Additionally, distinguishing between signals generated by intelligent sources and those produced by natural processes requires a level of precision and statistical rigor that few fields demand. A signal's origin might lie in the unknown mechanics of star systems, or it might be the distant echo of another civilization. But in the vast silence of space, certainty is elusive. Despite this, the very act of listening, of scanning the stars for meaning, speaks to something essential about the human spirit. The search for extraterrestrial intelligence is not only a scientific endeavor, but a philosophical one. It reflects our need to connect, to know we are not alone, and to understand our place in a universe that often feels incomprehensibly vast. Even without definitive proof, the process fuels technological innovation and stretches the boundaries of imagination. Every new detection, every unexplained anomaly is a spark that keeps the search alive, driven by curiosity and the hope that somewhere amid the celestial static, a message awaits us. In this broader context of cosmic discovery, our understanding of galaxies themselves is undergoing radical transformation. With the advent of more powerful telescopes and refined observational techniques, astronomers are peering deeper into the universe's past than ever before, and what they are finding continues to challenge long-standing theories. Among the most intriguing revelations is the discovery of ultra-faint dwarf galaxies, tiny assemblages of stars that orbit larger galaxies and are nearly invisible to traditional instruments. These galaxies are astonishing in their composition. They contain immense quantities of dark matter, but relatively few stars, giving them extremely low luminosity. Their existence poses a significant challenge to classical models of galaxy formation, which assumed that star formation and visible mass would go hand in hand. Instead, these dwarfs suggest that galaxies can be dominated by unseen matter to a degree not previously imagined. They may also hint at a hidden population of similar structures cloaked in the gravitational halos of larger galaxies, waiting to be uncovered. If so, the actual number of galaxies in the universe may be far greater than current estimates suggest. This would not only alter our calculations about the distribution of matter in the universe, but also reshape our understanding of how galaxies grow, interact, and evolve. Another profound revelation comes from the study of starburst galaxies. Galaxies that in certain periods of their history undergo episodes of extremely rapid star formation. Some of these galaxies are found in the early universe, less than 1 billion years after the Big Bang. During these starburst events, new stars are formed at rates hundreds of times higher than what we see in the Milky Way today. These galaxies shine with intense ultraviolet light and appear to be burning through their gas reserves with startling efficiency. This contradicts earlier theories suggesting that early galaxies formed stars at a slow and steady pace. The presence of such rapid star-forming regions in the young universe implies that the conditions during that epoch were far more dynamic than previously believed. Turbulent gas flows, gravitational interactions, and perhaps even feedback from the earliest generations of supernovae might have catalyzed this frenetic pace of star creation. These findings suggest that galaxies may mature and transform in ways that deviate significantly from the elegant, gradual processes once assumed. Moreover, the discovery of galaxies with unexpectedly high metallicity adds another layer of complexity. Metallicity, in an astronomical context, refers to the abundance of elements heavier than hydrogen and helium. Since these elements are forged in the cores of stars and spread through space via supernovae, a high metallic content is generally associated with younger galaxies that have undergone multiple generations of star formation. However, astronomers have detected ancient galaxies, dating back to the early universe, that exhibit unexpectedly high concentrations of these heavy elements. This contradicts the assumption that early galaxies would consist mostly of pristine, primordial matter. Instead, it suggests that some galaxies experienced a rapid and intense burst of star formation, followed by efficient recycling of stellar materials. Such activity implies that the cosmic enrichment process might occur much faster and more violently than previously imagined. These metal-rich galaxies challenge the standard timelines of cosmic chemical evolution and force theorists to reconsider how quickly and efficiently matter cycles through different phases of star life. Taken together, these discoveries paint a picture of a universe that is far less predictable and far more intricate than earlier models proposed. Rather than a slow and orderly progression from simplicity to complexity, the cosmos appears to have evolved through bursts of chaos, hidden structures, and phenomena still not fully understood. Each newly discovered galaxy, signal, or anomaly is not just a data point, but a clue in a grand, unfinished puzzle. A puzzle that spans time, space, and the boundaries of human comprehension. As we continue to probe deeper, the universe rewards our questions not with easy answers, but with new mysteries, each more fascinating than the last. Furthermore, the revelation of massive galaxies existing far earlier in the universe's timeline than previously believed has sent ripples through the very foundation of modern cosmological thought. These immense galactic structures, brimming with stars and intricately formed systems, were not expected to be found at such an early cosmic epoch, mere hundreds of millions of years after the Big Bang. Yet, their existence is undeniable. Observatories like the James Webb Space Telescope have peered deep into the ancient light of the universe and detected them. These sprawling stellar metropolises that seem to defy the chronological framework set by long-standing astrophysical models. This unexpected emergence of early massive galaxies presents a profound puzzle. According to conventional models, galaxies of such size and complexity should have taken billions of years to assemble. Their discovery so early in cosmic history suggests that the processes of star formation, gas accretion, and galactic structuring may have unfolded at a much faster pace than scientists have accounted for. The universe, it seems, might have matured with a swiftness that calls into question the bedrock assumptions about its formative years. Each new observation acts as both a revelation and a revision, a compelling push against the limits of our knowledge. These findings do more than astonish. They emphasize the ever-changing nature of scientific understanding, especially in cosmology, where timelines stretch across unimaginable scales. Our models are not static blueprints etched in stone, but living frameworks, constantly reshaped by the light that reaches us from across space and time. Every massive galaxy discovered in the early cosmos is not just a structure of stars and gas. It is a message from the past, a challenge to the present, and a guidepost for the future of astronomical theory. As we navigate the uncharted territories of the universe, we encounter other mysteries no less captivating. Among these are the enigmatic worlds known as hot Jupiters, gas giants resembling Jupiter in mass and composition, but residing perilously close to their parent stars. Picture, if you will, a world dozens or even hundreds of times the mass of Earth, yet orbiting its star at a blistering proximity. These planets are so close that their orbital periods can be just a few Earth days long, and their atmospheres, scorched by stellar radiation, blaze with temperatures far exceeding anything found on Jupiter or Saturn. The question arises, how did such massive planets come to dwell so close to their stars? The answer lies in the dynamic and often chaotic ballet of planetary migration. When a solar system is young, planets begin their lives within a rotating disk of gas and dust. Gas giants like Jupiter likely form in the cooler, more distant regions of this disk, where icy materials can clump together and accrete hydrogen and helium. But they do not always stay put. Through gravitational interactions with other planets or with the protoplanetary disk itself, these giants can be drawn inward, spiraling towards their stars in a cosmic migration that transforms their destiny. Once a hot Jupiter settles into its tight orbit, its environment becomes extreme. The searing heat causes atmospheric gases to expand, forming vast envelopes of storm-ridden clouds, chemical reactions, and even supersonic winds. Some hot Jupiters display phenomena never seen in our solar system, such as inverted temperature layers, glowing upper atmospheres, and metallic clouds made of vaporized elements. Studying them allows scientists to probe the physics of atmospheric chemistry under alien conditions, offering a deeper understanding of how planetary systems evolve and diversify across the galaxy. If hot Jupiters showcase the bizarre consequences of planetary migration and extreme proximity to a star, then carbon planets stretch the limits of what worlds can be made of. Imagine a planet forged not of silicate rock and iron like Earth, but of carbon-rich materials subjected to immense pressure, where deep below the surface, carbon atoms are squeezed into crystalline lattices, diamonds as far as the eye cannot see. This may sound like the fabric of fantasy, but astrophysicists suggest it is theoretically possible. Carbon-rich planets could arise in star systems where the initial molecular clouds were abundant in carbon and lacked sufficient oxygen. Over time, as these planets form and undergo geological differentiation, the immense pressures in their mantles could transform carbon into diamond. One of the most tantalizing candidates is the exoplanet 55 Cancri E, located roughly 40 light-years away. Classified as a super-Earth, this planet is estimated to be twice the size of Earth and several times more massive. Its density and chemical signatures have led researchers to hypothesize that a significant portion of its interior might be composed of carbon, with some speculating the existence of a diamond-rich subsurface. But the possibilities do not end with diamond. Across the cosmos, the variation in elemental composition and environmental conditions gives rise to a staggering diversity of planetary chemistries. Some exoplanets may host cores rich in exotic metals, while others might be layered with rare silicates or high-temperature minerals unknown to Earth science. The unique chemical legacies of the star systems from which they form dictate the planetary end products. Thus, every new discovery of a rocky world orbiting a distant star invites fresh speculation about what unfamiliar materials might be hiding beneath its crust. Super-Earths add yet another dimension to the emerging portrait of planetary diversity. These planets, larger than Earth but smaller than Neptune, straddle the line between rocky and gaseous worlds. Unlike gas giants, which lack solid surfaces, many super-Earths are thought to have terrain, rocky plains, volcanic mountains, perhaps even oceans of molten lava or flowing water, depending on their distance from their stars. The intrigue surrounding super-Earths is largely due to their potential habitability. With masses several times that of Earth, they can maintain substantial atmospheres, which may provide both climate stability and shielding from cosmic radiation. More importantly, many of them orbit within the habitable zones of their stars, where conditions might permit the existence of liquid water. In the search for extraterrestrial life, these are prime candidates, worlds where biology could emerge and evolve under entirely different conditions from our own. Their prevalence in the galaxy is equally noteworthy. Observational data suggests that super-Earths may be among the most common types of planets in the Milky Way. This could be due to their ease of formation. When a star forms from a molecular cloud, it is typically surrounded by a dense protoplanetary disk. Within this disk, small planetary embryos form through the accretion of dust and ice. Under the right conditions, these embryos grow rapidly, attracting more material and becoming super-Earths before the disk disperses. Their intermediate size allows them to avoid the problems associated with forming massive gas giants, which require enormous amounts of gas within a narrow time window. Super-Earths, on the other hand, can form with relative ease from the rocky and icy building blocks abundant in the inner parts of protoplanetary disks. This may explain why they seem to appear so frequently in planetary surveys. In essence, each of these planetary phenomena, massive early galaxies, hot Jupiters, diamond-rich worlds, and super-Earths, represent threads in the vast and intricate tapestry of cosmic evolution. They speak of processes both ancient and ongoing, from the fiery birth of stars to the subtle gravitational nudges that reshape planetary orbits. They hint at materials and conditions never seen on Earth, and they continually challenge us to revise our models, to expand our theories, and to remain humble in the face of the unknown. The universe is not a static painting, frozen in a single moment of perfection. It is a living, evolving cosmos where every observation opens new corridors of inquiry, From galaxies forming too quickly to gas giants baking in the glow of their stars, from crystalline planets to rocky super-Earths teetering on the edge of habitability, we are only beginning to understand the complexity of the cosmos. Yet, perhaps the most profound realization of all is this: the more we learn, the more we discover how much we do not know. Each advancement in observation, each technological leap forward, each distant point of light resolved into something tangible, serves as a stark reminder that the universe is more intricate, more bizarre, and more beautiful than we could have ever imagined. And so the search continues. And yet the very methods by which we peer into the great unknown of the cosmos, transit and radial velocity techniques, are not impartial tools of science. They favor the dramatic, the noticeable, the worlds that assert their presence through their size and proximity. These methods are particularly proficient at detecting planets that are both large and close to their stars. In the case of super-Earths, planets that are more massive than Earth, but lighter than ice giants like Neptune, this observational bias becomes an advantage. Many of these planets orbit their stars at short distances, allowing them to transit frequently. Every time one of these planets passes in front of its star, it dims the starlight ever so slightly, and with each repeated transit, the signal grows more certain. This frequency of transit does more than help confirm the existence of such worlds. It grants astronomers a unique opportunity to probe their natures, to estimate their sizes, to speculate about their atmospheres, to question the chemistry and physics that govern them. The super-Earth classification contains a staggering range of planetary environments. Some may be rocky and temperate, with the potential for geological activity, plate tectonics, and perhaps even volcanic systems. Others may be cloaked in thick atmospheres of hydrogen and helium, or shrouded in layers of superheated steam or carbon dioxide. The incredible diversity within this category challenges our assumptions about what planets can be. Each new discovery nudges us closer to understanding the conditions that might allow life to arise, or that might render a planet sterile and silent forever. Super-Earths are not merely curious anomalies. They are testaments to the complexity of planetary formation and evolution. They occupy a unique position in our cosmic census, offering insight into the possible paths a planet might take once it coalesces from the dust of a newborn star. As our catalog of exoplanets continues to grow, super-Earths remain pivotal in unraveling the mysteries of planetary systems scattered across the universe. But when we turn our gaze toward more familiar sights, when we think of the planets that grace our own solar neighborhood, there is one image that looms larger than most: Saturn, encircled by its majestic rings. They stretch out from the planet's equator like the arms of a celestial dancer, glittering with ice and reflecting sunlight in golden arcs. These rings have captivated human imagination for centuries, and for good reason. They are the most extensive and visually spectacular ring system we have ever seen. Yet Saturn's rings, for all their beauty and grandeur, do not stand alone. The gas giants Jupiter, Uranus, and Neptune also wear rings, though theirs are subtler, fainter, often invisible to the naked eye or even telescopes without specialized instrumentation. Jupiter's ring system is thin and dusty, composed largely of microscopic particles, perhaps the remnants of shattered moons or pulverized asteroids. These grains move at astonishing speeds, encircling the massive planet in a ghostly halo. Uranus and Neptune, too, have rings, delicate dark bands that absorb more light than they reflect. Sparse and enigmatic, they whisper secrets that scientists have only just begun to decipher. And beyond the perimeter of our solar system, beyond the last light of the sun, astronomers are discovering that ring systems might not be confined to familiar territory. Evidence has emerged of exoplanets, worlds orbiting distant stars that may host rings so vast they make Saturn's look modest by comparison. Some candidates, like the proposed ringed world J1407b, could possess ring systems hundreds of times larger than Saturn's. These colossal structures might be composed of rock, ice, or dust, and they might have formed from moonlets pulled apart by gravity or debris left over from cataclysmic collisions. Detecting these rings is a daunting task. They do not transit stars in the same clean, obvious way that planets do. Their presence must be inferred through minute fluctuations in starlight, through subtle patterns in transit data that hint at something broader, something layered and complex. As instruments improve and our reach extends deeper into space, we may one day be able to image these rings directly, to map their structures and trace their histories. Such discoveries would not only transform our understanding of rings as planetary features, they would reshape our sense of scale of the architecture that planetary systems can assume. Saturn's rings may dominate our textbooks, but the cosmos offers richer, stranger tales still untold. While some of these worlds tease us with beauty and grace, others evoke awe through danger, through violence, through environments so alien that they appear to defy the laws of nature. Imagine a planet orbiting so close to its star that its surface temperature climbs to over 2,000 degrees Fahrenheit. At such extremes, metal becomes liquid. Iron flows like water. Oceans do exist, but they are not of hydrogen or methane or water. They are seas of molten iron or nickel, glowing with heat, shifting sluggishly under crushing gravity. Winds whip across these infernal surfaces at thousands of miles per hour, driving storms of vaporized rock and droplets of metal. Some planets have been theorized to possess surfaces covered in molten glass or silicate rain, where the skies are eternally twilight, the clouds are made of reflective minerals, and precipitation cuts like knives. Others may be blanketed by atmospheres so thick and so hot that no spacecraft could survive entry. These are not planets designed for life as we know it. They are crucibles of extreme physics, laboratories for understanding the outer limits of planetary composition. We once imagined planets as variations of Earth or Mars, rocky bodies with perhaps a touch of atmosphere and water. Now we know better. Planets come in forms that dwarf our terrestrial expectations. Each discovery that pushes the boundary of plausibility opens new fields of inquiry. What geological processes shape a world where the surface is always molten? Can magnetic fields form around such planets? Could they have once been habitable, only to be baked into sterility by their parent star? And then, from the fiery surfaces of exoplanets, our gaze shifts again, this time toward the dark hearts of galaxies, like to regions where gravity becomes an all-consuming force. The discovery of supermassive black holes has shaken our cosmological understanding. These entities sit at the centers of galaxies, including our own Milky Way, and possess masses that range from millions to billions of times that of our Sun. Their formation is not fully understood, but it is suspected to begin in the early epochs of the universe. After the Big Bang, dense regions of gas and dark matter coalesce to form the first stars and galaxies. In these primordial cauldrons, some of the earliest stars, enormous short-lived behemoths, collapsed into black holes after going supernova. These initial black holes, if situated in the right environments, could have grown quickly, feeding on the abundant gas and dust surrounding them, merging with other black holes, and evolving into the giants we see today. As they grew, their influence became immense. The gravitational pull of a supermassive black hole shapes the orbits of stars, dictates the motion of gas clouds, and may even regulate the birth of new stars. Some galaxies exhibit a relationship between the mass of their central black hole and the properties of the galaxy itself, suggesting that these enigmatic objects and their host galaxies co-evolved. Active galactic nuclei, powered by material spiraling into black holes, emit tremendous energy, sometimes outshining the entire galaxy around them. Yet, despite their power, black holes remain shrouded in mystery. We cannot see them directly, only the effects they have on nearby matter. Their event horizons, the points of no return, mark boundaries where known physics begins to break down. Time dilates, space curves, light itself cannot escape. What lies at the core of a supermassive black hole? Is it a singularity, an infinitesimally small point of infinite density? Or is there something beyond, a deeper understanding of gravity and quantum mechanics that eludes us? Some theorists suggest that inside black holes may lie doorways to other regions of space and time. Others contend that black holes are not as final as they seem, that information might escape in some form, carried away by subtle mechanisms we have yet to comprehend. As we continue to refine our telescopes, our simulations, and our theories, the pursuit of understanding these colossal objects continues. Supermassive black holes are not only keystones of galactic architecture, they are keys to fundamental truths about the nature of matter, energy, and space itself. In all of these cosmic stories, whether told by molten worlds, hidden rings, or gravitational titans, there is a common thread. Mystery begets curiosity, and curiosity drives discovery. The universe is vast beyond comprehension, yet piece by piece we are learning its language. With every new exoplanet cataloged, every ring detected, every black hole mapped, we expand the frontier of human understanding. What we uncover may not always fit into our existing frameworks, but that, perhaps, is the most thrilling part. The cosmos does not bend to our expectations. It invites us to stretch our minds to meet its reality. And yet, in the obscured hearts of the earliest galaxies, where matter congregated into unimaginable densities, gravitational interactions whispered the first notes of a cosmic symphony. It is within these dense galactic cores that the universe's most enigmatic titans, black holes, began to exert their influence. As galaxies approached each other, dancing in slow motion on astronomical timescales, their mutual gravities pulled them ever closer. When collisions became inevitable and galaxies merged in vast interstellar cataclysms, their central black holes, each a remnant of collapsed stellar mass or earlier mergers, would spiral inward, drawn by their mutual attraction in a slow, spiraling waltz dictated by the geometry of spacetime itself. These cosmic mergers were not silent. When two black holes collided, they released a staggering amount of energy, rippling the very fabric of spacetime with gravitational waves. The product of their union was a new, more massive black hole, a gravitational Goliath, absorbing both the mass and momentum of its predecessors. This process, repeated across cosmic epochs, allowed black holes to grow with astonishing efficiency. Each merger added to the black hole's mass. Each surrounding star or gas cloud that spiraled inward contributed to its density. This constant process of growth through accretion, where nearby material pulled by the immense gravity fell into the black hole's event horizon, enabled these singularities to achieve sizes rivaling entire stellar populations. But the story of black hole growth is not merely a tale of gravitational consumption. It is also a story of cosmic regulation, of balance and feedback within the galactic ecosystem. As supermassive black holes expand, they begin to influence the very galaxies that birthed them. From their centers, they emit powerful jets of radiation and high-energy particles, forming galactic-scale winds capable of halting star formation. These stellar winds and relativistic jets are not merely outflows of energy. They are sculptors, shaping the evolution of entire galaxies. By heating and dispersing the surrounding gas, black holes can effectively shut down the raw material needed for star formation, thereby dictating the future of their galactic hosts. This delicate dance between growth and inhibition reveals a profound interdependence between galaxies and their central black holes. They grow together. They evolve in tandem. A galaxy's structure, its rate of star formation, and its very ability to sustain new life in the form of stars are inextricably linked to the activity of its core. The gargantuan black holes found at the centers of galaxies today are not merely remnants of past violence. They are records of the dynamic, often chaotic history of cosmic formation. Factors that drive black hole growth are multifaceted. Rapid gas accretion, facilitated by gravitational instabilities, provides one pathway. Another comes through the relentless sequence of mergers, both with other black holes and with the galactic environments that channel matter inward. Within galactic clusters and other dense environments, gravitational interactions disrupt equilibrium, send gas towards central regions, and ultimately feed these dark giants. As a result, the presence of unusually massive black holes is not an anomaly. It is a signature of an active, tumultuous past, one in which gravity, gas, and time have conspired to craft engines of incomprehensible scale. Yet not all galaxies blaze with the fire of star birth. Some have fallen silent. These are the so-called zombie galaxies, celestial relics of a more vibrant past. At first glance, they appear similar to their more active kin. They retain their spiral arms, elliptical contours, and glowing centers. But inside, the machinery of creation has ground to a halt. Like cities abandoned by time, their streets, once filled with the youthful fire of star formation, now echo with the quiet light of ancient stars. No new stars are born here. The birthplaces of future suns lie barren. This haunting stillness is the result of a slow, inevitable process, the depletion of gas. Stars are born from gas clouds that collapse under their own gravity, A galaxy rich in gas is a galaxy teeming with life. But as these clouds are consumed and as the rate of new gas inflow diminishes, the galaxy's internal factory begins to shut down. Once the supply is exhausted or ejected, the birth rate of stars drops to near zero. The galaxy becomes quiescent. External factors can hasten this fate. Gravitational interactions with neighboring galaxies can strip gas away, hurling it into intergalactic space. Galaxy mergers, which can trigger brief but intense periods of star formation, often end in exhaustion, burning through gas supplies in spectacular yet unsustainable bursts. Moreover, when galaxies reside in dense clusters, they may be subject to powerful winds created by the movement of hot gas throughout the cluster. These winds can forcefully remove gas from a galaxy, leaving it devoid of the necessary ingredients for new stars. These zombie galaxies may still shine with the faint light of aging stars, but they are fundamentally dormant. The once thriving ecosystems within them have entered stasis. Studying these systems allows astronomers to trace the life cycles of galaxies from birth through vigorous star-forming youth, into middle-age productivity, and finally into the cold, still twilight of cosmic senescence. They are windows into a quieter universe, one that waits in silence. Still, at the very heart of our understanding of galaxies lies an invisible truth, one that cannot be seen but makes its presence known through its gravitational signature. Dark matter. To comprehend its role, imagine attempting to build a vast cathedral with invisible scaffolding. The walls may stand for a while, but without support, they would crumble. Dark matter is the scaffolding that holds the universe together. Though we cannot see it, though it emits no light and interacts only through gravity, it accounts for the vast majority of mass in the universe. When galaxies form, vast clouds of hydrogen gas collapse under gravity, condensing into stars and structures. But if gravity were provided only by the visible matter, stars, gas, dust, the galaxies would not hold together. Observations of rotating galaxies reveal a paradox. Stars near the edges move far faster than they should, based on the mass we can see. These rapid rotation speeds defy Newtonian expectations. Unless there is more mass than we can observe, galaxies should fly apart. The answer, astronomers believe, is dark matter. It does not clump like normal matter, does not form stars, and remains invisible to electromagnetic detection. But its gravitational pull is undeniable. It forms vast halos around galaxies, binding them together in stable configurations. Without it, galactic evolution as we know it would be impossible. There would be fewer galaxies, and those that did exist would be smaller, less structured, and prone to disintegration. The presence of dark matter ensures that galaxies persist for billions of years, that clusters can form, and that the cosmic web, a vast network of galaxies and voids, can be maintained across cosmic scales. Even the largest galactic structures, such as the Laniakea supercluster, owe their existence to dark matter's invisible hand. It draws matter into vast filaments and nodal intersections, guiding the architecture of the universe. Galaxies are not merely floating islands of stars. They are embedded in the gravitational framework provided by this mysterious substance. Dark matter may yet prove to be the key to understanding the deepest structure of the cosmos, influencing everything from galactic rotation to the distribution of galaxies across the universe. And then there are the starburst galaxies, cosmic fireworks displays where star formation happens at a staggering pace. If typical galaxies are steady, candlelit chambers of creation, starburst galaxies are burning furnaces, forging stars at rates tens or even hundreds of times faster than normal. These are not quiet, orderly systems. They are chaotic and luminous, bright with the energy of countless young stars bursting into life. Often triggered by galactic interactions, two galaxies brushing past each other or slamming together, these events drive gas into central regions. The compression of gas in such interactions provides the perfect conditions for gravitational collapse. Massive clouds condense rapidly, leading to the simultaneous birth of thousands of stars. The results are spectacular. Entire clusters ignite almost in unison. Massive stars, short-lived and brilliant, pour radiation into their surroundings, creating hot, glowing regions that ripple across the galaxy like shockwaves. These events do not last long in cosmic terms. The starburst phase is transient, a few million to a few 100 million years, a blink of an eye on galactic timescales. But during that brief flare of activity, the galaxy can build a significant portion of its stellar mass. And like many intense processes, it carries consequences. The energy released by these new stars, particularly those that go supernova, can drive galactic winds that expel gas. Ironically, the same starburst activity that fuels creation also sows the seeds of future dormancy. Once the gas is gone, the galaxy may settle into a quieter phase, or even transition into a zombie state. Through these many pathways, from mergers of black holes and accretion of matter to starbursts, dormancy, and the silent strength of dark matter, galaxies are not static monuments. They are dynamic, evolving entities shaped by gravity, time, and invisible forces. The universe itself is a living archive of these stories, each galaxy a page in the chronicle of cosmic history. To read them is to glimpse the mechanics of the cosmos, to understand not only where we are, but how we came to be. And yet, amid the cold expanse of intergalactic space, a wild dance of creation and destruction continues with breathtaking fury. Starburst galaxies, named for their spectacular rates of star formation, do not just flicker into activity, they erupt. Driven by a convergence of environmental dynamics and internal upheaval, these galaxies are cosmic furnaces, churning out new stars at rates that far outpace their quieter, more sedate cousins. One of the most potent fuels for this galactic firestorm is primordial gas, ancient, unprocessed hydrogen and helium that has drifted for eons in the cosmic void. When this raw material is pulled into the gravitational well of a galaxy, it plunges into its heart like oxygen into a bonfire, igniting furious waves of stellar genesis. These inflows are more than mere infusions of star-making material. They are reminders of the deep interconnectivity of the universe. Gas clouds that form just after the Big Bang, untouched and pristine, still wander the great darkness. Occasionally, they are caught by a passing gravitational arm or a halo of dark matter, tumbling into the waiting cradle of a galaxy like fuel into a furnace. As these massive clouds collide and compress, gravity triggers the formation of star after star, each one a nuclear beacon blazing against the backdrop of interstellar space. But birth, in the cosmos as in life, is rarely quiet. As these newborn stars begin their luminous lives, they immediately begin to alter the environment that created them. Immense radiation pours outward in all directions. Stellar winds, high-velocity flows of charged particles rip through nearby space. These forces create turbulence, heating and dispersing the very clouds that gave rise to them. In some regions, this energy acts like a sculptor, carving out pockets where more stars can form. In others, it acts like a destroyer, shredding the clouds and halting further birth. This feedback cycle creates a galactic tempo that shifts between chaos and harmony, growth and suppression, over and over again. Starburst galaxies are not just interesting phenomena. They are explosive, kaleidoscopic chapters in the broader narrative of cosmic evolution. In these brilliant episodes of star formation, we witness the interplay between ancient gas, the relentless tug of gravity, and the unpredictable influence of nascent stars. They show us how even the oldest, quietest corners of space can spring into dramatic life, driven by forces we are only beginning to understand. Meanwhile, elsewhere in the universe, far from these vibrant nurseries of starbirth, lie the majestic titans of galactic architecture, the giant elliptical galaxies. These massive, smooth, spheroid giants loom in the cosmic tapestry like ancient fortresses, serene and unchanging in appearance, but forged through tumultuous histories. They are not sculpted overnight. Their massive forms are the end result of billions of years of cosmic accumulation and evolution. Where spiral galaxies charm with their twirling arms and delicate lanes of dust, elliptical galaxies are enigmas of mass and motion. Their light is softer, more diffuse, lacking the dramatic contrasts of spirals. There are no spiraling lanes of star formation here, no bright nurseries tucked within filaments of gas. And instead, these galaxies are dominated by old red stars, the elderly population of the cosmos. And yet beneath this quiet facade lies a story of immense violence, of relentless gravitational mergers and cosmic cannibalism. The formation of a giant elliptical galaxy begins in the distant past. Stars, dark matter, and gas are drawn together through the inexorable pull of gravity. Over time, smaller galaxies are absorbed, their individual identities erased, their stars and structures assimilated into the growing mass. With each merger, energy and mass are redistributed, spreading out instabilities and preserving a relatively smooth distribution of material. This process helps prevent the chaos that might otherwise tear the galaxy apart. What holds it all together? The answer is gravity. Monumental, unrelenting gravity. The combined mass of billions of stars, coupled with vast halos of invisible dark matter, creates a gravitational anchor so immense that it binds the galaxy in place, resisting dispersion or collapse. Every star, every fragment of matter within the galaxy's bounds is subject to this immense central pull. But the stability of elliptical galaxies is also reinforced by the nature of their stellar motions. Unlike spiral galaxies, where stars follow orderly, circular orbits, the stars in ellipticals follow more random paths. These orbits are not confined to a flat disk. Instead, they span all directions, creating a more even distribution of momentum and mass. The result is a dynamic equilibrium, less prone to rotation-based instabilities and more resistant to disruption. Without the centrifugal forces that shape spiral arms, elliptical galaxies become stable, spherical collectives of ancient starlight. Time in these galaxies feels almost frozen. There is little fresh star formation. The raw ingredients for new stars, cool gas and dust, are mostly absent. The galaxy instead glows with the accumulated light of ancient stars, slowly aging, quietly radiating the echoes of a more chaotic youth. Yet their endurance is unmatched. These galactic elders have survived the most violent epochs of the universe and stand as monolithic relics of cosmic time, silent witnesses to the unfolding story of everything. In sharp contrast to this grandeur and serenity, we turn now to one of the most perplexing and momentary phenomena in modern astrophysics: fast radio bursts. First detected in 2007, these ephemeral flashes of radio energy erupt across the cosmos like whispers from another dimension. They are short, lasting mere milliseconds, but in that flicker of time, each burst unleashes as much energy as the sun does over several days. They are cosmological firecrackers, bursting into our instruments seemingly without pattern, without warning, and without precedent. Fast radio bursts have become one of the most intriguing puzzles in astronomy. Scientists have cataloged dozens of them since their initial discovery, but each one brings more questions than answers. Where do they come from? What causes them? Why are some of them repeated while others appear only once, never to be heard from again? Various theories have been proposed. Some suggest they originate from the catastrophic collapse of neutron stars, those ultra-dense remnants of supernovae. Others point to the merging of black holes or magnetars, neutron stars with extremely powerful magnetic fields, as potential sources. Yet, despite sophisticated instrumentation and relentless observation, none of these theories has been conclusively confirmed. One of the greatest challenges in understanding fast radio bursts is their very nature. Their transience makes them difficult to observe. By the time a telescope has been pointed in the direction of a suspected FRB, the signal has already vanished. The immense distances they travel complicate things further. As these radio waves cross the cosmos, they are stretched, scattered, and distorted by the intergalactic medium. What reaches us is a ghostly echo, a puzzle missing half its pieces. Despite these hurdles, advances in telescope technology have begun to bear fruit. Some observatories have successfully pinpointed the locations of a few FRBs, tying them to specific galaxies, even identifying repeating sources. But each discovery seems to expand the mystery rather than solve it. The diversity among FRBs, their varying durations, intensities, and patterns, suggests that there may not be a single explanation. Instead, we might be looking at a new class of astronomical phenomena, or even several overlapping ones. Like messages scrawled in lightning across the night sky, fast radio bursts beckon us toward the edges of our understanding, inviting speculation and demanding patience. They remind us how much we have yet to learn about the cosmos. And then, in the climactic endgame of stellar evolution, we find the titans of destruction, supernovae. These are not quiet deaths, they are cataclysmic finales, cosmic detonations that rival the brightness of entire galaxies for brief moments in time. When a massive star reaches the end of its life, it no longer has the nuclear fuel needed to counterbalance the crushing force of gravity. Its core collapses inward in an instant, triggering an outward explosion of unimaginable power. Supernovae can form in several different ways. Some are the result of core collapse in massive stars. Others stem from white dwarfs that accumulate material from a companion star exceeding a critical mass until they explode. The classifications we use, type 1a, type 2, and so on, reflect the pathways we understand. But these classifications are only as comprehensive as our observations allow. The universe, however, is not obliged to fit neatly within our categories. Given the staggering diversity of stellar types and compositions, it is entirely plausible that stars exist whose final moments do not match any known pattern. These unknown supernovae, hypothetical as they may be, are not merely speculative fiction. They are a statistical probability. Somewhere in the vast, dark ocean of the cosmos, there are stars whose deaths will rewrite our textbooks, whose explosions will defy expectation, whose light will show us something we never thought to look for. As our instruments improve and our reach expands, we may one day witness these anomalies. And when we do, they will remind us of a fundamental truth. Our universe is not a closed system. It is a living, evolving entity filled with mysteries that deepen the more we learn. And every fast radio burst, every dying star, every flicker of light in the void is part of this ongoing narrative, a story of chaos and order, of endings that birth beginnings, of a cosmos ever in motion. And yet, the stages of a star's life do not unfold in a uniform or predictable way. The environments in which these massive furnaces are born, live, and eventually die can vary so dramatically that their final moments, their spectacular deaths, often defy our existing models and challenge the boundaries of classification. Stars are not solitary actors. They are shaped by the chaos and conditions around them. This chaotic influence can manifest in dramatic, unforeseen ways when they reach the end of their lifespans. As the final act begins, new and unanticipated variables, ranging from local gravitational fields to nearby companions or even previously unrecognized types of stellar interaction, can shape the resulting explosion into something astronomers have never seen before. These cataclysmic departures, often called supernova, are typically grouped into distinct categories, but reality does not always obey categorization. Moreover, as observational technologies race ahead with cutting-edge advancements in both ground-based telescopes and space observatories, we stand on the cusp of discovering events that have previously gone unnoticed, unrecorded, or misunderstood. These tools have opened up entire swaths of the electromagnetic spectrum to human inquiry, from gamma rays to radio waves. As these instruments peer deeper and more precisely into the cosmos, they bring forth revelations once thought impossible. A single newly observed stellar explosion may display characteristics so strange, so divergent from known templates, that astronomers are compelled to question whether it belongs to a type we have yet to define. It may very well represent a new class altogether, forcing an expansion or even a rewriting of astrophysical theory. Theoretical astrophysicists operating far beyond the reach of direct observation continue to expand the catalog of what might be possible. They propose exotic mechanisms for stellar death, speculating about supernovae driven by interactions in triple star systems, or those occurring in stars with highly unusual chemical compositions. Some theories suggest that under specific, extreme circumstances, the core of a massive star might collapse in a way fundamentally different from the well-understood models. These hypothetical explosions could produce observational signatures unlike anything recorded so far, signaling the birth of a new family of cosmic phenomena. The allure of such discovery is profound. An unknown supernova type could reveal missing pieces of the stellar life cycle and offer insight into the fabric of the universe itself. The search continues, driven by the idea that the cosmos is far more complicated and dynamic than our present knowledge suggests. As astrophysicists refine their models and observers cast their gaze ever farther into the night, the possibility of discovering unknown stellar cataclysms remains not only plausible, but likely. In this pursuit, we are not merely learning about the death of stars, we are mapping the forces that shape the galaxy and the larger cosmos. Each new insight is another step toward understanding a universe that is, by its very nature, a vast and continually unfolding mystery. Hidden deep within the crowded skies of the Centaurus constellation lies one of the most enigmatic gravitational forces ever discovered, the Great Attractor. This massive anomaly exerts a pull so powerful that entire clusters of galaxies, including our own Milky Way, are being slowly and inexorably drawn toward it. To comprehend this phenomenon, one must understand the scale of the gravitational influence involved. The Great Attractor is not a solitary entity. Rather, it is believed to be a dense, sprawling region made up of galaxies, intergalactic gas, and perhaps most significantly, an enormous concentration of dark matter, the elusive substance that comprises a substantial portion of the universe's mass, but remains invisible to direct detection. Imagine a vast stretch of cosmic fabric, space-time itself, distorted by the weight of something massive. The Great Attractor behaves like an immense object dropped into that fabric, creating a deep well that causes anything nearby to roll toward it. Galaxies, including our own, follow these warps and curves in space-time, drawn in by the gravitational dip created by this enormous cluster. But unlike a visible magnet, the Great Attractor remains partly obscured, not just by its own complexity, but by our position within the Milky Way. We are embedded in a galaxy veiled in interstellar dust and gas, making direct optical observation extremely difficult. Nevertheless, astronomers have developed indirect methods, such as measuring peculiar velocities of galaxies and mapping X-ray emissions from galactic clusters, that allow them to infer its gravitational footprint. Through these techniques, the presence of this vast attractor becomes evident. We observe galaxies moving not in random patterns, but along discernible paths that converge toward a central gravitational source. This behavior is not governed by local dynamics, but by a force acting over hundreds of millions of light years. It's a reminder that the structure of the universe is deeply interconnected, and that galaxies do not drift aimlessly through space, but instead are choreographed by massive gravitational influences. The Great Attractor compels us to rethink our place in the cosmic web, to consider that the path of our galaxy, and perhaps the future of many others, is influenced by forces we are only beginning to understand. Even more mysterious is what lies beyond it. Some cosmologists suggest that the Great Attractor may itself be a gateway, or merely one visible manifestation, of an even larger structure, the Shapley supercluster. If so, the gravitational narrative becomes even more intricate, suggesting a layered hierarchy of cosmic motion influenced by successive gravitational attractors, all embedded within the tapestry of dark energy and dark matter that constitutes the large-scale architecture of the universe. As we look deeper into the workings of stellar remnants, pulsars emerge as some of the most fascinating and extreme objects the universe has to offer. These are not ordinary stars, but the compressed cores of once massive suns left behind after a dramatic supernova explosion. What remains is a neutron star, a sphere no wider than a city, yet more massive than our sun, so dense that a single teaspoon of its matter would weigh billions of tons. And within that impossibly small volume lies a spinning dynamo, rotating sometimes hundreds of times per second. This rapid rotation, paired with a powerful magnetic field, gives rise to the phenomenon known as the pulsar. The magnetic field of a pulsar is misaligned with its spin axis. This misalignment is key to the pulsar's defining characteristic, the emission of concentrated beams of electromagnetic radiation from its magnetic poles. As the star spins, these beams sweep across space, and if the Earth happens to lie within their path, we detect the radiation as a regular pulse, hence the name. The precision of these pulses is almost eerie in its regularity. Some pulsars are so stable that they rival atomic clocks in their consistency. This makes them invaluable tools for astronomers who use them to measure time, study gravitational waves, and even test the limits of Einstein's general relativity. These beams of radiation are not simply passive emissions. They are forged in the crucible of extreme physics. Charged particles, accelerated along the magnetic field lines of the neutron star, reach energies that cause them to emit radiation across a wide spectrum, from low-frequency radio waves to intense X-rays and even gamma rays. Each pulse is a message from a collapsed star, a cosmic metronome beating out time with millisecond precision. The behavior of pulsars is not monolithic. Some are solitary. Others reside in binary systems where their interactions with companion stars can lead to accretion events, changes in spin rate, and phenomena like X-ray bursts. There are even pulsars that have been respun to higher frequencies through such interactions, known as millisecond pulsars. These are among the fastest spinning objects in the universe and are studied not only for their exotic nature, but also for their potential to reveal deeper truths about the state of matter under extreme pressure. Cosmic rays, too, bring their own kind of mystery and wonder. These are not rays in the traditional sense, but high-energy particles that continuously bombard our planet from all directions in space. They are primarily made of protons, but they also include electrons, photons, and the nuclei of heavier elements. Their origin is diverse and layered. Some come from our own sun, accelerated by solar flares. Others are ejected from the tumultuous aftermath of supernova explosions, while the most energetic of them are believed to originate from the distant hearts of active galactic nuclei, or quasars. We detect these particles using a range of ground-based and satellite-borne instruments, capturing the secondary showers they create when they strike Earth's atmosphere. Through decades of observation, we have come to understand a great deal about the energy spectra and probable origins of known cosmic rays. Yet the story is far from complete. The universe is vast and its mechanisms infinitely complex. It is not unreasonable to suspect that there are forms of cosmic rays we have yet to identify. Particles that defy our existing classifications, that evade our instruments, or that are produced by physics that lies outside the standard model. Some theorists propose that dark matter, which we know must exist yet have never directly detected, could interact with regular matter in a way that generates new, previously unknown forms of cosmic radiation. These hypothetical particles might be so rare or so weakly interacting that they pass through current detectors unnoticed. Others envision particles that arise from topological defects in space-time itself, or from decays of supermassive relic particles left over from the Big Bang. If such particles exist, they could represent a fundamentally new chapter in high-energy astrophysics and particle physics alike. They could challenge the boundary between cosmology and quantum mechanics and force a re-examination of how the fundamental forces of nature interplay across the scales of the universe. Until then, the search continues, driven by curiosity, technology, and the unrelenting desire to understand the unseen energies that travel through our world, bearing silent witness to the violent and beautiful processes unfolding in the farthest reaches of the cosmos. And yet, beyond the vast and well-documented barrage of heavy ions that rain upon our planet from the deepest corners of space, there exists the possibility, however faint, of far stranger travelers. These are not simply particles known to physics textbooks or familiar to particle accelerators. They might be ancient remnants from epochs closer to the birth of time itself, primordial black hole fragments, whispering relics of the Big Bang. Or perhaps, under circumstances we are just beginning to conceptualize, actual miniature black holes, microscopic yet furious with energy, darting invisibly across the cosmos and quietly radiating in ways we have only started to theorize. If such objects exist, they would be both cosmic fossils and energy fountains, offering insights not just into what the universe is, but what it has always been capable of becoming. The energy spectrum of cosmic rays has long fascinated scientists. What is known is dwarfed by what remains hidden. Among the most puzzling features is the unexpected and stubborn presence of ultra-high energy particles, cosmic rays that strike our planet with energies exceeding those produced by our most powerful particle accelerators. These particles do not simply originate from known events like supernovae or quasars. Their energies suggest birthplaces in regions of unimaginable force, perhaps near active galactic nuclei, colliding neutron stars, or exotic phenomena beyond our current observational reach. Their arrival at Earth is like receiving a cryptic postcard from an uncharted realm of the universe, each impact a message we are still trying to decode. As detection technology improves, the field is on the cusp of transformation. Space-based observatories with wide-field capabilities and advanced instrumentation are expanding our perceptual limits. Ground-based observatories, buried deep beneath Antarctic ice or hidden in high-altitude deserts, wait like silent sentinels for the brief signals of these elusive visitors. Together, these tools form an unprecedented network that allows for the capture, analysis, and perhaps even identification of exotic cosmic particles. Every detection might yield data that overturns long-standing assumptions. Each confirmed anomaly becomes a chapter in a new, unfolding story of the cosmos. The stakes are not small. If just one of these unusual high-energy intruders originates from an exotic event, a miniature black hole evaporating in our atmosphere, or a trace of matter from a parallel realm, it could force a complete rewrite of cosmic physics. With each new insight, the barrier between the known universe and the unknown frontier is peeled back, revealing a deeper complexity and a stranger beauty. And somewhere in that hidden structure, we may find truths that fundamentally alter our perception of the universe and our place within it. The pursuit of these particles, most invisible, many indifferent to electromagnetic radiation, and some perhaps immune to all interactions but gravity, is a quest into the fabric of reality itself. We search not just to observe them, but to understand the stories they carry from far-off cataclysms, from epochs before Earth had formed, or from domains of physics where our rules no longer apply. And then there is time. Not the ticking of clocks or the slow cycle of seasons, but time itself, the fundamental mysterious dimension through which all things move. In our everyday experience, time flows in one direction, from what was to what is to what might be. We remember the past, we imagine the future, but what if that flow is not universal? What if it is a local phenomenon, a mere accident of entropy, the cosmic tendency of systems to drift toward disorder? In theoretical physics, time is often treated not as a river, but as a landscape. It has direction, but only because of how the universe evolved. Some cosmological models, grounded in interpretations of quantum gravity and certain solutions to the equations of general relativity, suggest the possibility of universes where time flows in the opposite direction. In these mirror universes, what we call the future might be their past, and what we consider cause could be their effect. Imagine it, a world where time's arrow points backward, where entropy decreases rather than increases, and where every action is followed not by a result, but by a cause. In such a place, the shattering of a glass might be the beginning of its restoration, each splintered fragment leaping upward, finding its mates, sealing the cracks, and coming together in a reverse choreography of destruction undone. Life itself might move in a reverse chronology, with death the beginning and birth the end. Every breath inhaled would unmix the air. Every thought would echo from the future. But such a universe would not simply be our world played in reverse. It would follow its own laws of physics, shaped by different boundary conditions, and perhaps constructed from an entirely different foundation of interactions. Memory, consciousness, identity, all would be redefined. Would minds in such a universe remember what to us is yet to come? Would experience itself be inverted, with beings learning backwards, forgetting toward their beginning? These speculations, though abstract, are not idle fantasy. They emerge from real puzzles in cosmology, including the asymmetry of time, the mysteries of entropy, and the search for a unified theory that combines quantum mechanics with general relativity. In trying to understand why our universe has a direction to time at all, we inevitably confront the question of whether that direction is necessary or merely contingent, a byproduct of conditions at the Big Bang. Even more intriguing is the idea that such reverse time domains might coexist with ours. Perhaps beyond the observable boundary of our universe, a twin cosmos unfolds in temporal reverse, bound to ours in a way we cannot yet detect. Perhaps time itself, like space, curves and twists, intersecting itself in dimensions we have yet to perceive. These reflections challenge the very ground of ontology. What does it mean to exist, to act, to experience in a universe where the arrow of time may not be fixed? From these temporal mysteries, we transition into the equally compelling world of mirror matter. Imagine a reflection not in light but in substance, a form of matter that is identical to our own, yet does not interact with it in familiar ways. According to the theory of mirror matter, for every particle in our universe, there may be a counterpart existing in a parallel but separate sector. These mirror particles would have the same mass as their standard counterparts, mirror protons, mirror electrons, mirror neutrons, but would not participate in electromagnetic strong or weak interactions in the ways we observe. Their presence would be betrayed only by gravity, and perhaps by extremely faint interactions not yet clearly measured. Why would such matter exist? The idea emerges from attempts to explain symmetry in physics. While the laws of physics generally appear symmetrical, certain interactions, especially involving the weak nuclear force, show asymmetries. Mirror matter restores that balance by positing an unseen counterpart to every observed asymmetry. In a universe where parity symmetry is truly preserved, the mirror sector is not optional. It is necessary. The implications are immense. One of the great mysteries of modern astrophysics is dark matter, an invisible substance that exerts gravitational pull but does not emit or absorb light. It surrounds galaxies, dictates the formation of large-scale cosmic structures, and outweighs visible matter by a factor of 5 to 1. Mirror matter could be a candidate for this elusive substance. It would have mass, it would clump under gravity, it could form mirror galaxies, mirror stars, even mirror planets. But it would remain hidden because it would not interact with light in the ways we can detect. There are also subtler clues. In high-energy particle experiments, physicists sometimes detect missing energy. That is, particles vanish in ways that violate conservation laws unless something undetected carries away that energy. If particles occasionally oscillate into their mirror counterparts, flipping from ordinary to mirror matter, they would disappear from our detectors but continue to exist elsewhere. These transitions could explain why some experimental results deviate from expectations. Moreover, mirror matter might not be entirely disconnected from our own. If there are feeble interaction channels through kinetic mixing of photons or through exotic Higgs interactions, then under the right conditions, mirror particles might reveal themselves. These manifestations would be rare and difficult to distinguish, but not impossible. And if observed, they would mark the first contact with an invisible side of the cosmos. All of this leads us to consider the universe not as a singular entity, but as a layered, complex structure in which multiple realities overlap. The visible world, made of stars and galaxies, might be just one face of a deeper, more intricate creation. Mirror matter, flowing backward in time, carrying exotic energies, tied together by the faint strands of gravity and quantum fields. This is the frontier. Not a boundary to end exploration, but a threshold to something richer, stranger, more revealing. And through all of it, our tools evolve. Our questions sharpen. Our vision deepens. The pursuit of the invisible, the unheard, the seemingly impossible continues. And every discovery, however small, is a lens turned outward and inward, bringing us closer not only to the universe as it is, but to the profound mystery of our place within it. Furthermore, the concept of mirror matter introduces a fascinating realm of possibilities when considering the grand cosmic events that shape our universe. If mirror matter interacts with the ordinary matter we are familiar with during cosmic collisions or other astrophysical phenomena, it could result in highly unusual distributions of energy, patterns that defy the conventional frameworks of particle physics that have guided scientists for decades. This possibility invites us to consider that the cosmos might be operating under more complex rules than we currently understand. The potential interactions between mirror matter and regular matter might unlock new paths of inquiry, pushing the boundaries of physics into territories that were once thought impossible to explore. By delving deeper into this theory, researchers aim to illuminate some of the universe's most enigmatic puzzles, possibly transforming our fundamental understanding of how the cosmos operates. Mirror matter compels us to imagine a universe far richer and more intricate than our senses and instruments presently reveal. It encourages a reconsideration of the assumptions underlying modern physics and cosmology, opening the door to hidden dimensions or particles that might have remained invisible until now. Scientists investigating mirror matter hope that such efforts will shed light on the universe's darkest mysteries, those questions surrounding dark matter and dark energy, phenomena that have eluded clear explanation despite decades of rigorous study. These enigmatic substances form a substantial yet invisible portion of the cosmos, influencing everything from galaxy formation to the large-scale expansion of space. Dark matter, for example, is believed to be a form of matter that neither emits nor absorbs light or other electromagnetic radiation, rendering it effectively invisible to conventional telescopes and detectors. Its existence is inferred primarily through its gravitational influence on visible celestial objects. Observations show that stars within galaxies and galaxies themselves move as if there were far more mass present than the luminous matter we can detect. This unseen mass plays a critical role in holding galaxies together, preventing them from flying apart due to their own rotational velocities. Moreover, dark matter contributes fundamentally to the large-scale structure of the universe, guiding the formation and clustering of galaxies across billions of light years. Conversely, dark energy appears to be an entirely different kind of cosmic entity, an enigmatic force responsible for the accelerated expansion of the universe. While dark matter exerts a gravitational pull, drawing matter together, dark energy pushes space itself apart, counteracting gravity on the grandest scales. Current observations suggest that dark energy constitutes a majority of the total energy density of the universe, dominating the cosmic landscape and influencing the ultimate fate of all cosmic structures. The discovery of this accelerated expansion, confirmed through observations of distant supernovae and the cosmic microwave background radiation, has revolutionized cosmology and introduced profound questions about the nature of space, time, and energy. The tantalizing hypothesis that dark matter and dark energy might be two facets of a single underlying phenomenon remains a subject of intense theoretical investigation. Some physicists speculate that these seemingly distinct entities could emerge from a unified framework, potentially rooted in complex quantum mechanical processes or hidden symmetries governing the fundamental forces. If this were true, it could lead to a profound reshaping of our understanding of gravity and the structure of space-time itself. However, despite the conceptual elegance of this unified approach, direct experimental or observational evidence confirming such a connection remains elusive. Distinguishing the individual properties and effects of dark matter and dark energy continues to challenge scientists, driving the development of new instruments and observational campaigns to probe the cosmos with ever-increasing precision. In the meantime, dark matter and dark energy persist as two separate mysteries, each essential to the cosmic narrative, yet still veiled in uncertainty. Their continued study pushes the frontier of modern physics, inspiring new generations of researchers to seek answers beyond the visible universe and to venture into the unknown realms that govern reality on the largest scales. The idea that the fabric of space itself might be interwoven with unseen structures influencing its shape and behavior is a profound and captivating concept deeply rooted in both theoretical physics and cosmology. To grasp this notion, consider how the universe functions on an immense scale. Space is not an empty void, but a dynamic arena filled with various forms of matter and energy that continuously shape its characteristics and evolution. The force of gravity, for instance, arises from massive objects like stars, galaxies, and galaxy clusters, which create gravitational fields that curve the space around them. This curvature dictates the motion of celestial bodies and even the path of light, shaping the cosmic landscape in fundamental ways. Expanding this understanding leads to the recognition that the universe might harbor more subtle and mysterious structures. Dark matter, invisible yet influential, accounts for a large portion of the universe's mass, guiding the formation and motion of galaxies through its gravitational pull. Dark energy, on the other hand, drives the accelerated expansion of space itself, stretching the cosmos in ways that challenge classical physics. Beyond these, theoretical models propose even more exotic possibilities, such as cosmic strings, hypothetical one-dimensional defects in the fabric of spacetime. These cosmic strings, if they exist, could stretch across immense distances and affect the curvature of space, potentially influencing the motion of galaxies and the distribution of matter on cosmic scales. Though these structures remain beyond the reach of direct observation, they may be fundamentally woven into the universe's architecture, shaping its expansion, formation, and destiny in ways subtle enough to evade easy detection. As observational technology and theoretical models advance, the prospect of uncovering these hidden elements grows, promising deeper insights into the true nature of space itself and the forces that govern its evolution. The notion that black holes might serve as gateways or conduits, known as wormholes, is an idea that has captivated both scientific minds and the imaginations of science fiction enthusiasts for decades. To understand this concept, it is necessary to explore the nature of these two extraordinary phenomena. A black hole forms when a massive star exhausts its nuclear fuel and collapses under the relentless pull of its own gravity. This collapse leads to the creation of a singularity, a point of infinite density, where the known laws of physics break down, surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape the black hole's grasp. Wormholes, on the other hand, are purely theoretical constructs, tunnels or shortcuts through space-time that could, in principle, connect two distant points in the universe. Imagine space-time as a two-dimensional surface that can be bent and folded. A wormhole would be akin to folding this surface so that two far-apart points touch, allowing travel between them without traversing the intervening distance in the usual way. This concept offers a thrilling possibility of instantaneous travel across vast cosmic distances. The intriguing hypothesis suggests that black holes could act as entrances to such wormholes, with corresponding exits somewhere else in the cosmos. If true, this would revolutionize our understanding of space travel, causality, and the structure of the universe. However, this idea faces formidable challenges. The extreme gravitational forces near a black hole would almost certainly destroy any matter attempting to pass through, making traversal perilous, if not impossible, with our current understanding of physics. Moreover, the stability of such wormholes is questionable, as the theoretical constructs often require exotic matter or negative energy to keep them open, substances not yet observed in nature. Despite these challenges, the concept of black holes as wormholes remains a fertile ground for theoretical exploration, inspiring research at the intersection of quantum mechanics, general relativity, and cosmology. As our understanding deepens and technology progresses, future discoveries may reveal whether these cosmic shortcuts exist beyond the realm of imagination, offering unprecedented insights into the nature of the universe and the possibilities of interstellar travel. Furthermore, even if a stable wormhole were to exist in the fabric of space-time, keeping it open would require a form of matter unlike anything we have discovered so far, an exotic substance that defies our current understanding of physics. This exotic matter, theorized to have negative energy density, is essential to prevent a wormhole from collapsing under the immense gravitational forces that naturally try to close it. Without such matter, these hypothetical tunnels connecting distant points in the universe would pinch shut almost instantly. Thus, while the concept of black holes serving as natural wormholes unlocks a captivating door to possibilities within astrophysics, it remains firmly rooted in the realm of theoretical speculation. Our contemporary grasp of physics, bounded by general relativity and quantum mechanics, presents formidable challenges to confirming whether such phenomena exist in reality. For now, black holes maintain their enigmatic status, characterized by an almost unfathomable gravitational pull that warps space-time around them so profoundly that nothing, not even light, can escape once past the event horizon. This mysterious nature leaves the question of whether black holes could function as wormholes suspended in the air, caught between curiosity and skepticism. Black holes, with their dense cores known as singularities, invite endless speculation about what might lie within or beyond, yet solid proof remains elusive. In the year 2024, remarkable advances in radio astronomy opened a new chapter in our exploration of the cosmos. Scientists detected a series of fast radio bursts, brief, intense flashes of radio waves originating from galaxies millions or even billions of light years away. These fast radio bursts, or FRBs, appeared sporadically and their origins were shrouded in mystery. However, this latest wave of observations showed something novel. These signals exhibited complex patterns and consistent repetition that hinted at the possibility of artificial origins or at least unknown cosmic phenomena that defied previous explanations. One particularly captivating anomaly was a signal emanating from a nearby star system, a discovery that intrigued researchers due to its unusual frequency and modulation characteristics. Unlike the typical natural radio emissions produced by stars, planets, or nebulae, this signal showed patterns reminiscent of engineered waves. patterns that raise tantalizing speculation about extraterrestrial technology. Although these observations sparked cautious excitement, scientists remained prudent, emphasizing that more data and corroboration are necessary before drawing definitive conclusions. Adding another layer to the enigma, some radio telescopes detected bursts exhibiting unusual polarization patterns that did not align with any known astrophysical sources. Polarization refers to the orientation of the oscillations of electromagnetic waves, and unexpected patterns suggested unknown physical mechanisms at play. This revelation pushed researchers to revisit their models of magnetic fields and radiation processes occurring throughout space, questioning long-held assumptions and expanding the frontiers of astrophysical knowledge. Each of these detections fueled heated debates among scientists and ignited the imagination of the public alike. Radio waves traveling across vast cosmic distances carry with them secrets waiting to be deciphered. The fascination surrounding these signals lies not only in their scientific importance, but also in the profound questions they raise about humanity's place in the universe. Every new discovery brings us incrementally closer to unveiling the mysteries that lie beyond our planet, urging us to consider what other cosmic messages might be silently waiting for discovery. Among the many wonders of the cosmos, pulsars stand out as mesmerizing celestial objects often described as cosmic lighthouses. These highly magnetized, rapidly rotating neutron stars emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across the cosmos in regular intervals, creating a pulsing effect much like a lighthouse beam rotating over dark waters. The intervals between these pulses can range from a few seconds to mere milliseconds, and their astonishing regularity has led many to wonder if pulsars might somehow be conveying messages. The notion of pulsars sending intentional signals requires a careful, nuanced approach. Current scientific consensus holds that the pulses we detect from these stars are natural phenomena, the result of complex astrophysical processes governed by the laws of physics. The extraordinary stability and regularity of their pulses have been precisely measured and documented, showcasing their intrinsic nature rather than deliberate communication. Still, the regular patterns and remarkable precision have not stopped some researchers from entertaining the possibility that hidden within the vast datasets of pulsar emissions, there might be subtle complexities or anomalies yet to be uncovered. With advances in data processing and analytical technology, scientists are now able to sift through immense quantities of pulsar data in search of irregularities that could challenge existing models. If patterns were ever detected that significantly deviated from the expected behavior, it might suggest the presence of unknown forces or even artificial influences. For now, however, the signals from pulsars remain best understood as natural astrophysical phenomena, cosmic beacons revealing the intricate workings of neutron stars, rather than deliberate messages from intelligent beings. Yet the quest to unravel the secrets encoded in these pulses continues, with every new observation bringing us closer to understanding both these fascinating stars and the greater cosmic environment in which they reside. Among the legendary puzzles of radio astronomy is the infamous WOW signal, a mysterious burst of radio waves detected in 1977 by astronomer Jerry R. Eman. Lasting for 72 seconds, this signal stood out sharply against the background noise of space, raising the tantalizing possibility that it might have originated from an extraterrestrial civilization. If verified as an intelligent transmission, the WOW signal would represent one of the most profound scientific discoveries in human history. Confirmation that this signal was a deliberate communication from an alien intelligence would fundamentally alter our understanding of our place in the cosmos. It would offer compelling evidence that humanity is not alone and prompt a radical shift in scientific inquiry, encouraging more focused and rigorous searches for extraterrestrial intelligence. Such a discovery would ignite questions about the civilization behind the signal, its technology, its culture, and the motives driving it to reach across the stars to communicate. Until now, the WOW signal remains a singular, unexplained anomaly, a beacon of hope and mystery intertwined, urging humanity to continue its vigilant quest to listen and learn from the whispers of the universe. Furthermore, the study of the wow signal offers an extraordinary gateway into a realm of understanding that transcends mere curiosity about extraterrestrial life and ventures boldly into the heart of advanced communication technologies potentially employed by highly developed civilizations far beyond our own. This enigmatic signal, captured in the mid-1970s, has remained one of the most compelling mysteries in the search for intelligent life beyond Earth. Its investigation could inspire revolutionary breakthroughs, pushing the boundaries of how humanity perceives communication itself, especially over vast cosmic distances that today seem insurmountable. By deciphering the methods through which such signals are generated, we might unveil principles and technologies that could transform our own communication systems, leading to unprecedented advancements. Imagine a future where messages could be transmitted across interstellar space with a clarity and efficiency that dwarfs any technology currently at our disposal. The very act of understanding the wow signal holds promise for developing new tools and methods that could revolutionize long-distance data transmission, possibly integrating quantum principles, novel encoding schemes, or energy-efficient propagation techniques that defy conventional physics. Yet, the implications of the wow signal extend far beyond the technical. They plunge deeply into philosophical territories, challenging and expanding our collective worldview. Humanity's place in the cosmos might be reconsidered in light of the possibility that we are not alone, that there are other beings who have mastered the art of communication on a level far beyond our comprehension. The discovery of a deliberate, intelligent message woven into the fabric of that signal could transform our understanding of life itself and force us to rethink the boundaries of consciousness and intelligence. What might such a message contain? Could it offer a glimpse into the knowledge, culture, or history of a distant civilization? Might it reveal their experiences, warnings, or aspirations? The potential for such a communication to carry profound insights about their world or even universal truths about existence is tantalizing. Decoding it might provide humanity with clues about the fundamental nature of life, evolution, or survival strategies across the galaxy. This prospect fuels an excited and unified pursuit among scientists, philosophers, and the general public alike, a shared quest to seek knowledge that transcends terrestrial limitations. The significance of the wow signal, therefore, is not confined to the mere potential of discovering extraterrestrial life. It lies in how such a discovery could radically reshape multiple domains of human thought and endeavor. Scientifically, it could open new frontiers in astrophysics, signal processing, and space exploration. Technologically, it could spark innovations that change the way we connect across not only Earth, but the stars. Philosophically, it challenges us to expand our concepts of life, intelligence, and the vast universe we inhabit. It beckons us to reconsider what it means to be human in an infinite cosmos, where the silence of space is punctuated by mysterious, possibly intelligent signals waiting to be understood. In the unfathomable vastness of space, where distances are measured in light years and silence often reigns supreme, the search to decode such signals becomes one of the most intriguing and challenging scientific endeavors. Astrophysicists and astronomers relentlessly monitor the cosmic expanse, employing highly sensitive radio telescopes and sophisticated algorithms to detect any sign that might hint at the existence of extraterrestrial intelligence. Signal remains a singular unexplained anomaly, a beacon of hope and mystery intertwined, urging humanity to continue its vigilant quest to listen and learn from the whispers of the universe. Furthermore, the study of the wow signal offers an extraordinary gateway into a realm of understanding that transcends mere curiosity about extraterrestrial life and ventures boldly into the heart of advanced communication technologies potentially employed by highly developed civilizations far beyond our own. This enigmatic signal, captured in the mid-1970s, has remained one of the most compelling mysteries in the search for intelligent life beyond Earth. Its investigation could inspire revolutionary breakthroughs, pushing the boundaries of how humanity perceives communication itself, especially over vast cosmic distances that today seem insurmountable. By deciphering the methods through which such signals are generated, we might unveil principles and technologies that could transform our own communication systems, leading to unprecedented advancements. Imagine a future where messages could be transmitted across interstellar space with a clarity and efficiency that dwarfs any technology currently at our disposal. The very act of understanding the wow signal holds promise for developing new tools and methods that could revolutionize long-distance data transmission, possibly integrating quantum principles, novel encoding schemes, or energy-efficient propagation techniques that defy conventional physics. Yet, the implications of the wow signal extend far beyond the technical. They plunge deeply into philosophical territories, challenging and expanding our collective worldview. Humanity's place in the cosmos might be reconsidered in light of the possibility that we are not alone, that there are other beings who have mastered the art of communication on a level far beyond our comprehension. The discovery of a deliberate, intelligent message woven into the fabric of that signal could transform our understanding of life itself and force us to rethink the boundaries of consciousness and intelligence. What might such a message contain? Could it offer a glimpse into the knowledge, culture, or history of a distant civilization? Might it reveal their experiences, warnings, or aspirations? The potential for such a communication to carry profound insights about their world, or even universal truths about existence, is tantalizing. Decoding it might provide humanity with clues about the fundamental nature of life, evolution, or survival strategies across the galaxy. This prospect fuels an excited and unified pursuit among scientists, philosophers, and the general public alike, a shared quest to seek knowledge that transcends terrestrial limitations. The significance of the wow signal, therefore, is not confined to the mere potential of discovering extraterrestrial life. It lies in how such a discovery could radically reshape multiple domains of human thought and endeavor. Scientifically, it could open new frontiers in astrophysics, signal processing, and space exploration. Technologically, it could spark innovations that change the way we connect across not only Earth, but the stars. Philosophically, it challenges us to expand our concepts of life, intelligence, and the vast universe we inhabit. It beckons us to reconsider what it means to be human in an infinite cosmos, where the silence of space is punctuated by mysterious, possibly intelligent signals waiting to be understood. In the unfathomable vastness of space, where distances are measured in light years and silence often reigns supreme, the search to decode such signals becomes one of the most intriguing and challenging scientific endeavors. Astrophysicists and astronomers relentlessly monitor the cosmic expanse, employing highly sensitive radio telescopes and sophisticated algorithms to detect any sign that might hint at the existence of extraterrestrial intelligence. However, the universe is teeming with natural phenomena that produce radio waves and electromagnetic signals that can easily be mistaken for artificial communications. Pulsars, for example, are neutron stars that rotate rapidly and emit beams of electromagnetic radiation at highly regular intervals. These celestial lighthouses send out signals so precise that they can resemble deliberate communication patterns, yet they arise from purely natural astrophysical processes. Similarly, solar flares and other forms of solar activity, as well as interactions between cosmic rays and interstellar matter, can generate bursts of radiation with characteristics that might mimic structured signals, confusing even the most advanced detection systems. Distinguishing between signals originating from natural phenomena and those potentially engineered by intelligent civilizations presents a formidable challenge. Scientists analyze the frequency, modulation, and patterns within these signals, searching for markers of deliberate encoding or complexity that suggests intelligent design. Yet, without a comprehensive understanding of a signal's origin and its broader context, drawing definitive conclusions remains elusive. What initially appears as an artificial communication may eventually be revealed as a cosmic coincidence or an intricate natural process. The cosmic environment itself adds layers of complexity. The interaction of radiation, magnetic fields, and matter in space can produce unexpected and elaborate patterns that defy straightforward interpretation. The boundaries between natural and artificial signals can blur, creating what might be considered cosmic illusions. This complexity demands that scientists maintain an open mind and a cautious approach, continuously refining their listening techniques while acknowledging the limitations of current knowledge. Every new detection invites us to deepen our understanding of the universe's mechanisms and challenges our assumptions about the nature of signals that traverse the cosmos. In this grand endeavor, phenomena such as quasars or quasi-stellar objects illustrate the profound diversity and power of cosmic processes. Quasars are among the most luminous and energetic objects known, powered by supermassive black holes millions to billions of times more massive than our Sun. These black holes consume surrounding gas and dust, forming accretion disks that heat up as they spiral inward. The immense gravitational forces and energy released create intense radiation, making quasars some of the brightest beacons in the universe. While the prevailing theory attributes the incredible energy output of quasars primarily to these supermassive black holes, understanding the nature of quasars requires looking beyond the black holes themselves. The surrounding environment, including the density and composition of nearby matter, plays a crucial role in modulating their brightness and activity. A quasar actively feeding on vast amounts of material shines with extraordinary intensity, while one in a less material-rich environment dims significantly. Studying such extreme and dynamic phenomena enhances our understanding of cosmic processes and informs our approach to interpreting signals from space. It underscores the importance of context and environment in shaping what we observe, reminding us that the universe is a complex and ever-changing tapestry. The quest to decode signals like the WOW signal is part of a broader scientific mission to unravel the mysteries of the cosmos, probing the depths of space to uncover the origins and nature of intelligence, communication, and life itself. This exploration is more than a scientific challenge. It is a profound journey that stretches the limits of human knowledge and imagination. It demands persistence, creativity, and collaboration across disciplines and cultures. The search for answers about the WOW signal and other enigmatic cosmic messages inspires a collective curiosity that unites humanity in a shared pursuit of understanding our place in the vast, mysterious universe that surrounds us. Furthermore, quasars can be profoundly influenced by the dynamic interactions their host galaxies experience with other galaxies. When galaxies collide, a process that can take millions to billions of years, the immense gravitational forces involved cause vast amounts of gas to funnel directly toward the central supermassive black hole. This influx of material reactivates the quasar's intense energy output, essentially reigniting its luminous activity after periods of dormancy. This dynamic reveals that while a supermassive black hole serves as the essential core driving a quasar's existence, the phenomenon itself is embedded within a far more complex and larger-scale cosmic environment. This environment includes not only the internal structure of the galaxy, but also the flow and availability of gas, as well as external cosmic events such as galactic collisions. Some astrophysicists have taken this understanding further by hypothesizing that quasars might represent different evolutionary stages or phases of black hole activity. This means that quasars could display a range of behaviors and characteristics, rather than fitting into a single, fixed category. Essentially, quasars might be manifestations along a spectrum of black hole evolution, varying as the black hole's feeding patterns and surrounding environment change over time. This perspective paints a more nuanced and intricate picture, positioning quasars not merely as bright points powered by black holes, but as complex astronomical phenomena arising from the interplay of multiple cosmic processes. This ever-evolving scientific view underscores the ongoing quest for deeper insights into the nature of quasars and their role within the vast cosmic tapestry. In a broader sense, a substantial portion of the universe remains completely hidden from direct observation by our current instruments and technologies. Although we are able to observe countless stars, galaxies, and other celestial objects, these visible components represent only a small fraction of the entire universe's makeup. According to scientific estimates, about 95% of the universe consists of dark matter and dark energy, enigmatic substances that neither emit light nor interact with electromagnetic radiation in any detectable way. This means they cannot be seen or measured using conventional astronomical tools. Dark matter, which constitutes approximately 25% of the universe's total mass energy content, differs fundamentally from the ordinary matter that makes up stars, planets, and all known physical objects. Rather than interacting through electromagnetic forces, dark matter primarily influences the universe through gravity. This gravitational effect is crucial because it shapes the formation and behavior of large-scale structures such as galaxies and galaxy clusters. The presence of dark matter is inferred indirectly by observing phenomena like the rotation speeds of galaxies and the way galaxies group together in clusters. Without dark matter's gravitational pull, many cosmic structures would not hold together as they do. Even more mysterious is dark energy, which is thought to comprise roughly 70% of the universe's total energy. Dark energy is the driving force behind the accelerating expansion of the universe, pushing galaxies further apart at an increasing pace. Despite its profound influence on cosmic evolution, dark energy remains elusive. It cannot be directly observed or measured, yet its effects are clearly evident on the grandest cosmic scales. The presence of dark energy forces scientists to rethink traditional notions of gravity and the ultimate fate of the cosmos. These hidden components, dark matter and dark energy, raise profound questions about the fundamental nature of reality and humanity's place within the cosmos. They serve as reminders that the universe is far more intricate and mysterious than what our eyes or even our most advanced instruments can perceive. As researchers develop more sensitive technologies and novel methods to probe the cosmos, the secrets of dark matter and dark energy beckon scientists to venture deeper into the unseen realms that govern the behavior of everything we observe. The laws of physics, as currently formulated, provide a reliable framework for understanding and predicting natural phenomena. Yet, given the vastness and complexity of the universe, some scientists speculate about phenomena that may challenge or even defy these established laws. At the core of this debate lies the recognition that scientific knowledge, including the laws of physics, is always evolving. It is not fixed or final, but subject to refinement and sometimes radical revision based on new evidence. Take, for example, the concept of dark energy. Its discovery has upended previous understandings of gravity and cosmic dynamics because it appears to drive an accelerated expansion that classical physics struggles to fully explain. Ongoing research into dark energy could potentially reveal new physical principles or forces that stretch beyond the currently accepted framework, offering a deeper grasp of how the cosmos operates. Another frontier pushing the boundaries of physics is quantum mechanics. This field studies the behavior of particles at the smallest scales, where the usual rules of classical physics break down. One of the most puzzling quantum phenomena is entanglement, where particles become linked in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. This phenomenon defies classical notions of space and locality, hinting at a level of complexity in the universe that could eventually lead to new theories, possibly requiring a rethinking or extension of known physical laws. Speculative ideas such as warp drives and time travel further challenge our understanding of physical laws. While these concepts remain theoretical and beyond current technological reach, they provide intriguing possibilities for how the laws of physics might be bent or altered under extreme conditions. Scientists continue to explore these ideas, assessing their feasibility and implications for fundamental physics. Ultimately, the pursuit of knowledge in physics is a dynamic journey. Researchers often encounter phenomena that seem to contradict established principles, yet with time and deeper inquiry, these anomalies might be integrated into broader, more comprehensive theories. The boundaries of physics are therefore not fixed, but continually expanding, driven by discovery, curiosity, and the desire to understand the universe at its deepest levels. Turning to the structure of the cosmos, many regions of space are characterized by vast emptiness. These regions are often described as nearly empty because of the immense distances separating galaxies and star systems. To visualize this, imagine the universe as a gigantic sponge filled with heavy holes. Each hole represents a galaxy filled with stars, planets, and intense cosmic activity. The spaces between these holes, however, are enormous voids where almost no matter exists. These cosmic voids can span millions of light years, creating vast stretches of near emptiness that contrast sharply with the dense regions of galaxies. Their formation traces back to the earliest moments after the Big Bang. Initially, the universe was a hot, dense soup of gas and energy. Over billions of years, gravity caused this matter to clump together, forming the gas clouds, stars, galaxies, and even larger cosmic structures we observe today. The regions where matter was less concentrated eventually evolved into these enormous voids, remnants of the uneven distribution of matter in the early universe. In this way, the universe's large-scale structure resembles a cosmic web, where galaxies and clusters form the strands and knots interwoven with vast empty regions. This structure continues to evolve under gravity's influence, shaping the cosmic landscape that surrounds us. This expansive and intricate view of the cosmos reveals how much remains to be explored and understood. Each discovery adds a new piece to the cosmic puzzle, challenging scientists to reconsider what they know and to push further into the mysteries that lie beyond our current horizons. The universe, in all its complexity and grandeur, invites us to deepen our curiosity and expand our quest for knowledge indefinitely. Cosmic expansion continuously stretches the fabric of the universe, causing galaxies to drift farther apart over time. This gradual distancing accentuates the enormous gaps between clusters of galaxies, creating vast regions known as voids. Some of these voids are so immense that they appear almost completely empty, containing only a sparse scattering of galaxies that seem like distant islands in an ocean of darkness. Despite their apparent barrenness, these regions are far from being truly empty. Within the seeming voids, there exist faint traces of matter that defy the naked eye, diffuse intergalactic gas, elusive dark matter, and mysterious signals that hint at hidden activity within these cosmic deserts. These subtle presences serve as proof that even the most desolate stretches of space are part of an ever-shifting, dynamic cosmic structure, one that is constantly evolving across incomprehensible spans of time and space. The vastness of the cosmos holds countless secrets beyond what visible light can reveal. While traditional astronomy depends heavily on the observation of light emitted, absorbed, or reflected by celestial objects, there are entities that evade detection by simply not interacting with electromagnetic radiation in conventional ways. Dark matter is the most prominent example of this phenomenon. Comprising a substantial portion of the universe's total mass, dark matter does not emit light, nor does it absorb or reflect it, making it completely invisible to all standard forms of optical observation. Instead, its existence is inferred indirectly by its gravitational influence. For instance, dark matter affects the motions of stars within galaxies and the behavior of galaxy clusters, acting as a hidden scaffolding that shapes the cosmos. Beyond dark matter, other invisible phenomena populate the universe's vast, shadowy corners. Certain types of black holes, especially those situated in regions devoid of nearby matter, can evade detection. Unlike black holes in active environments, which reveal themselves through the violent destruction of surrounding stars or the intense radiation emitted as matter falls into them, these isolated black holes remain silent predators. They lurk undetected in cosmic shadows, hidden from our instruments because they interact with very little matter that would otherwise betray their presence. This silent, stealthy nature adds layers of mystery to the cosmic landscape. Expanding on this idea, theoretical astrophysics proposes the existence of primordial black holes. Unlike their stellar counterparts formed from the death of massive stars, primordial black holes may have originated in the chaotic, high-density conditions of the early universe, shortly after the Big Bang. These hypothetical objects could range in size from microscopic scales to several times the mass of the Sun. Their subtle presence could explain some of the unseen mass in the universe, and might even be linked to dark matter, though this remains a subject of ongoing research and debate. Considering such possibilities invites speculation about the existence of other exotic forms of matter and structures that could remain hidden even more effectively than known entities. Furthermore, the universe is filled with particles that pass through matter almost undisturbed, such as neutrinos. These nearly massless particles are incredibly difficult to detect because they rarely interact with ordinary matter. Trillions of neutrinos produced in the fiery hearts of stars, supernova explosions, and other energetic cosmic events stream silently through space and even through our own bodies without leaving a trace. Despite their ghostly nature, Neutrinos carry valuable information about processes occurring in the most extreme environments across the universe, providing insight into phenomena otherwise hidden from direct view. The contrast between the visible universe and the invisible landscape of dark matter, black holes, and elusive particles forms a profound duality in our understanding of the cosmos. While our eyes and telescopes capture the brilliance of stars, galaxies, and nebulae, the unseen components silently weave the very fabric of cosmic structure. They remind us that our picture of the universe is incomplete, that vast realms remain hidden beneath the surface of visible light. This mystery beckons scientists to push the boundaries of observation and theory, revealing a cosmos more complex, dynamic, and enigmatic than previously imagined. In this grand cosmic tapestry, voids are particularly fascinating. These enormous empty spaces stretch between filaments of galaxies, forming a kind of cosmic web. Imagine a vast three-dimensional spider web, where the strands represent clusters and groups of galaxies, and the spaces in between are the voids. Some voids span hundreds of millions of light-years across, dwarfing familiar cosmic structures and ranking among the largest known features of the universe. They arise naturally from the interplay of gravity and the uneven distribution of matter that originated shortly after the Big Bang. Initially, the universe was a hot, dense mixture of particles and radiation, but small fluctuations in density caused matter to clump in certain regions, while leaving others relatively empty. Over billions of years, gravity drew matter into dense clusters and filaments, leaving the low-density voids behind. Studying voids is crucial for understanding cosmic history and the mysterious forces that shape the universe. Because voids correspond to areas where dark matter is less concentrated, they visually highlight the gravitational dynamics governing the large-scale structure of the cosmos. By mapping voids and analyzing their properties, scientists gain valuable insights into the distribution of dark matter, the nature of cosmic expansion, and the evolution of the universe. These vast empty spaces are not simply cosmic accidents, but integral components of the universe's grand design. The search for unseen cosmic objects extends beyond voids to compact entities such as black holes. Traditionally, astronomers classify black holes into three main categories: stellar black holes formed from collapsing stars, intermediate black holes with masses between stellar and supermassive, and supermassive black holes lurking at the centers of galaxies. However, theories suggest the potential existence of other black hole types, including primordial black holes. These could have formed in the dense and chaotic conditions of the early universe, possibly playing a role in dark matter's elusive nature. Unlike typical black holes, primordial black holes might be much smaller but exist in enormous numbers, contributing subtly to the cosmic mass balance in ways that remain difficult to detect. This exploration into the hidden and invisible universe paints a picture of a cosmos filled with secrets waiting to be uncovered. It challenges humanity's perception of reality and expands the frontier of knowledge beyond what can be seen or directly measured. The dark matter shaping galaxies, the silent black holes lurking in empty space, and the ghostly particles streaming through the universe all point to a more intricate and mysterious universe than our senses alone can grasp. As science advances, it continues to peel back layers of the cosmic veil, revealing an ever more wondrous and complex universe where the unknown vastly outweighs the known. Furthermore, researchers are deeply engaged in unraveling the mysteries of other compact celestial objects, most notably neutron stars, which stand as some of the universe's most extraordinary remnants of supernova explosions. These neutron stars are incredibly dense, packing more mass than our sun into a sphere that can be as small as about 10 kilometers across. This incredible density means that a single teaspoon of neutron star material would weigh billions of tons on Earth. Such objects challenge our fundamental understanding of physics because they exist under conditions so extreme that the laws governing matter and energy begin to behave in ways we have yet to fully grasp. The study of neutron stars is complicated by their extreme size and density. They are both tiny and tremendously massive. Their gravitational fields are so intense that they warp space-time around them, making the physics of these stars a fascinating frontier where quantum mechanics and general relativity intersect. Neutron stars often reveal themselves through pulsars, rapidly spinning neutron stars that emit beams of electromagnetic radiation. These pulsars serve as cosmic lighthouses, their pulses sweeping across space at incredibly regular intervals, allowing astronomers to probe the star's properties with extraordinary precision. Adding further layers to this cosmic puzzle are the hypothesized quark stars. These hypothetical objects, theorized to be even more exotic than neutron stars, might be composed not of neutrons, but of their fundamental building blocks, quarks. Quark stars are thought to arise if the pressure inside a neutron star becomes so immense that neutrons break down into their constituent quarks, creating a state of matter denser than anything we have observed. Although no quark star has yet been definitively identified, the mere possibility of their existence pushes the boundaries of astrophysics and particle physics, opening new windows into the behaviors of matter at densities surpassing atomic nuclei. Driving this exploration forward are monumental technological advances in observational astronomy. Instruments designed to detect gravitational waves, ripples in space-time caused by the acceleration of massive objects, have revolutionized our capacity to observe phenomena previously hidden from traditional telescopes. The first detection of gravitational waves from colliding black holes confirmed a century-old prediction from Einstein's theory of general relativity, marking a transformative moment in astronomy. Since then, these detectors have observed multiple mergers of black holes and neutron stars, unveiling cosmic dances that happen billions of light years away, but sending ripples we can measure here on Earth. As detection techniques grow ever more sensitive and sophisticated, the potential to discover new types of compact objects looms large. These discoveries will not only enhance our understanding of their physical properties, but also shed light on how such objects influence the very fabric of space and time itself. This unfolding journey of discovery is exhilarating because each new finding tends to raise fresh questions and demands new theoretical frameworks, driving the frontiers of knowledge into uncharted cosmic territories. The importance of these findings extends far beyond understanding black holes or neutron stars alone. They can fundamentally alter our conception of the universe's origins, composition, and ultimate destiny. Each breakthrough deepens our grasp of the cosmos and can provide insights into the deepest questions about existence, such as what the universe was like in its earliest moments and how its vast complexity emerged from simple beginnings. The universe, with all its hidden layers and mysterious corners, continually invites humanity to probe deeper, reminding us that vast cosmic secrets remain just beyond our current reach. And one particularly intriguing idea emerging from the intersection of cosmology and philosophy is the concept of ancient remnants from failed universes. Imagine the universe not as a singular, isolated entity, but as a vast tapestry woven from countless threads, each thread representing a potential reality. Some of these universes might have flourished, evolving complex structures and sustaining conditions necessary for existence, while others may have never fully formed or survived the conditions required for long-term stability. The remnants or echoes of these failed universes could, in theory, persist in subtle ways within our own universe. Scientists speculate that certain cosmic anomalies or structures that defy straightforward explanations might be faint traces or echoes of these ancient realities. For instance, tiny irregularities detected in the cosmic microwave background radiation, the faint afterglow of the Big Bang, may carry signatures suggesting interactions or influences from other universes that no longer exist. This notion invites profound reflection on the very nature of reality and the possibility that our universe is just one among many in a vast multiverse. The multiverse theory posits that our universe might be one of countless others, perhaps infinitely many, each with its own laws of physics, structures, and histories. In this vast cosmic landscape, universes could be born, evolve, and eventually perish independently of each other. While they might not interact directly, the cosmic structures within our own universe could bear subtle imprints or influences from these other realms. Phenomena such as black holes or other high-energy cosmic events might serve metaphorically as bridges or gateways, hinting at the presence of realms beyond our observable universe, realms that may have been lost or forgotten over time. Though the idea of ancient remnants and the multiverse remains speculative, it is a field ripe for discovery, requiring a synthesis of profound theoretical insights and the relentless pursuit of observational evidence. As our technological prowess expands, future missions may uncover clues that illuminate the vast history of existence and reveal hidden chapters of reality that extend beyond the boundaries of our known cosmos. Gravitational wave echoes are a particularly fascinating phenomenon within this context. When two massive objects, such as black holes or neutron stars, collide and merge, they produce powerful ripples in spacetime that travel outward at the speed of light. Yet the initial burst of these gravitational waves is often followed by a series of fainter echoes, reverberations that ripple through spacetime, much like sound waves bouncing off the walls of a canyon. These echoes arise because the newly formed black hole or neutron star vibrates in response to the immense energy released during the merger, much like a drumhead oscillating after being struck. Detecting these gravitational wave echoes requires incredibly sensitive instruments capable of measuring minuscule variations in the distances between objects separated by kilometers or even millions of kilometers. Observatories like LIGO and Virgo have captured these faint signals, providing invaluable data that could unravel deeper mysteries about the nature of spacetime itself. These echoes might reveal the detailed structure and properties of black holes, including their event horizons, the enigmatic boundaries beyond which nothing can escape, and how quantum effects manifest at these extremes. By studying gravitational wave echoes, scientists hope to gain insights into quantum gravity, a theoretical framework that seeks to reconcile the principles of quantum mechanics with Einstein's theory of general relativity. Understanding how gravity behaves under the most extreme conditions found near black holes could open new windows into the fundamental workings of the universe. This research represents an exciting frontier in astrophysics, where theory and observation converge to explore the deepest layers of reality. In the cosmos, some star systems are remarkable for their extraordinary density and chaotic nature. The dense packing of stars in globular clusters, for instance, creates environments where gravitational forces are so strong that stars are drawn into frequent interactions, collisions, and near misses. These stellar gatherings are cosmic laboratories where the interplay of gravity, stellar evolution, and cosmic history unfolds in dramatic and sometimes violent ways. Within these dense star clusters, stars are born, live out their nuclear lives, and eventually die, often in spectacular explosions such as supernovae. These explosions not only mark the death of massive stars, but also seed their surroundings with heavy elements essential for the formation of new stars and planets. Shock waves from supernovae compress nearby clouds of gas and dust, triggering the birth of fresh stars and continuing the cycle of cosmic renewal. This ongoing dance between gravity pulling inward and forces pushing outward, like stellar winds and explosion-driven shock waves, creates turbulent and chaotic environments within star systems. The resulting complexity shapes the evolution of galaxies and contributes to the dynamic, ever-changing nature of the universe. Through the study of these compact objects, gravitational waves, and cosmic anomalies, humanity embarks on a relentless quest to understand the universe in all its intricate detail and vast grandeur. Each discovery, each observation, adds a new piece to the cosmic puzzle, expanding our view of existence and pushing the boundaries of what we know about the fabric of reality itself. Moreover, in the dense and bustling neighborhoods of stars, the paths that these stellar bodies follow can shift and become unstable over time, creating a cosmic dance that is both intricate and unpredictable. When stars pass close to one another within these crowded regions, their mutual gravitational attraction pulls and tugs, altering the trajectories they once followed. This gravitational interaction can send their orbits spiraling into erratic and chaotic motions, which ripple through the system like an invisible tide of disruption. The result is a dynamic and complex environment where the interplay between stars generates a constantly evolving scene full of tension and transformation. In such crowded stellar systems, the outcome of these gravitational encounters often results in a mixed population of celestial bodies. Among them are tightly bound binary star systems, pairs of stars locked in a gravitational embrace, orbiting each other in a rhythmic, cosmic waltz. These binary stars form stable units amidst the chaos, held together by the relentless pull of gravity. Yet alongside them there exist rogue stars, solitary wanderers expelled from their original homes after violent encounters with their neighbors. These stars are hurled into the vast emptiness of interstellar space, their journeys transformed from orderly orbits to unpredictable voyages through the galaxy's dark void. Adding another layer of complexity to these dense star clusters is the presence of black holes, mysterious and powerful remnants of massive stars that have ended their lives in catastrophic explosions. Black holes serve as gravitational anchors within these systems, their immense pull further twisting and complicating the surrounding dynamics. Their influence can send nearby stars into wildly eccentric orbits, stretching their paths into elongated loops or even pulling them inexorably closer until they are swallowed whole. These black holes act as centers of chaotic activity, creating localized hotspots where the laws of physics are pushed to their limits and the fabric of space-time itself warps under their overwhelming presence. The density and turmoil observed in these stellar systems arise from an intricate web of gravitational interactions, explosive stellar events, and ongoing dynamical evolution. Together, these factors paint a vivid and detailed picture of life among the stars, revealing the universe as a place of constant change and cosmic drama. Neutron stars represent one of the most extraordinary environments found in the cosmos. These stellar remnants present conditions so extreme that familiar states of matter, such as solids, liquids, gases, and plasma, transform into forms that challenge our understanding. Within the core of a neutron star, the density reaches staggering levels, compressing atomic structures beyond recognition. Under the immense pressure, electrons and protons are forced to merge, creating neutrons in a state known as neutron fluid, a remarkable phase of matter where neutrons flow freely, unbound by the atomic constraints that govern normal matter. But this remarkable journey into extreme physics does not end there. Deep within the core, scientists theorize that even more exotic states of matter may exist, pushing the boundaries of known physics. One such possibility is the formation of quark-gluon plasma, a primordial state believed to have existed shortly after the Big Bang. In this plasma, quarks, the elementary particles that combine to form protons and neutrons, exist freely, no longer confined within larger particles, but moving independently in a seething soup-like sea. This extraordinary state challenges the very notion of matter as we know it. Moreover, the crushing pressures inside the neutron star's core might give rise to phases of matter not yet fully understood or classified. Among these is the hypothesized existence of hyperons, particles made of different combinations of quarks that could radically alter the star's internal structure and behavior. These new forms of matter open doors to unexplored realms of physics, inviting us to reconsider the fundamental principles governing the universe under conditions of unimaginable pressure and density. Understanding these potential exotic states within neutron stars does more than deepen our knowledge of these compact objects. It forces a re-examination of physics itself, revealing how the universe behaves in extremes far beyond anything found on Earth. Among neutron stars, magnetars stand out as uniquely fascinating entities. Known for their unimaginably powerful magnetic fields, magnetars possess magnetic strengths that far surpass those of typical neutron stars and ordinary stars alike. Imagine the remnant core of a massive star that has exploded in a supernova, compressed into a volume so dense that a sugar cube-sized amount would weigh as much as a mountain on Earth. Within this tiny yet incredibly heavy core, the magnetic field can be 1,000 trillion times stronger than the strongest magnets humans have created. This immense magnetic field arises from the star's formation process. As a giant star runs out of nuclear fuel, it collapses under gravity, causing it to spin rapidly due to the conservation of angular momentum. This rapid rotation compresses the magnetic field lines, intensifying them dramatically. In magnetars, additional, unique processes during the star's life amplify these fields to unprecedented levels, possibly linked to the violent, turbulent conditions during their birth. The effects of such strong magnetic fields are profound and far-reaching. Magnetars frequently experience explosive surface events, releasing bursts of X-rays and gamma rays that can briefly outshine entire galaxies. These bursts occur when twisted and unstable magnetic field lines suddenly realign, unleashing enormous amounts of energy in spectacular flares. The magnetic forces also accelerate particles in the surrounding space, generating additional radiation and heat, making magnetars among the most hostile environments in the cosmos. Beyond their dramatic behavior, magnetars serve as natural laboratories for studying extreme physics. Their existence challenges current understanding of matter, magnetism, and fundamental forces, offering a glimpse into phenomena that push the limits of known science and hint at new physics waiting to be discovered. The life cycles of massive stars further enrich this story of cosmic transformation. A massive star begins its life fusing hydrogen in its core, producing energy that balances the inward pull of gravity. As the star ages and depletes its hydrogen fuel, it evolves, swelling into a red giant and progressing through stages where it fuses heavier elements like helium and carbon. This fusion continues, building elements up to iron, the heaviest element the star can fuse in its core. When the star accumulates an iron core, a critical turning point occurs. Iron fusion does not generate energy, so the core loses the ability to resist gravitational collapse. This imbalance triggers a catastrophic implosion of the core, resulting in a supernova, a spectacular explosion that blasts the star's outer layers into space. But the supernova is not always the end of the story. The dense remnants left behind, such as neutron stars, can themselves face further collapse. If the mass of the neutron star exceeds a critical threshold, the immense pressure forces it to collapse again, potentially transforming it into a black hole. This process reveals that a single stellar body can undergo multiple phases of collapse and rebirth, evolving from a massive star to a neutron star and, under the right conditions, finally becoming a black hole. This cycle of cosmic death and rebirth highlights the extraordinary complexity and dynamism of the universe, where stars live dramatic, transformative lives that shape the very fabric of space and time. Moreover, in certain binary star systems, the relationship between the two stars is far from simple. It becomes a complex, intertwined interaction filled with dynamic and dramatic phenomena. These stars, locked in a gravitational embrace, engage in a cosmic dance where matter and energy continuously exchange hands in ways that can radically alter their individual paths. One of the most striking processes observed in such systems is periodic mass transfer, a phenomenon where one star literally strips material from its companion. This transfer of stellar material is not just a simple flow, but a catalyst that can reignite nuclear fusion within the receiving star, injecting new life into a star that might have been fading or stabilizing, or it can hasten the decline of the donor star by stripping away its outer layers. This matter exchange can influence the evolution of both stars, sometimes triggering a collapse in one that leads to the formation of neutron stars, black holes, or other exotic remnants. This intricate interplay reveals that the journey of stars through their life cycles is not a straightforward, linear progression. Instead, it is a series of transformative events punctuated by collapse and rebirth, where stars can evolve into entirely new cosmic entities. Each phase of this celestial choreography contributes profoundly to the vast and complex tapestry of the universe. When one star dies, its whether as dust, gas, or compact stellar cores seed the cosmos, influencing the birth of new stars, planetary systems, and ultimately the ingredients for life itself. Thus, the universe is constantly renewing itself through these cycles of destruction and creation, with binary stars playing an essential role in this cosmic renewal. The idea that stars could exist that are older than the universe itself challenges our understanding and invites us to delve deeper into the complexities of cosmic time. The universe, as determined through meticulous observations of the oldest light available to us, the cosmic microwave background radiation, is approximately 13.8 billion years old. This ancient radiation is the afterglow of the Big Bang, the event that marked the beginning of the universe as we know it. Yet, when we consider stars, their life cycles can vary dramatically depending on their initial mass, composition, and environment. In this cosmic context, the oldest stars known to astronomers are often classified as population 2 stars, found in dense, ancient globular clusters scattered throughout galaxies, including our own Milky Way. These population 2 stars formed soon after the Big Bang, when the universe had cooled enough for the first elements beyond hydrogen and helium to come together and form stars. Many of these stars are faint and long-lived, with some potentially surviving for tens of billions of years, far longer than the current age of the universe. Despite their incredible ages, however, none of these stars can be definitively older than the universe itself. This fact roots all known stars firmly within the cosmic timeline, making the notion of stars existing before the universe more a fascinating theoretical puzzle than a scientific reality. As astronomical techniques and technology improve, new discoveries may challenge or refine this understanding, revealing previously unaccounted for phenomena or ancient celestial objects that deepen our comprehension of cosmic history. Each star tells a story, and by studying their ages, astronomers piece together the grand narrative of cosmic evolution. This ongoing research highlights the interconnectedness of all matter and energy in the universe, a unity that stretches back billions of years and extends across incomprehensible distances. Among the most captivating star systems are binary stars, pairs of stars bound together by mutual gravitational attraction, orbiting a common center of mass. Visualize 2 dancers moving in perfect synchronization, their motions a blend of grace and precision, bound together by an invisible force. This gravitational bond ensures that the stars remain closely connected, thus their interactions a complex blend of push and pull that shapes their fate. Binary systems are incredibly diverse. Some pairs consist of 2 stars that are nearly identical in size, temperature, and brightness, while others are mismatched, with one star being significantly larger or more luminous than its partner. This diversity creates a dynamic range of interactions and evolutionary pathways. As the stars age, their evolution can lead to some of the most dramatic and violent events in the cosmos. For example, when one star in a binary system expands into a red giant, a swollen, luminous phase toward the end of a star's life, it may engulf its smaller companion. Imagine a balloon inflating until it completely envelops a nearby object. This scenario mirrors what happens as the giant star's outer layers expand and wrap around its partner. During this engulfment, gravitational forces and the exchange of stellar material can strip mass from the smaller star, altering both stars' evolutionary trajectories. In other binary systems, especially those involving neutron stars or black holes, the interaction can be even more extreme. These compact objects, remnants of massive stars that have undergone supernova explosions, exert powerful gravitational forces. As they orbit each other, they emit gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity. Over millions of years, these waves carry energy away from the system, causing the 2 objects to spiral closer and closer together. Eventually, this inward spiral leads to a catastrophic merger, an event that releases colossal amounts of energy, often observed as short gamma-ray bursts or supernova explosions. These explosive finales are among the most energetic and awe-inspiring events in the universe, illustrating the incredible forces that govern stellar evolution in binary systems. The universe is a vast and wondrous realm where matter takes on forms that extend far beyond our everyday experiences. Among these are exotic particles, fundamental components of matter that differ from the protons, neutrons, and electrons familiar to us in atoms. These exotic particles may play a crucial role in the composition of certain celestial bodies, such as neutron stars or hypothetical dark matter stars. To understand this concept, consider that ordinary stars primarily form from hydrogen and helium, the simplest and most abundant elements created in the early universe. These elements provide the fuel for nuclear fusion, the process powering stars, and producing the heavier elements that compose planets and life itself. The potential involvement of exotic particles in celestial bodies opens new frontiers in astrophysics and particle physics. For example, neutron stars are incredibly dense remnants where matter is compressed to extraordinary densities, possibly allowing exotic states of matter or unknown particles to exist. Investigating these possibilities helps scientists explore fundamental questions about the nature of matter, the forces that govern it, and the ultimate fate of stars. Throughout this cosmic journey, the life and death of stars, whether solitary or in binary pairs, serve as vital chapters in the ongoing story of the universe. From the fusion fires that light up theirs, to the violent collisions and transformative events they undergo, stars shape the evolution of galaxies, the formation of planets, and the emergence of life. By studying their interactions, ages, and compositions, we gain insight into the profound connections between all things in existence, reminding us of the intricate, beautiful, and ever-changing nature of the cosmos. However, within the most extreme corners of the universe, conditions evolve in ways that enable phenomena utterly alien to our everyday experience, spawning realms where the ordinary rules of matter and energy bend and transform beyond recognition. One of the most captivating and enigmatic manifestations of these extreme environments emerges in the form of neutron stars, celestial remnants born from the violent deaths of massive stars in supernova explosions. These remnants, compressed to unimaginable densities by intense gravitational forces, exist as nature's densest stable objects aside from black holes. In these stellar remnants, gravity becomes so overwhelmingly powerful that it forces protons and electrons to merge, creating a dense sea of neutrons, a state of matter that is incomprehensibly compact compared to anything encountered on Earth. As the density within these neutron stars escalates further, theorists have proposed the possible emergence of even more exotic forms of matter. Among the most fascinating candidates is strange matter, an exotic substance where strange quarks join the more familiar up and down quarks that make up neutrons and protons. Unlike ordinary matter, composed mostly of these up and down quarks, strange matter incorporates the strange quark, introducing new properties that might grant it enhanced stability under the incredible pressures inside neutron stars. The very idea that an entire star might be composed solely of strange matter hints at a profoundly different kind of stellar object, one potentially more stable than ordinary nuclear matter under extreme density, yet completely foreign in its constitution. Pushing the boundaries of theoretical astrophysics even further, some researchers hypothesize the existence of quark stars. Unlike neutron stars, which contain tightly packed neutrons, quark stars could be made up of free quarks, the fundamental building blocks of matter that are usually confined within protons and neutrons. In this extraordinary state, quarks might roam unbound, forming a new phase of matter exhibiting unique physical characteristics. These quark stars would potentially cool and emit radiation in distinctive ways, setting them apart from their neutron star cousins. Their existence remains speculative, but the search for such objects drives intense scientific inquiry at the intersection of astrophysics and particle physics, challenging researchers to explore nature's most extreme limits. Despite the allure of these exotic theories, definitive observational evidence confirming the existence of strange matter stars or quark stars remains elusive. The search to uncover their true nature involves the combined efforts of astronomers, nuclear physicists, and particle theorists. They employ sophisticated telescopes and particle accelerators to decode the messages encoded in cosmic signals, looking for subtle clues in gravitational waves, electromagnetic emissions, and the behavior of matter under extreme conditions. This quest not only deepens our understanding of the universe, but also reveals the mind-boggling complexity of the cosmos, where familiar rules break down and new, unimaginable forms of matter come into being. In a different yet equally intriguing realm of cosmic inquiry lies the pursuit of discovering planets with environments fundamentally opposite to Earth's. To imagine such a planet, one must dissect the myriad environmental parameters that define Earth: temperature, atmospheric composition, pressure, gravity, and the planet's position relative to its star. Earth enjoys a temperate climate, supporting a rich diversity of life adapted to moderate temperatures, balanced atmospheric gases, and a stable gravitational field. In stark contrast, envision a planet residing in a domain of extremes, where scorching heat or bone-chilling cold reigns supreme, eradicating the presence of liquid water, the cornerstone of life as we know it. On this hypothetical planet, temperatures might soar far beyond what we consider survivable or plunge into frigid realms where water exists only as ice. Such extremes would render the environment hostile to the ecosystems we are familiar with, fundamentally altering any biological possibilities. The atmosphere of this opposite planet could be dense and laden with toxic gases, such as sulfur dioxide or methane, creating conditions inhospitable to respiration and photosynthesis, processes essential to Earth's life forms. Atmospheric pressure might diverge dramatically as well, crushing anything resembling terrestrial life under immense force or leaving it exposed to the harsh vacuum and relentless cosmic radiation in near space-like conditions. Gravity, another crucial environmental factor, plays a vital role in shaping life and planetary conditions. Earth's gravitational pull is finely balanced, enabling stable structures, liquid water retention, and biological processes to flourish. Imagine instead a world with gravity significantly weaker, where structures could barely hold their shape, or conversely, gravity so strong that it compresses everything into dense, compact forms, suffocating the environment from a biological perspective. Such extremes would radically redefine the planet's habitability, posing challenges to any form of life patterned after Earth's blueprint. Further complicating this cosmic puzzle is the planet's distance from its parent star, a parameter that profoundly influences its climate and potential to sustain life. Earth's position lies within the habitable zone, a region where temperatures allow liquid water to exist. A planet closer to its star would be bombarded with relentless solar radiation and scorching heat, transforming it into a fiery wasteland. Conversely, one too distant would become a frozen desert, plunged into eternal darkness and frigid temperatures. Thus, even minor shifts in orbital distance can produce environments utterly inhospitable to life as we understand it. Although planets exhibiting extreme conditions do exist within our cosmic neighborhood, like Venus with its oppressive heat and toxic atmosphere, or Mars with its frigid climate and thin air, finding a planet that represents the absolute opposite of Earth, where the fundamental physical and chemical rules diverge radically, remains an immense challenge. Astronomers continuously scour the galaxy, searching for exoplanets with diverse characteristics, hoping to uncover worlds that expand our understanding of planetary systems and life's potential forms. The vastness of the universe ensures that the possibilities for such discoveries remain open, fueling ongoing exploration and speculation. Adding another layer to this cosmic complexity are rogue planets, celestial wanderers that drift through space untethered to any star. Unlike planets orbiting stars in traditional systems, these rogue planets traverse the darkness of interstellar space alone, their origins often traced back to formation within protoplanetary disks, followed by gravitational ejections caused by interactions with other planets or passing stars. These solitary wanderers defy conventional planetary models, challenging scientists to rethink the ways planets can form, evolve, and survive without the warmth and light of a central star. Their mysterious journeys through the cosmic void offer another window into the universe's incredible diversity and the endless variety of planetary phenomena. In sum, the universe presents an astonishing array of extraordinary objects and environments, from neutron stars harboring matter in unimaginable states, to planets existing in conditions utterly alien to our own, to rogue worlds roaming freely through space. Each discovery pushes the boundaries of human knowledge, compelling us to reconsider our place in the cosmos and inspiring relentless curiosity about the hidden corners of reality where nature's laws play out in the most extraordinary fashions. Additionally, it is entirely conceivable that some planets might find themselves orbiting around black holes or neutron stars, both of which are incredibly dense and fascinating remnants of massive stars that have reached the end of their life cycles. These objects, though small in size compared to regular stars, wield extraordinary gravitational forces so powerful that if a planet were to wander too close, it could become ensnared in an orbit, effectively captured by the intense pull. However, such orbits would differ drastically from those we observe around regular stars due to the unique and extreme nature of the gravitational fields generated by these compact objects. In the case of rogue planets drifting through the vast emptiness of space, or those locked in orbit around black holes, the environments are profoundly hostile to life as we know it. The absence of a nearby star means there is no reliable source of warmth or light, two critical ingredients for sustaining life on Earth. The cold darkness envelops these planets, making any form of life highly unlikely or dependent on extraordinary adaptations. If we shift our focus to planets orbiting neutron stars, the scenario becomes even more extreme. A neutron star is the ultra-dense core left behind after a supernova explosion, a catastrophic death throw of a massive star. These neutron stars emit intense radiation, and the gravitational forces in their vicinity can be violent and unpredictable. Any planet caught in this environment would be bombarded by powerful radiation and subjected to gravitational stresses, unlike anything experienced by planets orbiting more typical stars. Despite these challenges, the mere possibility that such planets exist reveals the astonishing diversity of planetary systems throughout the cosmos. It expands our understanding of how celestial bodies interact and evolve, emphasizing that the universe is far more varied and dynamic than the relatively calm neighborhood of our solar system. By the year 2024, astronomers have made remarkable progress in identifying exoplanets, planets outside our solar system that share characteristics similar to Earth. This progress has sparked immense excitement because these Earth-like planets could potentially harbor life. Scientists focus particularly on planets located within what is called the habitable zone, the region around a star where conditions might allow liquid water to exist on the planet's surface. Water, as we understand it, is a fundamental prerequisite for life. One of the most intriguing recent discoveries is a planet with a size roughly comparable to Earth's, orbiting a star not far from our solar system. This exoplanet lies comfortably within the habitable zone of its star, meaning that surface temperatures could support liquid water, a key factor in nurturing life. In addition to this promising location, the composition of the planet's atmosphere suggests the presence of clouds and even climatic conditions that might resemble those found on Earth. Such atmospheric features could imply the existence of weather patterns and a potential for sustaining life-friendly environments. Another fascinating candidate among these exoplanets has been identified with a rocky surface, much like Earth. Atmospheric measurements hint at the possibility that this planet experiences a climate that could support life, including seasonal changes. This stability and diversity of conditions raise hopes that it might foster a range of environments suitable for different forms of life. Further still, astronomers have observed an exoplanet that exhibits signs of geological activity, such as volcanic processes. These volcanic activities are significant because they can sustain a dynamic atmosphere, contributing to the regulation of weather patterns and cycling essential elements, both crucial for maintaining a life-supporting environment. Each of these discoveries adds layers to the growing evidence that we may not be alone in the universe. Ongoing studies aim to analyze the atmospheres and chemical compositions of these distant worlds in even greater detail, searching for biosignatures, substances or patterns that could indicate the presence of life. With each new piece of data, astronomers move closer to answering one of humanity's most profound questions. Are we the only living beings in this vast and mysterious universe? The year 2024 stands as a milestone in our expanding understanding of the cosmos and the possibilities it holds. When contemplating life beyond Earth, it is vital to keep an open mind about the forms that such life might take. Life on our own planet thrives under an astonishing variety of conditions, from the crushing pressures and darkness of deep ocean trenches to the blazing heat of deserts. This remarkable adaptability encourages scientists to explore how life could exist elsewhere, even in environments that seem inhospitable by earthly standards. Many alien worlds discovered orbit stars under extreme conditions. Some are so close to their stars that they endure intense heat, while others linger in the cold darkness of deep space, far from any stellar warmth. Life in such extreme places might not rely on sunlight or warmth at all. Instead, it could be based on biochemical processes vastly different from those found on Earth, perhaps extracting energy from chemical reactions within the planet itself, rather than from light. This idea finds support in Earth's extremophiles, organisms that survive and thrive in some of the harshest environments on our planet, including acidic hot springs, radioactive waste sites, and frigid polar regions. The concept that life can adapt to such varied and extreme surroundings suggests that a planet's atmosphere, surface conditions, and available resources will largely determine the kinds of life that could emerge. It is even plausible that alien life forms might be built on chemical foundations entirely unlike those of carbon-based life on Earth. Scientists have speculated about the possibility of silicon-based life, given silicon's abundance in the universe. Silicon might enable biochemistries that are profoundly different, perhaps better suited for surviving in high radiation environments or under extreme pressures. Imagine creatures that can withstand radiation levels that would obliterate any earthly organism or live in environments with crushing pressures beyond human endurance. Such life forms might thrive in oceans of liquid methane, float in thick gaseous atmospheres rich in exotic chemicals, or reside in subterranean caves beneath a planet's surface, protected from harsh conditions above. Thus, the potential variety of alien life forms is limited only by the diversity of conditions throughout the universe. As we continue to explore space and expand our knowledge, our understanding of what life might be grows ever more complex and fascinating. This quest not only broadens our horizons, but also provokes profound philosophical questions about our place in the cosmos. At its heart, it echoes humanity's timeless inquiry. Are we alone, or are there other beings out there utterly different from us, existing in ways we cannot yet imagine? Among the fascinating celestial bodies that astronomers study are tidally locked planets. These are worlds that have synchronized their rotation with their star, in such a way that one side always faces the star, basking in continuous daylight, while the opposite side remains in perpetual darkness. This phenomenon is akin to a spinning top that gradually slows until it stops, always showing the same face to the surface it orbits. On a tidally locked planet, the star-facing side endures constant illumination, with heat and light pouring in ceaselessly. This side may experience soaring temperatures, while powerful winds could sweep across the landscape, driven by the stark temperature contrasts between the scorching day side and the cold night side. The dark side, shrouded in eternal night, could plunge into freezing cold, creating an environment starkly different from the starlit hemisphere. This unique configuration produces extreme environmental contrasts on the same planet, raising intriguing questions about the possibility of life and weather patterns. Scientists hypothesize that the boundary region between the day and night sides, the twilight zone, might harbor more moderate temperatures and conditions suitable for liquid water and possibly life. These regions could be refuges where atmospheres mix, clouds form, and climates moderate. The study of tidally locked planets opens new frontiers in understanding planetary climates, atmospheric circulation, and the potential for habitability in environments far different from Earth's. This research is crucial as many exoplanets discovered in habitable zones around red dwarf stars, stars smaller and cooler than our Sun, are tidally locked due to their close orbits. All these lines of research, discoveries, and theories weave a rich and complex tapestry of the universe's capacity to host worlds and perhaps life in forms we have yet to conceive. They paint a picture of a cosmos alive with potential, waiting for humanity's curiosity and ingenuity to uncover its deepest secrets. However, planets that endure frigid conditions and icy terrains present an extraordinary stage for life's resilience and adaptation, where the challenges of extreme cold are met by nature's boundless ingenuity and evolutionary creativity. On such frozen worlds, life would encounter harsh realities: bitter temperatures plunging far below freezing, landscapes cloaked in sheets of ice stretching for miles, and an environment that defies the warmth and light many organisms on Earth rely upon. Yet, amid these seemingly inhospitable settings, life might not only survive, but thrive, exhibiting adaptations that are as fascinating as they are complex. Imagine organisms evolving to exist under a star that never sets, or one that never rises, a world locked in eternal day or endless night. In regions bathed in constant light, photosynthetic life forms could develop highly specialized sensitive mechanisms designed to capture and utilize every photon available, optimizing energy intake during unending daylight. Their biology might include pigments tuned finely to the star's specific light spectrum, or protective structures to prevent damage from prolonged exposure to intense radiation. Conversely, in perpetually dark zones, life might abandon photosynthesis entirely, relying instead on alternative biochemical processes to harvest energy. Chemosynthesis, a process where organisms extract energy from chemicals in their environment rather than light, could become the dominant mode of survival. Such life forms might exploit volcanic vents, frozen ocean floors, or subterranean chemical-rich reservoirs, harnessing the unseen energy flowing beneath the surface. The dynamic interaction between these extremes creates a compelling ecosystem where species could migrate between illuminated and shadowed regions. This migration might be driven by seasonal shifts, environmental changes, or life cycles intricately linked to the planet's unique light and dark cycles. Between these extremes lies the twilight zone, a narrow, delicate band where the fading light blends gradually into darkness. This transition zone may serve as a rich and diverse habitat, a refuge balancing the extremes of temperature and illumination. Life here might adapt in both physical and behavioral ways. Creatures dwelling on the hotter side could develop reflective surfaces to bounce away harmful sunlight, or adopt burrowing behaviors to escape the relentless heat of the surface. Meanwhile, organisms inhabiting the cold, dark regions might evolve exceptional thermal insulation, perhaps employing layers of fat, fur, or specialized cellular adaptations to conserve heat. Some might develop biochemical systems enabling survival through chemical energy extraction or bioluminescence to navigate and communicate in the perpetual darkness. Planets locked tidally in this manner offer a unique theater for evolutionary innovation. Their biospheres, while undoubtedly challenged by extremes of temperature and light, hold vast potential for diverse and resilient life. The possibilities extend beyond our terrestrial experience, suggesting ecosystems woven from the interplay of extremes, each organism an extraordinary product of adaptation and survival. Meanwhile, on a grander scale, the vast invisible structures known as dark matter halos envelop galaxies across the universe. These halos, immense in scale yet elusive to direct observation, are thought to comprise a significant portion of the universe's total mass. Though invisible, dark matter exerts a profound gravitational influence, holding galaxies together, shaping their rotation, and influencing their trajectories within the cosmic web. This unseen gravitational glue affects visible matter and, intriguingly, may host hidden celestial bodies within its depths. Within these dark matter halos, speculation and ongoing research ponder the existence of planets or stars hidden from our usual astronomical detection methods. Because dark matter interacts with ordinary matter primarily through gravity and not electromagnetic radiation, any planets or stars formed or captured within these halos could evade traditional observation, especially if they drift far from bright stellar clusters or galactic centers. The gravitational pull generated by dark matter could foster environments conducive to the accumulation of gas and dust, the essential ingredients for star and planet formation. Yet, these hidden celestial bodies would remain veiled, emitting little to no light and challenging astronomers to detect their presence indirectly through gravitational effects or disturbances in known systems. This prospect of unseen worlds within dark matter halos opens captivating possibilities about the universe's complexity and the realms of matter that remain beyond our current reach. It also highlights the still evolving understanding of dark matter itself, a frontier in astrophysics where each discovery pushes the boundaries of what we know about the cosmos, promising revelations about the formation, structure, and hidden corners of the universe. Extending this cosmic contemplation to the idea of advanced civilizations scattered throughout distant galaxies introduces a rich tapestry of potential life forms and cultures shaped by their unique planetary and stellar environments. Consider a civilization flourishing on a planet orbiting a stable star with Earth-like conditions, moderate temperatures, a reliable climate, and abundant liquid water. Such a society might develop technologies using materials and energy sources native to their world, possibly metals different from those familiar to us, or energy harnessed from resources unlike fossil fuels. Their architecture, transportation, and energy systems could be optimized for their environment, reflecting a deep integration with the natural resources available. In stark contrast, imagine life evolving in the thick, turbulent atmosphere of a gas giant. Instead of terrestrial ground dwellers, these beings might float or drift, adapting to life suspended in dense clouds. Their energy could come not from solar light, but from the powerful electrical storms raging through their skies. Rather than constructing buildings, they could build networks of buoyant structures, using atmospheric currents to navigate and interact with one another. Their society and technology would revolve around mastering and harnessing these environmental forces, leading to cultural values and scientific focuses that differ profoundly from human norms. Other advanced life might develop in environments marked by extremes, icy moons orbiting distant stars, or planets with intense volcanic activity. Such life could rely on bioluminescence for communication and navigation in dark or murky habitats, or employ thermophilic adaptations that allow survival in near-boiling conditions. Their technology might center on bioengineering and symbiosis with their surroundings, emphasizing sustainability and coexistence rather than exploitation. These creatures might harness the energy produced by their environment in novel ways, integrating biological and technological systems to thrive in habitats that would seem inhospitable by Earth standards. Communication across such civilizations could vary dramatically, using sound, light, or even chemical signals to create languages and social structures complex beyond human imagination. Social organizations might range from cooperative community groups to hive-like collectives, where individual roles are tightly integrated into a greater whole. These differences in communication and social interaction would fundamentally shape governance, innovation, and cultural development. Despite the vast divergence in physical forms, environments, and technologies, these civilizations might share universal drives: the pursuit of knowledge, the imperative of survival, and the search for connection with others. Their existence would echo the profound themes of life's resilience and creativity, embodied uniquely within their particular galactic context. On the grandest scale, certain cosmic phenomena stretch beyond our capacity for complete observation. The universe itself, vast and ancient, reveals only a fraction of its total extent through telescopes, limited by the speed of light and the universe's age. This observable portion is immense, but represents just a tiny window into what might be an infinite expanse. Galaxies span hundreds of thousands of light years, yet even these colossal structures can only be partially imaged, with many regions remaining shrouded in mystery. Moreover, galaxies often gather into clusters containing hundreds of members, sprawling across immense distances, further complicating our ability to grasp the full scale. The cosmic web, the large-scale architecture of the universe, weaves together galaxy filaments and clusters connected by enormous voids stretching across unimaginable expanses. The patterns formed in this web are so vast and complex that humanity can study only limited sections, with much of the grand design lying beyond current observational reach. This intricate cosmic tapestry reflects a universe of staggering scale and complexity, where each discovery reveals new layers of mystery and wonder, inviting continual exploration and deepening our appreciation of the cosmos we inhabit. Additionally, enormous cosmic structures, known as superclusters, rank among the grandest formations ever observed in the universe. These colossal assemblies consist of countless groups of galaxies bound together by gravity, sprawling across unimaginably vast expanses of space. The immense scale of superclusters presents formidable challenges for astronomers and astrophysicists alike, as capturing their entirety within a single observation remains nearly impossible with our current technology. Often, these superclusters combine or align in patterns that extend far beyond the limits of our most powerful telescopes and observational instruments, pushing the boundaries of what we can directly perceive in the cosmos. Despite the incredible advances humanity has made in our technology and scientific understanding, the universe's vast distances and the speed at which light travels impose natural constraints. Because light takes an immense amount of time to reach us from the farthest regions of space, what we observe is essentially a glimpse into the past, showing objects as they existed millions or even billions of years ago. This cosmic delay, combined with the sheer magnitude of structures like superclusters, means large portions of the universe remain tantalizingly out of reach, hidden beyond our observational horizon. Every glimpse we obtain, though invaluable, offers only a partial and fragmented picture, hinting at the overwhelming scale and complexity of the universe's grand architecture. Turning from these vast cosmic structures to one of the most enigmatic and profound mysteries in astrophysics, we find ourselves contemplating the nature of singularities, particularly those lurking at the cores of black holes. A singularity represents a point where gravitational forces become so intense that matter is compressed into an infinitely small space, resulting in a density that approaches infinity. It is within this extreme environment that the familiar laws of physics, as we understand them, begin to unravel. The conditions defy the known rules of physics, creating a paradoxical situation where the established frameworks of general relativity and quantum mechanics struggle to coexist or provide a coherent description. To visualize this, imagine space and time as a flexible fabric stretched across a vast framework. This fabric represents the continuum known as space-time, which is warped and curved by mass and energy. When a black hole forms, it dramatically distorts this fabric, creating a deep gravitational well that pulls inward with unimaginable strength. At the very bottom of this well lies the singularity, concealed from direct observation by a boundary called the event horizon. This horizon acts as a point of no return. Anything that crosses it, whether light or matter, becomes trapped forever, inaccessible to any outside observer. Because no information can escape once it passes this threshold, the singularity remains hidden, shrouded in profound mystery. Scientists around the world continue to explore various theoretical frameworks in hopes of shedding light on the nature of singularities. Some promising approaches attempt to unify the seemingly incompatible theories of gravity and quantum mechanics, aiming to develop a comprehensive theory of quantum gravity. Among these are string theory and loop quantum gravity, which propose different mathematical models and physical principles that might describe the behavior of matter and energy at these extreme scales. Despite these advancements, the intrinsic nature of singularities suggests that they may forever remain beyond direct observation. The extreme warping of space-time within them creates an environment where conventional concepts of space and time break down entirely, leaving us to rely on simulations and theoretical constructs to imagine what might occur at their cores. The idea that there could be regions in the universe where physical laws differ fundamentally from those we observe introduces an intriguing dimension to our understanding of reality. According to current scientific consensus, the laws of physics governing gravity, electromagnetism, and the behavior of subatomic particles hold consistent throughout the observable universe. However, some cosmological theories, especially those emerging from the study of string theory and inflationary cosmology, entertain the possibility of multiple universes existing beyond our own. This concept, often referred to as the multiverse, envisions a collection of separate universes, each potentially governed by its own unique set of physical laws and constants. In such scenarios, one universe might feature gravity that is stronger or weaker than in ours, or particles that behave in fundamentally different ways, resulting in alternate physical realities. These hypothetical universes could exist in dimensions beyond the 3 spatial and 1 temporal dimension we experience, making them undetectable with our current scientific instruments and methods. Some hypotheses even suggest that during the earliest moments after the Big Bang, fluctuations in energy might have caused different regions of our own universe to develop distinct physical characteristics. Yet, despite the theoretical appeal and mathematical modeling behind these ideas, no definitive experimental or observational evidence has been found to confirm the existence of alternative physical laws or separate universes within our cosmic horizon. Within our solar system, the study of comets has recently unveiled remarkable discoveries that challenge previous assumptions and deepen our appreciation for these icy wanderers. This past year, several unexpected observations have reshaped how scientists view comets and their dynamic behavior. One particularly striking example involved a comet exhibiting an unusual brightness, accompanied by a tail that defied typical expectations. Instead of the straight, narrow tail commonly seen, this comet's trail twisted and curved dramatically, Such a complex shape suggests intricate interactions with solar wind particles and cosmic radiation, revealing that the processes governing cometary material ejection are far more complicated than once believed. Another surprise arose when astronomers discovered a comet in a part of the sky where they had not anticipated finding one. This challenged long-held assumptions about the distribution and population of comets within our solar system, implying that many more such objects might be lurking undetected in the outer reaches or shadowed regions. The comet's orbit was also unusually elongated, a clue that provides insights into its origins and the gravitational influences it has experienced over time. Perhaps the most astonishing revelation came from a comet showing a coma, or atmosphere of gas and dust, significantly larger than what is typical for its size. The expansive coma suggests a higher level of geological activity, possibly driven by internal processes that release gas and dust more vigorously than in other comets. These findings have implications for planetary science, hinting at complex phenomena that could parallel those found on planetary bodies. Asteroids, traditionally viewed as inert rocky remnants from the formation of the solar system, have also surprised scientists with newfound behaviors. Some asteroids, classified as active asteroids, display characteristics previously thought to be exclusive to comets. When these bodies approach the sun, they exhibit comet-like features, such as developing tails or ejecting dust and gas. This activity implies the presence of volatile materials beneath their surfaces, which heat up and sublimate, transitioning directly from solid to gas as they are warmed by the sun's rays. These outgassing processes cause sudden changes in brightness and create visible tails or clouds of particles trailing the asteroid. Such behaviors reveal that internal dynamics of these small bodies can be surprisingly complex, involving physical and chemical processes that were not fully appreciated before. These discoveries underscore the endless surprises the universe holds. Every comet and asteroid can reveal new stories about the formation and evolution of our solar system, offering glimpses into the forces shaping planetary bodies and the dynamic environment through which they travel. As scientists continue to observe and analyze these celestial objects, our understanding will only deepen, revealing more of the cosmos's hidden secrets and expanding the boundaries of our knowledge. Additionally, advancements in observational technology have revolutionized our ability to study asteroids, unveiling behaviors previously beyond our imagination. Among the most surprising revelations is the discovery of asteroids spinning at rates much faster than scientists once deemed physically possible. These rapid rotations challenge traditional notions about the structural integrity and stability of these celestial bodies. The force of their swift spins can dramatically alter their shapes, transforming them from compact spheres into elongated or even wildly irregular forms. Centrifugal forces generated by these rotations redistribute mass within the asteroid, sometimes causing surface material to migrate or even be flung into space. This ongoing research not only enriches our comprehension of asteroid dynamics, but also compels scientists to rethink their role in the broader cosmic landscape of our solar system. Each new piece of data deepens our understanding of these space rocks as dynamic entities rather than static remnants of planetary formation, and highlights the complex interactions they may have with planets, including our own Earth. The year 2024 was marked by an extraordinary celestial event, the Perseid meteor shower, which captivated skywatchers worldwide with a dazzling spectacle. Occurring annually, the Perseids are the result of Earth traversing the trail of debris left behind by Comet Swift-Tuttle. As our planet follows its orbit around the Sun, it intersects this stream of tiny particles shed by the comet over centuries. These fragments, often no larger than grains of sand, enter Earth's atmosphere at tremendous speeds. The friction generated by their high-velocity entry causes the particles to ignite and burn, producing brilliant streaks of light across the night sky. Meteors. The Perseids are especially renowned for their intensity and the sheer number of meteors they generate, making them a favorite among astronomers and casual observers alike. In particular, many of these particles are larger than those found in other meteor showers, resulting in spectacular fireballs that can outshine even the brightest stars for brief moments. Favorable observing conditions in 2024 including a dark night sky with minimal light pollution and timing that coincided perfectly with the shower's peak, allowed countless stargazers around the globe to witness this magnificent display. This annual event serves as a vivid reminder of the constantly changing and dynamic nature of our universe, encouraging humanity to look up and marvel at the cosmic dance unfolding above. Asteroids scattered throughout the solar system have long intrigued scientists due to their ancient composition and their potential to unlock the mysteries of planetary formation. But beyond their role as remnants of the early solar system, some researchers entertain a more imaginative hypothesis. Asteroids could act as natural interstellar probes. Picture an asteroid ejected from the depths of a distant solar system, breaking free from its star's gravitational hold and embarking on a solitary journey through the vast expanse of space. These fragments of rock and metal, although devoid of human-made instruments, could carry invaluable information about their origins and the environments in which they formed. As they drift through interstellar space, such asteroids might encounter and interact with gas and dust from other star systems. Over millions of years, they could accumulate cosmic materials, essentially collecting samples from distant stellar neighborhoods. This natural sampling process offers a tantalizing glimpse into the molecular makeup of other star systems, providing clues about star and planet formation processes beyond our own cosmic neighborhood. Despite this captivating scenario, the actual likelihood of one of these interstellar asteroids making meaningful contact with our solar system remains extremely low. The distances between stars are incomprehensibly vast, and the probability of an asteroid wandering directly into our path is exceedingly slim. However, the discovery of Oumuamua, the first confirmed interstellar object detected passing through our solar system, has reignited interest and speculation about these mysterious visitors. Oumuamua's brief, enigmatic passage sparked intense debate about the nature and origins of such wanderers and their potential to carry untold stories from beyond our solar system. Were more of these objects to be found, they could be regarded as natural cosmic messengers, time capsules traveling through the dark fabric of space, bearing the histories of their distant home worlds. Meanwhile, in the field of exoplanet research, recent discoveries continue to challenge and expand our understanding of planetary atmospheres. Some of the most surprising findings come from planets known as hot Jupiters. These gas giants orbit their host stars at extremely close distances, where intense heat would normally strip away lighter atmospheric elements like hydrogen and helium. Yet, observations have revealed atmospheres on some of these planets containing unexpected elements such as iron and magnesium. This surprising composition suggests complex and perhaps previously unknown processes at play during the planet's formation or evolution, allowing it to retain materials under conditions once thought impossible. Another intriguing discovery involves super-Earths, planets larger than Earth but smaller than Neptune, which were expected to have thin atmospheres or rocky surfaces. Instead, some have been found to possess thick, steamy atmospheres rich in water vapor, suggesting that they may develop climates and weather patterns unlike anything found on Earth. These findings challenge preconceived notions about planetary atmospheres and hint at diverse evolutionary pathways. Moreover, researchers have detected signs of carbon-bearing molecules in the atmospheres of other distant planets, hinting at chemical reactions that may mirror those on Earth. This discovery opens new avenues in the search for life and complex chemistry beyond our solar system, raising the possibility that some exoplanets could harbor conditions conducive to life, or at least complex organic chemistry. Each new finding expands the vast and intricate tapestry of planetary diversity, compelling scientists to continuously refine theories about how planets form and evolve in the cosmos. In the realm of stellar phenomena, young stars often exhibit awe-inspiring jets of energy that extend across incredible distances in space, sometimes spanning several light years. These jets are formed during the tumultuous early stages of star formation, as a massive cloud of gas and dust, known as a stellar nebula, collapses under gravity. As the material condenses and spins, it forms a protostar surrounded by a rotating accretion disk composed of gas and dust. Matter from this disk gradually spirals inward towards the growing star, heating up tremendously due to friction and gravitational forces. This heating can reach temperatures so high that it powers the spectacular jets of energy and matter ejected from the star's poles, piercing through the surrounding nebula and influencing the star's environment for light years around. Such jets provide key insights into the processes that govern stellar birth and early evolution, revealing the interplay between gravity, rotation, magnetic fields, and radiation. Their dramatic appearance and immense scale serve as vivid reminders of the energetic and violent processes that shape stars, and by extension, the galaxies they inhabit. Through these phenomena, astronomers continue to peel back layers of cosmic mystery, unraveling the complex story of how stars, and ultimately planetary systems like our own, come to be. However, not all the material drawn toward a star actually makes its way into the star itself. Some of this matter is instead hurled outward at astonishing velocities, racing along the star's rotational axis to create the spectacular and highly energetic jets that astronomers have observed across the universe. These jets are primarily composed of charged particles and intense radiation, both driven by magnetic fields generated within the rapidly spinning, swirling gas surrounding the star. As this matter shoots out into space, it encounters and interacts with the surrounding interstellar medium, the sparse gas and dust that fill the vast expanses between stars. This interaction generates powerful shock waves, which can shine brightly across various wavelengths of light from visible to radio to X-rays, creating breathtaking cosmic light shows visible to instruments across the electromagnetic spectrum. The mechanism that drives these magnificent jets is deeply connected to the conservation of angular momentum, the natural tendency of a rotating object to maintain its spin. As the star spins faster, this angular momentum directs some of the infalling material into narrow, tightly focused streams. These cosmic jets, forged through a blend of physics involving rotation, magnetism, and gravity, become some of the universe's most awe-inspiring displays. Remarkably, these jets can persist long after the star has finished forming, continuously emitting energy and shaping their cosmic neighborhoods. Their powerful outflows stir the surrounding gas and dust, sometimes even compressing it to trigger the birth of new stars in nearby regions, creating a vibrant, interconnected cycle of stellar evolution. Observing these jets provides a vivid reminder of the universe's dynamic and ever-changing nature. Stars are not static entities. They live complex, dramatic lives that impact their surroundings profoundly. This ongoing cosmic dance shapes galaxies and influences the large-scale structure of the cosmos itself. Beyond the behavior of individual stars and their jets, the grander scale of celestial mechanics often surprises us. In the vast reaches of space, the motions of stars and planets sometimes defy simple predictions based on classical gravity alone. Galaxies spin in graceful, delicate spirals, and stars orbit within them, governed by the invisible pull of gravity. Yet astronomers have noticed instances where a star's trajectory deviates from what should be expected, or where a planet wobbles mysteriously in its orbit. Such anomalies have led scientists to propose the presence of unseen forces or objects influencing these celestial bodies. One of the most significant ideas that emerged from these observations is the existence of dark matter, an invisible form of mass that does not emit or absorb light, but makes up a large fraction of the universe's total mass. Though invisible to our telescopes, dark matter's gravitational influence subtly alters the motions of galaxies and clusters, causing deviations that hint at an invisible hand guiding these cosmic dancers. It is as if some unseen cosmic puppeteer is pushing and pulling, shaping the universe in ways we are only beginning to understand. Another fascinating aspect of this cosmic complexity comes from the study of exoplanets, planets that orbit stars outside our solar system. Many of these distant worlds exist in star systems with complex gravitational interactions that can lead to erratic orbital paths or dramatic atmospheric changes. For example, a planet may be partially displaced from its expected orbit due to the gravitational tug of a nearby star or a massive planetary neighbor. Such interactions illustrate the chaotic yet beautiful nature of cosmic evolution, where forces unseen and interactions complex create a universe filled with diversity and unexpected behavior. Adding further mystery, there are tantalizing hints of phenomena that remain beyond our full comprehension. These include the possible existence of massive, isolated celestial objects, such as rogue planets wandering through space alone or dense neutron stars whose immense gravity warps spacetime around them. These objects may exert gravitational influence or send ripples through the fabric of space and time without being easily detected by conventional means. As observational astronomy advances, it continues to refine our picture of the universe, compelling us to peer deeper into the night sky to find explanations for behaviors that gravity alone cannot fully account for. Each new discovery in this ongoing cosmic investigation has the potential to rewrite our understanding of how the universe functions. We are constantly prompted to reconsider the fundamental forces and mechanics that govern the cosmos, as new anomalies and phenomena challenge the boundaries of our knowledge. Traditionally, black holes have been thought of as voracious cosmic beasts, relentlessly consuming everything that ventures too close, matter and light alike, trapping it within their event horizons. However, recent research has revealed a more nuanced and surprising picture. Under certain extreme conditions, black holes, particularly the supermassive varieties found at the centers of galaxies, can actually expel matter back into space. These supermassive black holes are surrounded by accretion disks, vast swirling collections of gas, dust, and stellar debris that spiral inward, drawn inexorably toward the black hole's gravitational grip. As this matter accelerates and compresses, it heats up to extraordinary temperatures and builds tremendous pressure. Sometimes this buildup leads to explosive outflows of material. In specific cases, these outflows manifest as powerful jets that blast away from the black hole's poles at nearly the speed of light. Imagine a garden hose that, when twisted and kinked, suddenly releases a high-pressure stream of water with incredible force. In a similar manner, particles trapped in the intense magnetic fields near the black hole can be violently ejected, creating jets that extend across vast distances, sometimes spanning hundreds of thousands of light years, even outstretching the size of the host galaxy itself. These jets carry not only gas and dust, but also heavier elements forged near the black hole, dispersing them into the surrounding intergalactic medium. The impact of these jets on their environments is profound. They can regulate star formation by heating or dispersing the gas clouds from which stars are born, and they contribute to the evolution of the host galaxy's structure. The energy and matter ejected in these jets can reshape regions of space, influencing the cosmic ecosystem on scales both large and small. This ability of black holes to both consume and expel matter adds a remarkable complexity to their role in the universe. They are not mere cosmic vacuum cleaners, but active, dynamic players in the ongoing cycle of matter and energy that drives galactic and cosmic evolution. Galaxies themselves are grand, swirling assemblies of stars, gas, and dark matter, each rotating at incredible speeds and exhibiting a breathtaking diversity of shapes and sizes. These colossal structures form the cosmic tapestry that defines the large-scale architecture of the universe. As we continue to study the motion, formation, and interaction of these galaxies and their constituents, we deepen our understanding of the universe's past, present, and future. A universe filled with endless wonders, surprises, and mysteries waiting to be unraveled. However, there are moments when astronomers observe something truly unexpected. Certain galaxies, which one might anticipate to spin at consistent speeds, suddenly begin to slow their rotation. This surprising deceleration does not just puzzle scientists, but opens a window into the deeper, complex dynamics governing our universe. What drives this unusual slowdown is far from simple. Rather, it's a layered interplay of cosmic forces and phenomena that paint a picture as intricate and mysterious as the galaxies themselves. One of the primary reasons for this rotational braking involves the interactions between galaxies. Picture, if you will, two dancers on a grand cosmic stage. As they twirl and glide closer to each other, their movements inevitably influence one another's rhythm. In the vast expanse of space, galaxies behave much the same way. When two galaxies draw near, their mutual gravitational attraction acts like invisible threads pulling on each other. This force can be immensely powerful. Sometimes they collide, other times they merely pass by, but in both scenarios they exchange momentum and energy. This gravitational dance often leads to a redistribution of stars, gas, and dust within each galaxy. The outer regions of a galaxy, once spinning freely, can feel a tug akin to a cosmic drag that gradually saps their rotational speed. The result is a slower, altered rotation that tells a story of a recent encounter, a cosmic collision or a near miss, each leaving an indelible mark on the galaxy's motion. Yet gravitational interactions are just the beginning. Another key player in this cosmic slowdown is star formation itself. Inside a galaxy, enormous clouds of gas, primarily hydrogen, collapse under their own gravity, sparking the birth of new stars. This process is not merely a light show of twinkling orbs coming to life. It fundamentally changes how mass is distributed throughout the galaxy. When significant quantities of diffuse gas condense into dense stellar bodies, the overall mass distribution shifts. Dense stars, unlike diffuse gas, don't orbit as easily or as rapidly. This transformation reshapes the galaxy's internal structure, altering the delicate balance that once kept it spinning steadily. It is as if the galaxy's frame is remodeled from within, influencing its rotational dynamics in subtle but profound ways. Delving deeper, the enigmatic presence of dark matter weaves another thread into this tale. Though invisible to telescopes and undetectable by direct means, dark matter exerts a powerful gravitational force. This mysterious substance envelops galaxies in a vast halo, acting as a scaffolding that holds visible matter in place. When dark matter is redistributed, whether through interactions with other galaxies or internal dynamic shifts, the gravitational grip on the galaxy's stars and gas changes. If dark matter shifts outward or is somehow lost, the force keeping the galaxy spinning rapidly weakens, causing the rotation to slow. The silent influence of this unseen matter is pivotal, making it a cornerstone in understanding galactic behavior. Its elusive nature means much remains to be uncovered, but its impact is unmistakable. Furthermore, the environment in which a galaxy resides plays a critical role in its rotational fate. Galaxies often exist not in solitude, but within massive clusters, cosmic cities teeming with hundreds or thousands of galaxies. In these dense neighborhoods, gravitational forces from nearby galaxies exert continuous pressure, known as tidal interactions. Imagine a galaxy caught in a crowded dance floor, constantly jostled and pulled by its neighbors. This external gravitational tug can create additional drag, gradually slowing the galaxy's spin. The combined effects of these interactions within clusters showcase how a galaxy's surroundings influence its internal dynamics, further complicating the picture of rotational slowdown. The slowing rotation of a galaxy is, therefore, a multifaceted phenomenon. It arises from a combination of forces: the gravitational interplay during galactic encounters, the internal reshaping due to star formation, the critical but invisible hand of dark matter, and the broader environmental factors within galaxy clusters. This complex cosmic ballet reflects the ever-changing, evolving nature of the universe, reminding us that galaxies are not static objects, but living entities influenced by both internal and external forces. The universe itself can be seen as a grand tapestry, woven from threads of order and chaos. This cosmic fabric is shaped by forces both visible and hidden, forces that sculpt galaxies, stars, and clusters over billions of years. The chaotic influences shaping the cosmos are not abstract ideas, but tangible realities observable in countless ways. One striking illustration of cosmic chaos is found in the interactions between galaxies. When two galaxies draw close enough, their gravitational pulls can trigger dramatic, often violent cosmic events. These encounters frequently create tidal tails, vast streams of stars and gas stretched out like elongated arms into space. These distorted structures serve as visible evidence of the unpredictable gravitational dance between galaxies. The forces at play distort the very fabric of these enormous systems, illustrating how gravity can create both spectacular and chaotic effects on a colossal scale. Similarly, the birth of stars within galaxies showcases chaos on a smaller, yet equally fascinating, scale. Within dense clouds of gas and dust, turbulence roils and churns. These turbulent motions influence where and how material collapses to form stars. Some regions within the cloud become dense enough to trigger star formation, while others remain diffuse and inactive. This turbulent environment creates a patchwork effect, a cosmic quilt of newborn stars and stellar remnants, each following its own trajectory through the galaxy. The process is far from uniform or predictable, embodying chaos at a fundamental level of cosmic evolution. On an even grander scale, the structure of the universe itself reveals the imprint of chaotic forces. Dark energy and dark matter, invisible yet omnipresent, tug and pull at the very fabric of space. These forces drive the formation of the cosmic web, a vast network of filaments, clusters, and voids that stretches across billions of light years. This web is not orderly or symmetrical. It emerges from the complex, chaotic interactions of matter and energy on a universal scale. Over eons, these interactions have shaped the distribution of galaxies, guiding their clustering and the formation of massive structures. The cosmic web stands as a testament to the intricate and unpredictable forces at work in the universe. These examples of chaotic forces are not just theoretical concepts, they are observable phenomena that continue to fascinate astronomers and astrophysicists. From the majestic collisions of galaxies to the delicate birth of stars and the colossal patterns of cosmic structures, the universe constantly reveals its unpredictable and dynamic nature. This interplay of order and chaos drives the ongoing evolution of the cosmos, pushing our understanding forward while reminding us of the vast mysteries that remain. In this vast and ever-changing cosmic landscape, spontaneous and massive phenomena often arise when conditions align perfectly. Consider, for instance, the formation of enormous clouds of gas and dust, commonly known as nebulae. These nebulae are born as gravity draws together vast amounts of material from the surrounding space. Over time, as the density of gas and dust within these clouds increases, a tipping point is reached. At this critical density, a chain reaction can ignite. The collapse of gas under gravity leads to the birth of new stars, marking a rebirth in the galaxy's life cycle. These nebulae and their star-forming processes highlight the universe's ability to generate grand and sudden transformations, reminding us of the dynamic forces at play in the depths of space. Thus, the universe's intricate dance, shaped by gravity, star formation, dark matter, and chaotic forces, continues to unfold. Each galaxy, star, and cosmic structure tells a story of interactions, transformations, and evolution. Through detailed observations and ongoing research, humanity gradually uncovers the complex mechanisms that govern the cosmos, deepening our appreciation for the universe's beauty and mystery. The slowdown of galaxy rotation is but one chapter in this vast narrative, inviting us to explore the boundless forces shaping the cosmos around us. Furthermore, celestial phenomena often unfold in ways that challenge our perceptions of the universe's stability, revealing the extraordinary and sometimes sudden transformations that define cosmic evolution. One such phenomenon is the spectacular event known as a supernova, which marks the explosive death of a massive star. This event occurs when a star, having exhausted its nuclear fuel, loses the ability to support itself against the relentless pull of gravity. What follows is a rapid collapse of the star's core, a process that, though swift on a cosmic timescale, unleashes a tremendous explosion powerful enough to scatter elements throughout interstellar space. These expelled materials, forged deep within the star's core, travel across the void to seed the formation of new stars, planets, and potentially the very building blocks of life itself. The death of a star, thus, becomes the genesis of future celestial bodies, underscoring a cosmic cycle of destruction and creation that continuously reshapes the fabric of the universe. Adding to the awe-inspiring complexity of stellar life cycles is the sudden appearance of pulsars, objects that emerge seemingly out of nowhere after certain supernovae. These highly magnetized, rapidly spinning neutron stars emit beams of electromagnetic radiation, sweeping across the cosmos like lighthouse beacons. When conditions align perfectly during the collapse of a star, the remnant core can become a neutron star so dense that it defies ordinary matter's properties, compressing a mass greater than that of our sun into a sphere barely the size of a city. This transformation can occur almost instantaneously in cosmic terms, producing bursts of energy intense enough to be detected across millions of light years. Pulsars not only illuminate the night sky with their rhythmic flashes, but also serve as laboratories for studying matter under extreme conditions, helping scientists probe the limits of physics. Even more speculative and captivating are theories about the spontaneous formation of black holes, suggesting these mysterious entities might not only arise from the deaths of massive stars, but could also originate from dense pockets of matter collapsing under their own gravity in unexpected ways. Though largely theoretical and still under rigorous investigation, these ideas highlight the universe's intrinsic tendency toward surprise, with gravitational forces orchestrating the birth of new cosmic structures from regions once thought stable. The dynamic and evolving nature of space reveals that what appears fixed and unchanging can in fact shift rapidly, giving rise to phenomena of monumental scale that challenge our understanding and invite deeper exploration. The year 2024 witnessed extraordinary moments that transformed the scientific community's grasp of the cosmos, sparking widespread excitement and curiosity. Among these breakthroughs was the discovery of a new exoplanet situated within the habitable zone of its star, a region where temperatures could allow liquid water to persist, a critical ingredient for life as we know it. The detection of water vapor in this planet's atmosphere sent ripples through the global research community, fueling imaginations and intense discussions about the prospects for extraterrestrial life. This find represented not only a milestone in exoplanetary science, but also a beacon of hope in the ongoing quest to find life beyond Earth. Simultaneously, deep space observations uncovered unusual cosmic signals that defied previous understanding. These enigmatic emissions led astronomers to speculate about novel astrophysical processes, potentially rewriting the textbooks on phenomena like supernova explosions and black hole formation. The intrigue was not limited to the phenomena themselves, but extended to the profound implications these findings held for fundamental physics and our broader comprehension of the universe's evolution. In parallel, advances in particle physics brought to light experimental results suggesting the existence of an elusive particle that might carry a form of dark matter. This revelation was especially momentous, considering that dark matter is believed to constitute the vast majority of the universe's mass, yet its true nature remains one of the greatest mysteries in modern science. The prospect of finally unraveling the secrets of dark matter energized the scientific community, prompting collaborations and new initiatives aimed at deciphering its role in shaping cosmic structures. The cascade of discoveries ignited a flurry of reactions among researchers worldwide. Excitement and a sense of urgency permeated conferences and academic gatherings as the community pivoted toward exploring these novel insights. Discussions centered on the thrilling unknowns and the possibility of fundamentally altering long-standing theories, uniting scientists across disciplines in a shared pursuit of knowledge. The year became a landmark chapter in humanity's ongoing effort to peer deeper into the universe, to understand its origins, dynamics, and the forces that govern it. These developments highlighted the interplay of curiosity, persistence, and innovation that drives scientific progress. Among the significant findings was the detection of unusual gravitational waves, ripples in the fabric of space and time generated by massive cosmic events such as colliding black holes or neutron stars. The characteristics of these waves contained unexpected signatures, indicating new interactions or properties of celestial bodies that current models had yet to predict. This revelation hinted at undiscovered physics and opened new avenues for understanding the universe's most extreme environments. In addition, astronomers analyzing images from powerful telescopes noted anomalies in the rotational behavior of distant galaxies. Some galaxies were observed to spin in ways that defied existing models of dark matter's influence, challenging the assumption that dark matter governs galactic rotation in specific predictable patterns. These observations suggested either the presence of previously unknown forces or the need to reconsider the fundamental nature of dark matter itself. This unexpected twist in cosmic dynamics underscored the fluidity of scientific knowledge and the ongoing need for exploration and reevaluation. The dynamic nature of these discoveries encapsulates the essence of cosmic study, a relentless journey through the unknown, where each revelation broadens the horizon of what is possible. From the death throes of stars to the mysterious signals from the farthest reaches of space, the universe reveals itself as a place of constant transformation and infinite complexity, inviting us to continually deepen our understanding of the cosmos and our place within it. Furthermore, the exploration of extreme environments, particularly those found in the vast and seemingly endless stretches of deep space, has revealed an astonishing array of unexpected chemical compounds and reactions. These discoveries have fundamentally challenged long-held theories about how such materials form and evolve over time. Scientists once believed they had a solid grasp on the processes governing the birth and development of cosmic substances, but recent findings demand a reevaluation. These new chemical signatures and interactions suggest that the pathways through which cosmic materials come into existence are far more intricate and dynamic than previously imagined. These groundbreaking revelations have the potential to revolutionize our understanding of star formation and the broader life cycle of cosmic materials. The classical models that describe the gradual accumulation and transformation of matter within stellar nurseries now appear incomplete. Instead, the universe seems to engage in a far more complex chemical dance, involving interactions under conditions that were once considered inhospitable to such processes. The presence of exotic compounds in regions with extreme radiation, intense gravitational forces, or near absolute zero temperatures indicates that the cosmos operates on principles that continually evolve as our instruments and knowledge deepen. Together, these discoveries underscore a fundamental truth about our relationship with the cosmos. Our understanding is always provisional, subject to change as new evidence emerges. Every new observation, every piece of data collected from the farthest reaches of space serves not only to deepen our knowledge, but also to remind us of the profound complexity and mystery that characterize the universe around us. This ongoing expansion of understanding urges scientists and thinkers worldwide to remain open to fresh ideas and alternative explanations, fostering an environment where curiosity and skepticism coexist in the pursuit of truth. The quest to comprehend the cosmos is far from complete, and the universe, vast beyond imagination, likely holds many more surprises yet to be uncovered. With so much space still unexplored, the possibility of discovering entirely new categories of celestial objects is not just a dream, but a tangible prospect. Researchers continuously push the boundaries of current scientific understanding, often overturning previous classifications and encountering phenomena that defy existing knowledge. Such discoveries highlight the dynamic, evolving nature of cosmic exploration and remind us that our view of the universe remains only partially illuminated. Consider the early observations of pulsars, celestial objects that first perplexed astronomers by emitting regular pulses of radio waves. Initially, these signals were speculated to be attempts at communication from extraterrestrial civilizations, capturing the imagination of both scientists and the public. However, further study revealed that pulsars are rapidly rotating neutron stars possessing extraordinary properties, such as intense magnetic fields and precise rotational periods. This transformation in understanding, from mysterious signals to well-characterized stellar remnants, illustrates the evolving nature of astronomical discovery. Today, advancements in telescope technology and observational techniques are propelling our ability to explore the cosmos to unprecedented depths. These improvements enable us to detect faint objects that were once invisible to previous generations of astronomers. As a result, we are now on the verge of identifying unusual celestial bodies that fall outside existing categories, including objects that challenge our conventional understanding of planetary systems, star clusters, and galaxies. It is entirely plausible that we will encounter exotic planetary systems with configurations unlike anything we have yet imagined, or phenomena arising from novel physical processes that are still poorly understood. Theoretical physics further enriches this landscape of potential discovery. Concepts such as dark matter and dark energy hint at aspects of the universe that remain shrouded in mystery. Dark matter, thought to make up a significant portion of the universe's mass, interacts with visible matter primarily through gravity, acting like an invisible scaffold that shapes the structure and behavior of galaxies. Despite its crucial role, it has never been directly observed, leaving scientists to speculate about its true nature and origin. Similarly, dark energy is believed to drive the accelerated expansion of the universe, yet its characteristics and mechanisms remain elusive. The possibility of discovering an entirely new category of celestial objects might depend on breakthroughs in our understanding of these enigmatic components. As our knowledge of dark matter, dark energy, and other cosmic mysteries expands, so too does the potential for encountering objects and phenomena that defy all previous classifications. Every new expedition to distant worlds, every advance in computational astrophysics, brings with it the promise of surprising findings that could reshape our cosmic worldview. Just as the study of comets and asteroids once expanded our perception of the solar system, future discoveries may redefine how we categorize and comprehend celestial entities. With each new telescope launched into orbit, equipped with cutting-edge sensors and designed to observe the universe across a range of wavelengths, we move closer to uncovering the hidden secrets of the cosmos. Each space mission that ventures further into the unknown extends our reach into regions of space that were once inaccessible. These combined efforts gradually peel back the layers of mystery enveloping the universe, offering glimpses into potential new celestial categories that could reshape the foundations of astronomy and cosmology. Throughout the history of space exploration, scientists have repeatedly encountered phenomena that challenge existing paradigms, inspiring bold and fascinating theories. One of the most captivating among these is the concept of dark matter. Although invisible to direct observation, the gravitational effects of dark matter are clearly visible in the motion of galaxies and galaxy clusters. This unseen mass appears to influence the structure and dynamics of the universe at the largest scales, prompting ongoing efforts to detect and understand it. The elusive nature of dark matter has sparked numerous hypotheses, some proposing exotic particles or new fundamental forces yet to be discovered. Another theory that stretches the boundaries of our imagination involves the existence of parallel universes. Some physicists suggest that what we perceive as our universe might be just one among countless others, each governed by different physical laws, constants, or even timelines. The implications of such a multiverse are profound, raising questions about the nature of reality, identity, and existence itself. What if infinite versions of ourselves exist, living out alternate destinies in these parallel realms? The idea opens a realm of philosophical and scientific inquiry that challenges the limits of human understanding. Additionally, scientists are intrigued by the phenomenon of fast radio bursts, brief, intense pulses of radio waves originating from distant regions of space. Since their discovery, these fleeting signals have puzzled astronomers, sparking diverse hypotheses. Some speculate they could be artificial signals from advanced extraterrestrial civilizations, while others propose natural origins, such as the collision of neutron stars or emissions from magnetars, which are highly magnetized and dense remnants of collapsed stars. Despite ongoing research, the true cause of fast radio bursts remains one of the most compelling mysteries in modern astrophysics. Finally, there is the enigma of cosmic inflation, a theory positing that the universe underwent an extraordinary exponential expansion within an unimaginably brief period shortly after the Big Bang. This rapid growth phase helps explain the large-scale uniformity observed across the cosmos today. Yet the mechanisms that triggered cosmic inflation and its integration with other aspects of the universe's evolution remain subjects of intense study and debate. Understanding cosmic inflation is critical to piecing together the earliest moments of our universe's history, offering clues to its ultimate fate and the fundamental laws governing reality. As humanity continues its relentless pursuit of cosmic knowledge, each discovery, each new mystery encountered, expands the horizons of what is possible. The universe, vast, mysterious, and continually evolving, remains a frontier that beckons us forward, promising wonders beyond imagination and challenging our most deeply held assumptions. The journey to unravel its secrets is ongoing, and with every step, we come closer to understanding the profound and beautiful complexity of the cosmos we call home. Rent models of physics remain an enduring puzzle, a formidable challenge that continues to captivate scientists and thinkers alike. These theoretical frameworks are more than mere mathematical exercises. They embody the very essence of scientific inquiry, an intellectual odyssey that propels humanity beyond the familiar and into the realms of the unknown. Each breakthrough, each discovery is not an end but a new beginning, a portal that opens onto an ever-expanding landscape of questions, enigmas, and mysteries. The pursuit of knowledge, far from stagnating, becomes a vibrant and exhilarating journey that keeps the human spirit inquisitive and vibrant. Within this grand tapestry of cosmic exploration, the notion of Dyson spheres emerges as one of the most intriguing and visionary concepts ever conceived. Originally proposed by the visionary physicist Freeman Dyson, these hypothetical megastructures represent an extraordinary solution for civilizations that have reached levels of technological advancement far surpassing our own. Imagine a colossal shell or a swarm of satellites encompassing an entire star, designed to capture the immense energy radiating from it. This is no small feat of imagination. It is a conceptual leap that forces us to rethink the limits of engineering, energy consumption, and cosmic ambition. Though no Dyson spheres have yet been discovered in our universe, the idea is not relegated to the realm of mere science fiction. Rather, it serves as a profound catalyst for scientific speculation and cosmic curiosity. It poses fundamental questions about the existence of extraterrestrial intelligence, the potential for monumental engineering projects on a galactic scale, and the very nature of energy consumption by advanced beings. To construct such a structure would require capabilities that dwarf anything humanity currently possesses. It would entail the ability to transport and assemble gargantuan quantities of material in space, perhaps even dismantling entire planets or mining vast asteroid belts to provide the necessary resources. The challenges of verifying the existence of Dyson spheres are as daunting as their construction would be. If a star were encapsulated by such a structure, the light it emits would be altered in very specific ways. Scientists searching the heavens scan the cosmos with increasingly sophisticated telescopes, looking for anomalies, irregular light patterns, or unexpected surges of infrared radiation that cannot be explained by natural phenomena. Infrared emissions are of particular interest because a Dyson sphere would absorb a star's visible light and re-emit energy as heat. Detecting these unusual signatures is like searching for a needle in a cosmic haystack. The enormity of our galaxy, with its hundreds of billions of stars, further complicates this search. The probability of directly observing such a megastructure is exceedingly small, yet the pursuit is far from futile. Instead, it inspires new lines of inquiry and technological advancement in astronomy and astrophysics. The concept of Dyson swarms, collections of satellites orbiting a star instead of a solid shell, has gained traction as a more plausible configuration. These dispersed arrays could capture stellar energy while avoiding the enormous engineering difficulties of constructing a rigid sphere. Despite remaining theoretical, the implications of Dyson spheres or their equivalents are profound. They invite us to imagine the future trajectory of human civilization and to speculate on the capabilities of intelligent life forms scattered across the cosmos. Whether we ever find direct evidence of these megastructures, contemplating their existence expands our understanding of what might be achievable, not just by distant civilizations, but potentially by humanity itself, as we reach outward into space. The discovery of such an alien megastructure would be nothing short of revolutionary. It would offer tangible proof of advanced extraterrestrial civilizations, a cosmic signpost marking the progress of intelligence far beyond our own. One of the most compelling indicators would be irregularities in the brightness of distant stars. Imagine observing a star whose light dims unpredictably in ways that cannot be accounted for by the usual suspects, such as planetary transits or cosmic dust clouds. This irregular dimming could hint at the presence of an immense artificial structure capturing the star's energy. Another critical sign might come in the form of excess infrared radiation. While stars naturally emit a spectrum of light and heat, an unusual surplus of infrared emissions could suggest the presence of engineered constructs harvesting and re-radiating stellar energy. Detecting such signals would require meticulous observation and interpretation, distinguishing between natural astrophysical processes and potential artifacts of alien engineering. Moreover, the presence of these megastructures might manifest in gravitational anomalies. The immense mass of a Dyson sphere or swarm could influence the orbits and motions of nearby celestial bodies in subtle yet detectable ways. Physicists and astronomers tracking the movement of stars, planets, and asteroids might notice deviations from expected trajectories, pointing toward an unseen massive structure exerting gravitational influence. These anomalies would act as a cosmic fingerprint, a silent yet compelling testimony to the existence of extraordinary engineering projects conducted by intelligent beings. Such discoveries would not only expand our understanding of the cosmos, but would also profoundly alter our perception of humanity's place within it. The knowledge that other civilizations possess the capability to manipulate their environments on such a colossal scale would redefine our aspirations and our understanding of technological progress. It would underscore the vast potential that intelligent life has to transform not only their immediate surroundings, but entire star systems. This quest to detect and understand Dyson spheres and related megastructures is part of a broader scientific endeavor to comprehend the universe's complexity and the diversity of life it may harbor. It embodies the relentless human drive to explore, to question, and to push beyond the boundaries of current knowledge. Even in the absence of direct evidence, the theoretical exploration of these concepts enriches our scientific imagination and inspires new generations of researchers, engineers, and dreamers. As we gaze into the depths of the galaxy, the faint glimmers of stars may conceal wonders we have yet to comprehend. The search for Dyson spheres represents a beacon of hope and curiosity, a testament to the power of human intellect to envision realities beyond our immediate reach. It challenges us to consider not only the technical challenges of constructing such megastructures, but also the philosophical and existential implications of encountering other advanced civilizations. In the vast, silent expanse of space, where stars burn with the energy of billions of years, the notion of capturing and harnessing that power speaks to a future where intelligence and technology converge on an unprecedented scale. Whether or not we ultimately find evidence of Dyson spheres, the very act of imagining them enriches our understanding of the cosmos and our place within it, urging us onward in the eternal quest to unravel the mysteries of the universe. Lastly, should humanity ever detect signals or communications that exhibit distinct structure and clear purpose, it would mark one of the most profound discoveries in the history of science. Such a finding would point directly to the existence of intelligent life behind these signals. Whether these communications are electromagnetic in nature or involve modifications of light emitted by distant stars, their presence would serve as compelling evidence of an advanced civilization operating somewhere in the vast cosmos. As we continue to scan the universe, every observation demands meticulous analysis and deep scrutiny. The universe is overwhelmingly immense, its scale and complexity staggering beyond everyday comprehension. While the idea of alien megastructures remains in the realm of speculation, the possibility itself opens doors to extraordinary truths about our position and significance in the grand cosmic scheme. Observations of stars exhibiting unusual light patterns often intrigue astronomers and stir the imagination about potential artificial interference. One of the most renowned examples is the star known as KIC 8764. It captured scientific attention because it displayed strange and irregular dimming behavior that puzzled astronomers and led some to hypothesize the presence of a colossal structure orbiting it. This speculative structure, sometimes imagined as a Dyson sphere or another kind of megastructure, could theoretically be the handiwork of an extraterrestrial intelligence engineering and advanced construct. The key piece of evidence supporting this hypothesis was the detection of periodic dips in the star's brightness that defied the usual predictable patterns created by planets orbiting stars. However, as investigations deepened, most of these intriguing phenomena were found to have natural explanations. For instance, variations in starlight can result from a star's own pulsations, rhythmic expansions and contractions that cause changes in brightness. Other causes might include clouds of orbiting debris, such as asteroids or cometary fragments, which temporarily obscure the star's light. Additionally, the gravitational pull of a nearby stellar companion might cause shadows or eclipses, creating unusual light patterns. Such natural cosmic occurrences can often closely mimic the light signals we might expect from artificial sources crafted by intelligent beings. Astronomers use rigorous methods and advanced technologies to analyze these light patterns, primarily employing spectroscopy. This technique breaks down the star's light into its component wavelengths, revealing detailed information about the star's composition, temperature, movement, and behavior. By studying brightness variations across different wavelengths, researchers search for signatures that could hint at a non-natural origin. Although some of these light patterns spark fascinating theories about artificial structures, the scientific consensus remains that most are best explained by the dynamic and often chaotic processes inherent to the universe itself. Despite this, the ongoing search for extraterrestrial intelligence inspires deep curiosity and fuels relentless scientific inquiry. It drives advances in both technology and our understanding of the cosmos, continually pushing the boundaries of what we know. Beyond searching for signals or artificial light patterns, the concept of advanced civilizations harvesting energy from black holes captivates both scientists and enthusiasts of science fiction alike. One intriguing theoretical method involves the exploitation of a process called Hawking radiation, named after the renowned physicist Stephen Hawking. According to this concept, black holes can emit tiny amounts of thermal radiation as a result of quantum mechanical effects occurring near the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. In simpler terms, pairs of particles and antiparticles spontaneously emerge from the vacuum of space near this boundary. Occasionally, one particle falls into the black hole while its counterpart escapes into space. The escaping particle carries away energy, which effectively causes the black hole to lose mass over extremely long timescales. In theory, an immensely advanced civilization might engineer a structure capable of harnessing this escaping Hawking radiation. Imagine a gigantic apparatus built around a black hole, designed specifically to capture this elusive energy as it radiates away. Realizing such a feat would require technologies far beyond what humanity currently possesses, especially considering the extreme gravitational forces, intense radiation, and violent environment surrounding black holes. Another captivating idea involves capturing energy from the accretion disk, a swirling disk of gas and dust that spirals inward toward the black hole. As matter accelerates and compresses in this rotating disk, it heats to extraordinarily high temperatures. The immense gravitational and frictional forces generate tremendous energy output, some of which, in principle, could be converted into usable power. Civilizations with sufficiently advanced engineering capabilities might develop methods to extract this energy efficiently, analogous to how humans generate electricity from thermal power plants on Earth. However, these notions remain deeply speculative, constrained by numerous uncertainties. The materials needed, the energy demands of constructing such technology, and the formidable challenges posed by the black hole's environment all contribute to the difficulty of these concepts becoming reality. Yet, even as theoretical discussions, they ignite the imagination and motivate scientific investigation into extreme astrophysical phenomena. To confirm the existence of any alien-built structures, scientists rely on a comprehensive approach combining observation, analysis, and critical reasoning. The first step typically involves scanning the skies with powerful telescopes and advanced sensing instruments, searching for unusual signals or patterns that cannot be explained by natural phenomena. Such signals might appear as unexpected bursts of light or radiation, or as physical structures displaying geometric shapes and regularities that strongly suggest artificial construction rather than natural formation. Upon detecting a candidate signal or structure, a more detailed and thorough investigation is undertaken. Scientists analyze the object's composition, energy output, and behavior over time. If the structure exhibits consistent and unusual emissions, such as strong radio waves or laser-like signals, it draws intense interest. The next crucial step is to rule out natural explanations like meteor showers, cosmic dust clouds, or stellar phenomena that might mimic these signals. To do this, researchers gather additional data from multiple instruments, cross-referencing and verifying observations to eliminate false positives. This painstaking process exemplifies the scientific method at work in the search for extraterrestrial intelligence. It demands patience, precision, and skepticism, but the potential payoff is profound. Discovering definitive proof of intelligent life beyond Earth would forever transform our understanding of the universe and our place within it. Until that moment arrives, the quest to find signals that stand out amidst the cosmic noise continues unabated, driven by humanity's insatiable curiosity and hope. Furthermore, collaborations between international space agencies and observatories have become increasingly vital in constructing a robust framework for scientific validation. These partnerships allow for the pooling of resources, expertise, and data, creating a multi-layered approach to exploring the cosmos. Scientists engage deeply with archival data, meticulously analyzing it to search for signals or structural patterns that resemble previously observed phenomena. This thorough examination helps establish whether a detected occurrence is an isolated event or part of an ongoing, repetitive pattern. For example, when ground-based instruments detect an unusual signal or structural anomaly, these observations can serve as a catalyst for more targeted exploration missions, designed specifically to investigate the origin and nature of the phenomenon in question. Such missions often involve sending robotic probes equipped with a suite of advanced instruments, including high-resolution cameras, spectrometers, and other sensors capable of capturing live data from distant celestial bodies. These robotic explorers gather not only images, but also physical samples when possible, enabling direct study of surface materials. This form of investigation vastly expands our understanding by allowing scientists to look for materials or artifacts that may suggest artificial design or construction. The search for these indicators demands rigorous scientific scrutiny at every stage, from the initial observation to the complex data analysis and ultimately to the physical exploration. Each phase is subjected to intense peer review and a commitment to scientific skepticism. This ensures that any proposed identification of alien-built structures is backed by credible, reliable evidence rather than misinterpretations of natural phenomena. The quest to find extraterrestrial intelligence merges humanity's deep curiosity about the cosmos with a methodological dedication to scientific rigor. Discovering an alien-built structure would not only captivate the public imagination, but also represent a monumental milestone in our understanding of the universe and our place within it. As we advance through the year 2024, the technological landscape that supports this search is rapidly evolving, bringing with it an impressive suite of new tools and capabilities designed to deepen our cosmic insights. Among the most remarkable innovations are the next generation of space telescopes. These instruments boast highly sensitive technologies and finely tuned optics that enable astronomers to capture details of distant celestial bodies with clarity previously unattainable. The advanced imaging techniques employed by these telescopes allow them to observe faint light emitted by astronomical phenomena located many light years away. This capability effectively opens a window to the early universe, allowing scientists to peer back in time to study the origins of stars, galaxies, and potentially habitable exoplanets. The discovery of such planets, lying in the so-called habitable zones of their stars, could revolutionize our understanding of life's potential beyond Earth. Alongside the leaps made in telescope technology, artificial intelligence has started to play an indispensable role in modern astrophysics. Sophisticated algorithms now comb through enormous datasets generated by space observatories, detecting subtle patterns and correlations that might escape even the most trained human eye. This powerful synergy between human intuition and machine learning accelerates the pace at which complex cosmic events are deciphered, shedding light on phenomena such as supernova explosions, black hole mergers, and galaxy formations. The computational power of AI allows researchers to model these events in unprecedented detail, offering new insights into the dynamics of the universe. In addition to observational advances, propulsion technology has seen significant progress, particularly in the realm of robotic space exploration. Emerging propulsion systems promise to drastically reduce travel times for missions within our solar system, making previously distant locations more accessible. This technological progress hints at a future where detailed exploration of celestial bodies, such as the icy moons of Jupiter, including Europa and Ganymede, or the dusty plains of Mars, could become routine. These advancements might enable more frequent robotic missions, equipped to analyze surface chemistry, geology, and even potential biosignatures. Furthermore, the deployment of small satellite constellations has greatly expanded our ability to monitor space weather and detect potential hazards, such as asteroids and cosmic radiation. These networks of miniature satellites operate collaboratively, providing continuous, real-time data streams. This comprehensive monitoring system enhances our ability to predict, respond to, and mitigate risks posed by space phenomena, which could threaten both Earth and ongoing space missions. Complementing these technological developments is the increasing spirit of international cooperation among space agencies worldwide. By sharing data, research, and technological resources, these agencies harness their collective expertise to tackle fundamental cosmic questions. This collaborative approach maximizes the efficiency of scientific inquiry and fuels a unified pursuit to understand the origins of the universe, the nature of dark matter and dark energy, and the prospects for life beyond our planet. Such partnerships ensure that humanity's exploration of space is a global endeavor, grounded in the principles of openness, shared knowledge, and mutual respect. All of these technologies and initiatives come together to paint an exciting and hopeful picture of the future of cosmic exploration. As scientists continue to piece together the vast and intricate puzzle that is the universe, every advancement brings us closer to unlocking the mysteries of space and expanding our cosmic horizon. One of the most transformative tools in recent years has been the James Webb Space Telescope, often referred to as JWST. Since its launch, JWS has revolutionized astronomy by providing unprecedented observations of the distant universe. With its advanced infrared technology, the telescope can penetrate thick cosmic dust clouds that obscure many objects from view in visible light. This capability allows astronomers to observe the birth of stars and the formation of galaxies in exceptional detail, offering a glimpse into processes that shaped the cosmos billions of years ago. JWST's observations have led to several unexpected discoveries, challenging long-standing theories about cosmic evolution. For instance, it has identified galaxies that appear to have formed much earlier than scientists previously believed possible. These galaxies, detected at epochs shortly after the Big Bang, raise profound questions about how stars and galaxies could have developed so rapidly in the young universe. Such findings suggest that current models of cosmic evolution may require significant revisions to accommodate these early formations, potentially rewriting the narrative of how the universe grew and matured over time. Through this continual cycle of observation, hypothesis, and discovery, instruments like JWST and the collaborative efforts of scientists worldwide are driving the frontier of knowledge further into the cosmos. As the tapestry of the universe becomes ever more detailed and complex, humanity stands on the brink of transformative discoveries that may forever alter our understanding of existence itself. Additionally, the James Webb Space Telescope has achieved remarkable feats by detecting light emitted or reflected from planets beyond our solar system, known as exoplanets. This light reveals components in their atmospheres that were previously invisible to us, including water vapor and a variety of other gases. Such discoveries do more than merely hint at the possibility that these distant worlds might support life. They reveal an astonishing variety of environmental conditions that exist on planets far removed from our own. These findings push the boundaries of human knowledge by suggesting that planets with Earth-like qualities could manifest in many different ways, far beyond what we once imagined when thinking about the nature of worlds orbiting other stars. Moreover, the telescope's unparalleled ability to capture detailed spectra, essentially the fingerprints of light that allow scientists to decode chemical compositions, has transformed our understanding of distant celestial objects. This capability enables researchers not only to confirm the presence of elements familiar to us, such as oxygen, carbon, and hydrogen, but also to uncover unexpected chemical reactions and processes occurring in remote and exotic corners of the universe. Through this spectral analysis, the James Webb Space Telescope opens new frontiers in astronomy by unraveling long-standing mysteries that have puzzled scientists for decades, while simultaneously presenting a host of surprises that challenge and expand our prior assumptions about how the cosmos operates. Each observation made by the telescope adds another intricate layer to the vast and complex tapestry that is our universe. These layers remind us of the immense scale of the unknown, highlighting how much more there is to learn. At this moment in history, we find ourselves at a particularly fascinating juncture in our quest to comprehend the universe. Thanks to cutting-edge technology, we can now peer into regions of space that were once completely hidden from view. One of the most groundbreaking advances has been the development of sophisticated telescopes and observation techniques capable of detecting light from incredibly distant and faint objects. For most of humanity's history in astronomy, vast portions of the universe remained shrouded in darkness, obscured either because of the vast distances light had to travel or because earlier instruments were simply unable to capture certain wavelengths of light. However, today's modern telescopes, designed to observe across a wide range of the electromagnetic spectrum, including infrared and radio wavelengths, have the power to penetrate these hidden cosmic regions. This enhanced observational ability allows scientists to look back in time, past the dense clouds of cosmic dust that once blocked their view, and witness the formation of stars, galaxies, and even entire clusters during the universe's earliest epochs. For example, the James Webb Space Telescope is capable of observing star and galaxy formation occurring just a few hundred million years after the Big Bang, a period when the universe was a tiny fraction of its current age. This offers an unprecedented glimpse into the dawn of cosmic history. Alongside this, recent breakthroughs in detecting gravitational waves, ripples in the fabric of space-time caused by cataclysmic events such as colliding black holes, have opened another new window into the universe. These observations reveal phenomena that were completely beyond reach until now, illuminating the most violent and energetic processes in existence. We are truly entering a new era where regions of space that were once completely inaccessible are now open to scientific study, enabling a much deeper and richer understanding of the universe's history, structure, and the fundamental laws that govern it. Each new discovery brings humanity one step closer to answering profound questions about the nature of reality and the cosmos itself. Moreover, the advancement of new telescopes holds the promise of revolutionizing our knowledge not just of distant galaxies, but also of hidden objects within our own solar system. As technology progresses, these instruments grow increasingly sensitive, capable of detecting faint glimmers of light and subtle movements that once went unnoticed. Imagine standing on a beach, looking out at the vast ocean. With a pair of ordinary binoculars, you might see only waves crashing on the shore. But if you were to use high-powered spy glasses, you might spot a distant lighthouse or even a ship far beyond the horizon. Similarly, advanced telescopes equipped with state-of-the-art optics and enhanced imaging capabilities can capture light from objects lurking in the far reaches of our solar neighborhood. These telescopes employ multiple wavelengths of light, including infrared, which can penetrate through thick clouds of gas and dust that typically obscure celestial bodies from view. What might appear to be empty space through traditional observation methods could, in fact, be teeming with asteroids, comets, or even small dwarf planets that have remained hidden until now. This leap in observational power is reshaping our understanding of the solar system's architecture and the dynamic processes taking place within it, revealing a cosmos far more intricate and alive than previously imagined. Additionally, a new generation of survey telescopes has been meticulously engineered to methodically scan vast expanses of the night sky over prolonged periods. This innovative approach significantly elevates the likelihood of detecting celestial bodies that subtly change their positions against the seemingly fixed tapestry of distant stars. By extending our observational reach in this systematic manner, we stand on the brink of discovering not only previously unknown neighbors within our cosmic vicinity, but also unlocking deeper insights into their very nature, their composition, their dynamic behaviors, and their interactions within the vast celestial arena. Delving into the diversity of objects populating our solar system offers more than just a cataloging exercise. Each new discovery holds the promise of shedding light on the intricate processes that govern the formation and evolutionary pathways of planetary systems, including our own. By piecing together this complex puzzle, scientists aim to enrich humanity's comprehensive understanding of the cosmos, a universe that we inhabit, explore, and continuously strive to comprehend more fully. Turning our gaze toward the horizon of space exploration, The coming years promise an exhilarating epoch filled with anticipation and groundbreaking discoveries. Following the anticipated revelations expected in the year 2024, the trajectory of exploration is set to shift towards a more profound and focused investigation of our immediate cosmic neighborhood, emphasizing particularly the enigmatic landscapes of Mars alongside the frozen, mysterious worlds orbiting the distant outer planets. Mars missions are poised to ascend in ambition and complexity. Future ventures aspire to undertake the monumental challenge of sample return missions, wherein soil, rock, and other material from the Martian surface would be carefully collected and transported back to Earth. This endeavor would mark an unprecedented step in planetary science, allowing researchers to scrutinize Martian materials in unparalleled detail within terrestrial laboratories. Such analyses could unlock vital clues about the red planet's geological history, including compelling evidence regarding its potential to have once harbored life or even maintain environments conducive to life. Simultaneously, attention is set to intensify on the outer reaches of our solar system, where icy moons such as Europa and Enceladus captivate scientists due to their concealed subsurface oceans. These vast hidden reservoirs of liquid water beneath thick layers of ice present compelling habitats that might sustain primitive life forms. Upcoming missions are likely to pioneer technologies designed to penetrate these icy crusts, potentially drilling into these concealed aquatic realms to directly explore the biochemical environments they shelter. This daring exploration could revolutionize our understanding of where life might exist beyond Earth, broadening the parameters of habitability in the cosmos. An equally thrilling frontier lies in the detailed study of asteroids, especially those identified as potentially rich in valuable resources. These ancient, rocky remnants offer a dual promise. On one hand, they serve as living archives of the early solar system, preserving clues about its primordial conditions and the processes that shaped planetary bodies. On the other hand, they could become critical waypoints for humanity's expanding presence in space, providing essential materials for constructing habitats, fueling spacecraft, or supporting other logistical needs in deep space missions. Technological advances are expected to be the cornerstone of these ambitious endeavors. The development of more powerful and efficient propulsion systems is anticipated to drastically shorten travel times to distant worlds, thereby expanding the feasible scope and duration of missions. Robotics and artificial intelligence stand ready to enhance exploration capabilities, enabling increasingly sophisticated operations to be conducted remotely, particularly in environments too hostile or distant for direct human presence. These technologies will usher in a new era of discovery, with autonomous probes and intelligent systems undertaking complex scientific tasks with unprecedented precision and autonomy. Human exploration is also making a robust comeback on the horizon. The Artemis program, spearheading efforts to return astronauts to the moon, aims to establish a sustainable outpost, a permanent foothold on the lunar surface that could act as a strategic launch pad for further exploration, including ambitious missions to Mars. This international collaboration exemplifies the growing trend of pooling expertise, resources, and knowledge across nations to confront the immense challenges posed by deep space missions. The discoveries expected in the near future will serve as critical milestones, propelling humanity toward new chapters of space exploration. This next era will likely focus heavily on Mars, the icy moons of the outer planets, resource-rich asteroids, and the development of infrastructure to sustain human life beyond Earth. Each step forward is not merely an expedition into the void, but a profound quest to deepen our understanding of our place within the vast cosmos. Turning to cosmic rays, these are high-energy particles originating from the depths of outer space, bombarding Earth continuously. Most cosmic rays consist primarily of protons, though they also include heavier atomic nuclei and even electrons. Scientists generally have well-established expectations for their energy levels informed by various known astrophysical processes. Yet, some cosmic rays challenge these expectations by exhibiting energies far exceeding typical ranges. One key reason for such extraordinarily high energies lies in the extreme environments where these particles originate. Cataclysmic events such as supernova explosions, where massive stars end their lives in spectacular detonations, and the highly energetic regions surrounding supermassive black holes known as active galactic nuclei play crucial roles. In these settings, particles are accelerated to mind-boggling speeds through interactions with powerful magnetic fields and shock waves, akin to how a child on a swing gains height with each well-timed push. Additional candidates for the source of these ultra-high energy cosmic rays include neutron stars and gamma-ray bursts, phenomena so energetic that they emit brief yet intense flashes of gamma radiation. The extreme physical conditions in these environments enable particles to reach energies that dwarf those achievable in more common cosmic occurrences. Further complicating this cosmic mystery is the influence of magnetic fields not only within our Milky Way galaxy, but extending throughout the cosmos. These magnetic fields can trap and guide cosmic rays over vast distances, sometimes energizing them further in the process. This dynamic interplay suggests a universe that is far more active and energetic than initially perceived, where particles traverse immense stretches of space while engaging with complex mechanisms that amplify their energies beyond initial expectations. The existence of ultra-high energy cosmic rays remains one of the most compelling puzzles in astrophysics. It points to powerful and intricate processes operating on cosmic scales that humanity is only beginning to unravel. Continued research into these enigmatic travelers offers the tantalizing prospect of unlocking new principles in fundamental physics, deepening our grasp of the universe's most profound workings. Finally, the notion of objects transitioning between universes or dimensions occupies a fascinating place both in scientific discourse and science fiction. While largely speculative, this concept stimulates imaginative explorations of realities beyond our own, challenging the boundaries of known physics and hinting at the possibility of a multiverse, a collection of multiple, perhaps infinite, universes existing alongside each other. This idea continues to captivate minds, inspiring both rigorous scientific inquiry and creative storytelling about the nature of existence itself. However, it delves deeply into the profound and intricate realms of theoretical physics, particularly in the landscape of modern scientific theories that explore the very fabric of reality itself. Among these, string theory stands out as a fascinating and highly complex framework that pushes the boundaries of our conventional understanding of the universe. According to certain interpretations of string theory and related advanced hypotheses, our universe may not be the solitary cosmic arena we once believed it to be. Instead, this perspective introduces the compelling concept of a multiverse, a vast ensemble of numerous universes, each potentially governed by its own distinct set of physical laws and constants. In this extraordinary vision of reality, the notion of traveling or shifting between these alternate universes or dimensions becomes a subject of intense speculation and scientific intrigue. Yet, this is not a simple or casual form of travel akin to stepping through a doorway or moving from one room to another in our everyday experience. Instead, transitioning across these dimensions would likely demand conditions and energies that far exceed anything encountered in ordinary human life. Imagine it as requiring an extremely specialized and powerful key to unlock a door key that leads to an entirely different realm of existence. Without precisely meeting these extraordinary requirements, the portal to another universe would remain steadfastly closed, inaccessible to any conventional means. Furthermore, our understanding of what constitutes a dimension has evolved significantly in contemporary physics. Beyond the familiar three spatial dimensions, length, width, and height, scientists now propose the existence of multiple additional dimensions that are hidden from direct perception. These extra dimensions may be compactified or curled up into incredibly small scales, so minute that they evade direct detection by our current instruments. Nonetheless, their presence could subtly influence the behavior of particles and forces in the visible universe, offering tantalizing theoretical pathways for unusual phenomena that could, in principle, enable something resembling dimensional travel or interaction. Despite these captivating theoretical advances, it is important to emphasize that the ideas surrounding dimensional travel or interuniversal movement remain speculative and reside largely in the realm of mathematical models and conceptual physics. There is currently no experimental evidence demonstrating that tangible objects or living beings have traversed between universes. The field continues to be one of active research and debate, where profound questions about the nature of reality inspire both awe and rigorous scientific investigation. In parallel with these theoretical explorations, the ongoing year has witnessed several remarkable and enigmatic occurrences in the vast reaches of space, which challenge and expand our comprehension of the cosmos. One such phenomenon is the behavior of fast radio bursts, extraordinarily brief and intense pulses of radio waves originating from distant galaxies far beyond our own. Throughout the year, astronomers have identified a particularly unusual source emitting a repeating sequence of these bursts, a pattern unlike the fleeting, one-off flashes usually observed. This discovery has raised intriguing questions about the astrophysical mechanisms generating these signals and what they reveal about extreme cosmic environments. Another equally perplexing event involved the sudden dimming of a massive star located in a remote galaxy. This unexpected fading defied conventional explanations such as interstellar dust clouds or the star transitioning into a known evolutionary phase, like a supernova precursor. Instead, the star appeared to vanish temporarily before regaining its brightness, prompting scientists to explore new hypotheses. These include potential gravitational interactions with nearby celestial bodies or entirely novel types of stellar behavior that have yet to be fully understood. Simultaneously, the persistent mysteries surrounding dark matter and dark energy, components that together constitute the majority of the universe's mass energy budget, continue to captivate cosmologists. Recent observations, particularly those related to subtle fluctuations in the cosmic microwave background radiation, the ancient afterglow of the Big Bang, have suggested anomalies that challenge existing theoretical frameworks about these elusive phenomena. Such findings fuel ongoing debates and hint at deeper cosmic secrets waiting to be uncovered. Each of these extraordinary events ignites vigorous discussion within the scientific community, reinforcing the ceaseless human endeavor to decode the mysteries of the cosmos. The path from initial observation to scientific understanding follows a well-established, though often painstaking, process. When confronted with an enigmatic phenomenon, scientists begin by meticulously gathering detailed observational data. This may include precise measurements of celestial motions, spectral analysis of emitted light, or controlled experiments designed to replicate aspects of the phenomenon under laboratory conditions. With ample data in hand, researchers then construct hypotheses, carefully reasoned explanations that attempt to account for the observed facts. These conjectures are imaginative and inventive, pushing the boundaries of known science while remaining grounded in the principles of testability and falsifiability. Designing experiments or further observations to confirm or refute these hypotheses is essential, as empirical validation forms the backbone of scientific credibility. Upon testing, if the outcomes align with predictions, the hypotheses gain acceptance and contribute to the expanding body of knowledge. Conversely, if results contradict expectations, scientists must refine their theories or consider alternative explanations, embodying the iterative nature of scientific progress. Collaborative dialogue among experts enhances this process, allowing for diverse perspectives and critical scrutiny that help reveal hidden complexities and refine understanding. In tackling the most confounding mysteries, interdisciplinary approaches often come into play. Insights drawn from fields such as particle physics, astronomy, biology, and advanced technology interweave, enabling holistic investigations into phenomena that resist simplistic explanation. Over time, this collective scientific effort can unravel even the most baffling riddles, though some may remain elusive for extended periods. In the broader scope of the universe, it is conceivable that certain mysteries will forever evade full comprehension. The sheer scale and complexity of the cosmos, with billions upon billions of galaxies, each hosting billions of stars, imply that some aspects of reality might lie beyond the reach of current or even future scientific methods. Dark matter exemplifies this challenge. Although it exerts a gravitational influence crucial to the structure and evolution of galaxies, it emits no light or other detectable radiation, rendering it invisible to direct observation. Despite advanced instruments and ingenious detection techniques, its fundamental nature remains unknown, a cosmic enigma that might never be fully unraveled. Similarly, the quest for a unified theory that integrates all fundamental forces of nature, a so-called theory of everything, remains one of the greatest scientific pursuits. While the forces governing electromagnetism, gravity, and the nuclear interactions have been studied extensively, a comprehensive framework that seamlessly combines them continues to elude physicists. Such a theory may involve dimensions or principles beyond current human understanding, requiring revolutionary breakthroughs to comprehend. Beyond the physical universe, profound questions about consciousness and the origin of life continue to intrigue scientists and philosophers alike. Despite significant advances in biology, chemistry, and neuroscience, explaining how subjective experience arises from purely biological substrates remains an open challenge. The complex conditions that led to the emergence of life on Earth, coupled with the possibility that those conditions may no longer exist or be reproducible, deepen this enduring mystery. Ultimately, while the relentless pursuit of knowledge illuminates many shadows in the vast cosmic expanse, some enigmas may remain forever woven into the universe's very fabric. These timeless mysteries spark imagination, fueling humanity's insatiable curiosity and the enduring drive to explore and understand. They serve both as reminders of the limitations of our present understanding and as invitations to continue the adventure of discovery, where each new question opens the door to countless more, ensuring that the quest for knowledge is an infinite journey without end.